Okay, Shubham, started.
It's also showing that custom live streaming, yeah, service, yeah, no problem. Maybe I can go and check once.
I will send the.
Mm.
It's not for everybody, so I'll send.
Mm. Jadi, is it the same link, na, for
No,
YouTube?
no.
Okay, okay.
I'm sending. I'm trying to send. Okay. Check your message.
So, if this is a different, yeah,
Hmm.
link,
Hmm. It's
don't
not
we?
for. So I have not. This is not for everybody, right?
Yeah.
This is just for recording our.
Acha, okay.
Yeah.
Then it's fine. Good, no problem.
Yeah.
So, yeah, this we can actually put it later on, as I mentioned.
Yeah, exactly. Once everything is done.
That would be nice, yeah,
Yes.
because all the teaching things will be coming into
In the society
society
website.
thing, yeah. That everybody can also separately access whenever it's required.
Yeah, absolutely.
Yeah, where the others, it's already
Yeah, 20
oh,
participants are there.
only. What are the
Yeah, well,
participants?
they
There were
will
like
they'll come.
290 people that we sent
Yeah,
email.
they will come.
They will come anyway, Saturday. And here, everybody can unmute and speak, or
Yes.
yeah,
They
anyway,
can
anyway.
unmute and speak.
Okay, anybody can. Okay.
So Anindya has also joined, I think.
Uh-huh.
I will make you the co-host.
Mm.
I don't see Anindya though. Okay, maybe.
RGCV, ठीक है.
That is fine. Yeah.
That is fine.
Gaurav,
To
I don't know. Who is Gaurav?
this IIT Jodhpur is also there.
Yeah.
You can do step by step.
Yeah.
There is also Gitanjali waiting.
Yes,
Yeah.
Gitanjali. So I am messaging these people again that you have
Mm.
to put full name and institute name.
Mm. These messages can be seen by the waiting list. Waiting.
Yes,
Okay.
yes.
Oh, Ananda is here probably. Yeah.
Yes, Anindya is here. I made him enter.
Hello.
Morning.
Hello, Anindya.
Hello.
So things are going fast now. People are
Yeah.
coming in.
Yeah, because anyway, now it's getting time, na? People will now come. Sudipta, where is Sudipta? Sudipta is here?
He's
No.
here. He's here.
Is here? Okay.
Yeah.
No, but where Sudipta?
Is
It's
there?
not.
Is there? Shukrita is
Is
there.
it?
Yeah.
I can see his name. Sudipta. No, where?
Sudipto. As
Hmm.
Sudipto.
No, no, he's not here yet.
Ah, he's here, he's here. He's in the background.
Hmm.
As Sudipto.
Oh, meaning I can only see SM Rose,
No, no, no,
Shakya.
no. Go top. He's a co-host. He's a co-host.
Acha, go, acha, pause, pause, pause. Okay. So you can make also another post.
Mhm. Another has to be co-host. Okay. Yeah. So people are joining in. 40 people are in.
Hmm, 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 hmm.
Kothari, she doesn't understand.
Sandeep, Amitan, Mansi.
Yeah, Mansi Kothari was hanging out yesterday also without changing the name.
But can you check that, your list?
Yeah, she's there. She's there.
Is that- Then
I
maybe
will
Mansi is
can.
ad
a
I will
Arindam
admit her.
student.
Yeah, I will admit her today.
Admit her and tell her, because I told her in person that you have to give the institute name.
Yeah.
Now she is already here, maybe.
Yeah, I have admitted. I have
Yeah,
admitted.
yeah. I think everybody should actually change, meaning their name along with the this institute name.
I have not done that because basically I don't know how.
I can do it for you.
Mine is already written, yeah, SPS Genuine.
It says I'm not allowed to view my profile.
Not allowed to zoom, what?
View my own profile.
Oh, really?
I tried to do it, it said you're not allowed to view this participant's profile.
Okay. I am doing it. Don't worry.
Right. Good. Thank
Stop.
you for giving me an institution. I have lost the email I sent to everybody. Yeah, just a second.
Okay, we are almost there at 5 minutes before 10. So we have 49 participants. Make it 50.
Not yet 100 participants. It's only
It
53.
will it will happen. It will happen.
It'll happen, yeah, yeah. So, for sure. People are not putting up their, institute
Yeah,
name.
I don't see why that is the
Hmm. Where is that message I sent everybody?
Which message?
Or where is that file where all the participant list is there?
You have, na, from your Gmail. You have sent it from Gmail to all the BCCs. Yeah.
Yes, but
You again
then
send one.
they have sent like hundreds
There-
of emails.
yeah, yeah. There was this yesterday
What
also.
was that? What was the title? Do you remember?
Title was, please join with your name and institute. Please join together in your typing.
That is helpful because then I can find it easily.
Okay, I'm here.
Okay.
Great.
Thank you, Sudipta.
Morning, Sudipta.
How are you feeling,
Hello,
Sudipta?
good morning.
You feeling okay?
I'm okay. I'll be fine.
Voice is not okay.
No, it's better. It's better.
Okay. Okay, I think
Let
it's
me know when I start.
Yeah, it's 9:58. I'll just start. Okay, thank you all for joining for today morning's common teaching sessions, as well as this will then go on to become breakout sessions for the 5 different tracks on which the teachings are going to be done for this FCS workshop. The tracks will be available to you in due course of time once the session ends by um, 4 p.m. So today there are 5 common talks in all the tracks. Sudipta Maiti will be teaching FCS basics. Anindya Datta will be teaching TCS PC in the ultrafast track. Chandrabhas Narayana will be teaching Raman spectroscopy basics in the Raman track. Then that will end at 1 at around 1 p.m. And then there will be a lunch break for an hour, and then the common talks will resume from 2 p.m. with A.S.R. Koti taking AFM basics, and then continue on with single molecule basics being taught by Arindam Chowdhury from IIT Bombay. So it's a feast of very nice speakers and talks and sessions. So just have some food and a little bit of tea and enjoy. The first speaker, of course, is our own Professor Sudipta Maiti, who started the entire idea of this workshop. So, Sudipta, it's all up to you now.
Thank you, Jyotishman. Can you hear me? Can everybody hear me well?
Yes.
Yep.
Okay, good. Jyotishman, if you also allow Sudipta's tab, I might need it for my whiteboard. It's waiting in the waiting room.
Sudipta's tab, okay. It's there.
Okay, good. So, oops. Mute Sudipta's tab, please. Okay. Hopefully that works. To get the people in, there are many people. Achha, you are getting them in.
So maybe we can start a couple of minutes late.
Yeah.
Yeah, waiting.
This is when people are coming in.
Coming in, actually. A lot of people are coming in now.
Because I just sent the message. Maybe meanwhile, since we do have an audience, you can tell them how this all began.
Yeah.
How to do what?
How this all began. That is
FCS.
quite
How this
an
all
inspirational
began.
story.
I think
Why
they
don't
heard it
you say that?
yesterday. Yeah, so it all began when we decided that people need to build their instruments. I used to get a lot of requests because I built a what is known as a fluorescence correlation spectrometer, and I decided that I will teach everybody, but it's like teach a man to fish and he can eat for his lifetime. So we'll build instruments together and they will take those instruments home. So luckily, the Department of Electronics, it's called Maiti now, the Ministry of Electronics and Information Technology, kept some money for me to build mostly from Indian components, 10 or 12 such instruments. And I got a fantastic bunch of people. I made it mandatory that the faculty member and a student both have to be there for 3 weeks. And they were there. We dined together, wined together, and played together and built 12 FCS microscopes, and 2 remained in my lab for future things, and 10 were given away to the 10 teams. And I'm so delighted. So I thought it'll be a one-off thing or maybe a follow-up session. That was 2009. And here we are in 2024. It has grown by leaps and bounds, thanks to the mainly the enthusiasm of my friends, my close friends, but also the enthusiasm of students like you. And every year we have this workshop which shows hands-on how to do things. This particular thing is, I think, originally Shobhan Sen's idea to do it over online so that lots of people who cannot be admitted to the in-person workshop gets a flavor of it. And because I think we had like 200 or 200 plus applications, and we have only 80 or so seats for the in-person thing, which will happen in November. So this is, and also the other idea is to do the basics, cover the basics now.
Hello.
Hello, whatever.
Maybe Sudipta froze.
Froze. Yeah. Maybe some power or something.
You can continue, Shobhan.
No, yeah. So I think, regarding this particular online and the version of our FCS meeting, it was discussed. I remember in the last 2 FCS meetings in Mohali as well as in Trivandrum, and everybody was actually in that our executive council meeting that we were actually discussing, and many of the inputs came from both students and the faculty that you should start some kind of a meaning the playing of this system that and give some kind of basics first, so that we actually can cover much more advanced levels during the hands-on session. So I think that was the plan, and obviously, as we've also mentioned that I think just to also accommodate as many as number of people together. And in fact, Sudipta was also mentioning yesterday, like when we had this big people were speaking, and we did it during this COVID time, when IIT Bombay actually did this organization, Anindya and everybody. And that was fantastic because we even went to the best possible labs in the world, including, I think, Eric Betsick lab, to show that light sheet microscopy and so on. I think that was very nice. And we thought that maybe this online version of the FCS meeting can be also a nice addition to this one. In fact, after a lot of discussion, that we thought that, okay, let's start it this year, even though we know that we got a little bit late to send out all the information regarding this online session and so on this year. But again, this is the first year. I'm sure the next year onward, it will be much smoother in that manner. So with this, I believe we hope to have a much bigger, participation now on this online session, and take up as much as possible things, because it will be also extended over the 2 full days, and we can have a lot of time to actually also discuss over online. And I'm sure that students will be having many more queries. They can also think about the queries over the time, and then again come during this offline FCS meeting in November, and we can discuss even more during this roundtable and during this general session and so on. So I think that's good enough. But then what happened? Which will
Sudipta
is back. Sudipta is back.
I don't think so. I don't think so.
He's back. He's back.
We admitted somebody who's with only Sudipta. Yeah, that's it.
Very sorry about that. I'm a bit under the weather, so I am doing it from home meaning a guest house room, where I understand that the connection is not very stable. So I have put it on my phone thing, and hopefully it will work. So without go to the main thing. Okay, let's start with a fluorescence correlation spectroscopy. You learned a lot of things, but let's start with this. Okay, all right. So can I share my?
Yes.
Okay. Okay, full screen?
Yes, it is
okay.
Full screen now.
So what is FCS, as we call it lovingly, fluorescence correlation spectroscopy? It actually determines molecular properties from photon arrival times. That's all it does. you have something that is fluorescent, and you just time when the photons are coming in. So it's a time domain technique. It's called spectroscopy, but there is not really much spectroscopy in it in that sense. We don't have dispersion, color, etc. I mean, fluorescence, you select it and you look for the photons. So photon arrival times. All right. So what does the photon arrival time tell me? It can tell you a lot of things, which is surprising, really. You can have a fluorescent molecule by itself, or a bigger molecule or a bigger particle which is tagged with some fluorescent molecules. So you can tell the size of that. If it's, suppose it's a protein and it's attached to some fluorescent tag, or it itself is fluorescent, such as GFP, you can tell its size. You can tell its reaction kinetics. For example, protonation of GFP. Okay. You can talk about conformational fluctuations. Suppose you have a FRET pair and you have a motion that brings them together occasionally. You can look at that. You can get rotational correlation time. For those who do TCSPC, you'll be familiar with this rotational correlation time. You can measure phosphorescence lifetime, the triplet lifetime. You can measure the fluorescence lifetime. Okay, in that way, it competes with TCSPC. Of course, everybody has his own domain, so TCSPC in its domain is very good. But the arrival time, since they're recorded with a good instrument, from picoseconds to seconds, all the things that happen across these time scales, different things, can be actually interrogated with FCS. So we analyze things across time scales. Let's try to understand it, how it does. So let's try to understand with the simplest possible case. You have some material, something, in which there are some fluorescent molecules. You see the blue, and let's focus on one. You are exciting one, and you are detecting photons from that one, the one that is circled here. You just excite and observe. And there is not pulse excitation. You can do that, but it's say continuous wave excitation. So occasionally, randomly, the thing gets excited. And then since it's a fluorescent molecule, emits a photon. And you make a record of that time. So you see at the bottom, the graph that you have a record of that time. And suppose I'm recording in nanosecond time scale. I see the first photon came in here, the second photon came in here, third photon came in here, etc. Can people see my cursor?
Yes.
Oh,
Yes.
good. So you get this. You will see that it's nanoseconds, and I have drawn things which are like few nanoseconds apart, and I haven't drawn anything which has two photons coming very close together. There is no photon that has arrived very close to another photon. It's sort of anti-bunched. No, not bunched together. They're spread out in the nanosecond time scale. I'm just recording the time of arrival. Why are they anti-bunched? They're anti-bunched for a very simple reason. You have a molecule, that single molecule getting excited, and it emits. But this emission, after the excitation, takes some time. It is the fluorescence lifetime. Of course, it doesn't take one single time. It stochastically emits. But if its fluorescence lifetime, let's say, is 3 nanoseconds, which is very common, 3, 4, 5 nanoseconds, then it's very unlikely that you'll see a photon at 0.1 nanoseconds. This is why the things are anti-bunched. You don't see once, because there is only one molecule, right? So once it has gone up, so you see one photon, once it has emitted, you see that photon, it has to go up again and emit again. And even if you pump a lot of light into it, it can go up very quickly, but coming down will take time. Will take time because it's bound by the fluorescence lifetime. So the probability of detecting a second photon, look at the right graph, at very small time, for delay time after the first photon, is negligible. Okay, so this is a nanosecond time scale, and then the probability increases and goes to some steady state depending on how hard you are exciting. So far, so good. Photons are anti-bunched if you have single molecule, because obviously they have to wait for some time before they can emit. Once they have emitted once, they have to go up and wait for some time. Oh, good. So this actually has some information. Okay, so that information is that if your probability really goes to 0 here at short times, it's a backward proof that you're looking at only one single molecule. Why? Suppose you are looking at a larger area here, and there are two molecules. They're not connected to each other. So the red photon that you see can actually come, it's not very unlikely if it comes from the second photon, second molecule. Right? So if you have multiple molecules, your ability to get paired photon quickly one after the other increases. So the probability would not go to 0 if you have 2 molecules or 3 molecules. The probability at 0 time will be something. So by looking at how deep this thing dips, theoretically it dips to 0, the probability of getting a second photon right after the first photon, you can tell how many photons are there. These days, there's technologies which people are talking about single photon emitters, and you can actually tell by this photon correlation whether if they're perfectly anti-banched and your probability is 0 at very short time, you know there is only one single emitter, and they're emitting one photon at a time. There are funny processes called bi-exciton processes where one single molecule can put 2 photons out, and there also you will see then that therefore you don't have things coming to, well, it will come to 0, but it will come to 0 at a very short time. So here's some beautiful paper that one of my friends, George Thomas, and his student Vishnu and their collaborators published a few weeks ago in Nanoletters. Okay, so these photons are anti-bunching. Very simple. It's actually the simplest thing to understand in the whole of FCS. That photons are anti-bunch because they have you have one molecule and they have a fluorescence lifetime. Okay. Now, what happens if you look at a longer time scale? So longer time scale, other processes can come in because the molecule can change its character. Very simple thing is photophysics. The molecule occasionally can go into a triplet state. Okay, the triplet state is a state that is very long-lived and it is not going to fluoresce. So it is going to be a dark state. So this triplet state lifetime, the way it comes back is usually many microseconds. Okay, 2, 3, 4 higher microseconds. So the molecule occasionally, maybe every few microseconds, will get stuck in a dark state for a few microseconds. Okay, so if you plot your photon arrival times in a longer time scale now, zoom out in microsecond time scale, you will see that when the molecule was in the singlet state for a while, for a few microseconds maybe, you got these photons coming together. And they are anti-bunched at the nanosecond time scale, but they're bunched in a microsecond time scale because all singlets, it was singlet state, and they all kept going down and going up and going down and going up, etc. But when they came to a triplet state, this gap in between, they cannot emit. So again, the triplet state has a lifetime, which is microseconds. So it will be silent for a microsecond. So same thing looking at a microsecond time scale looks bunched. So if you plot the probability, then the probability will be that things will be bunched. It's not anti-correlated, it's correlated. If you start getting photons at some point, you'll keep getting photons until in a microsecond time scale, you don't get photons for the while. So what I've been talking till now is basically, hand waving, saying the probability is low, that you'll see something within 0.1 nanosecond. But if you have seen something at a microsecond time scale, the probability high, you will see another photon. That means this molecule is in the singlet state. Another photon probably 100 nanoseconds later or 5 10 nanoseconds later. So, however, occasionally at a microsecond level, the probability will be low again. So there's the kinetics we're looking at. And these kinetics, we need to characterize. Suppose I am interested, as I said in the beginning, what it can do for you. Already you have looked at 2 things. It can tell you if there is a single emitter. And second, it can give you, if you give you fluorescence lifetime, because the single emitter thing, the way it recovers to the normal probability is at a time scale that is given by the fluorescence lifetime. At longer than fluorescence lifetime, you have this anti-bunching is gone, and you see the probability recover. You go much longer, in the triplet lifetime, phosphorescence lifetime time scale, you see they're bunched again, positively bunched, sometimes dark, sometimes positively bunched. And you should be able to get these numbers out of this instead of hand waving. So here, so you heard me talk about fluorescence. So that's first part of fluorescence correlation spectroscopy. The spectroscopy part I already said, don't pay any attention to it. So you have to learn the second part, which is correlation. The correlation is basically a mathematical trick by which you can get a number, fluorescence lifetime, etc. Instead of going for each individual photon arrival time, making how much time that it takes for the second photon to come in, and going event by event, event by event, event by event. There's one shot way to analyze this data. I have broadened the photon arrival times because obviously we don't have infinite time resolution. So basically it's a probability distribution of photon arrival times. So what I'm trying to tell you is that there is something called an autocorrelation function, which will give you numbers. That probability curve I do, how do I draw that probability curve without going through painstaking every photon thing? Those of you who already know TCS/PC, what I'm doing is pulling the plug on you. There's no sync signal. Things arrive at arbitrary times. Can you still tell the fluorescence lifetime? You can, and I'll tell you that. Okay, so there is no sync because when the photon arrives is quite random, except that at sub-nanosecond time scale they're anti-bunched, and at many microsecond time scale they are bunched because of the singlet and the triplet candidates. So how do I do it? Since I cannot have a trigger, if I have a trigger, I can always measure, like in TCS/PC, Anindya will tell you, how long did it take for the photon to arrive? I have no trigger. They're arriving at random times. Okay, but I can do a masking. So I prepare a mask, which is the same, this function. So this is my photon arrival times. And what I do is prepare a mask, the dotted line, and if I put them one on top of each other, they're always, I don't have to go photon by photon. I put the whole pattern on top of each other. Of course, if they're on top of each other, what I do, I multiply the two patterns. So one I call FT, the fluorescence arrival time. The second thing I call FT plus tau. Tau is, I can also translate the pattern a little bit and multiply. Basically asking the simple question, if a photon had arrived at, say, time 0, or time t, what is the probability it will arrive at? Another photon will arrive at t plus, let's say, 0.1 nanosecond. You know that the probability is low. But if you're talking about microseconds, then if the photon arrived, the first photon arrived at some time t, then there is high time that within another 100 nanosecond or something, within a bunching time of a few microseconds, another photon will arrive. So this thing is plotted in a microsecond kind of time scale. So they're bunched because the molecule is dark in these times, bright in these times, dark in these times, bright in this time. But the mathematics works whether it's anti-bunching at nanosecond time scale, bunching at microsecond time scale, or whatever you have. Okay. So what do? I multiply the two patterns. If I translate them by this tau amount, then, and I'm multiplying the two, this is just a normalization factor. I multiply the two, and tau is small compared to the width of the bunching, small compared to a microsecond. I'm talking about triplet kinetics here. Then they'll be making a large number because you'll multiply this point with this point, this point to this point, and it'll add up. We average out throughout the pattern. The pattern may have billions of photons. Okay, and I don't have to go one by one. I take the whole pattern, multiply itself, then ask the question, if the photon probability, detection probability is high 100 nanosecond later, then this will give rise to a large number because I'm pretty much squaring the function. At tau equal to 0, I'm exactly squaring the function. At tau, which is small compared to the bunching time, which is the microsecond time, it's still large. But if I go further and further, increase my tau, then the pattern is multiplying mostly with 0 here. You see, again, I'm doing FT plus tau. So I have translated it. I'm making a product of this point to this point, this point to this point, this point to this point. Everything is 0 until I hit here, and there is a small number. There's a small number. The number sort of increases, but then starts falling again because this guy is falling. So as you go further out compared to the bunching width, characteristic bunching width, there is no one width, but there is a characteristic width. If I go further than that, my product falls. Ft times Ft plus tau falls at tau large compared to the triplet lifetime. In this case, the example is triplet. What you will see for anti-bunching, you'll get a negative thing because at very short tau, the probability is low. It will increase later. So you'll get a negative thing and a positive thing in a microsecond time scale. Okay. Till now, everything is fixed. I'm just looking at a single molecule, triplet, and singlet kinetics. Okay. Now, something that I won't explain here is that this correlation thing works even if you multiple fluorophores. Of course, your anti-bunching depth will go down and other things will happen. Your total height of this function, normalized function, will go down as you have multiple molecules. But it basically works because a molecule and its neighbor, they're not correlated to each other. So they each contribute independently to this. So the correlation function is defined sometimes because you'll get confused talking to two different FCS people, sometimes defined as this, the fluorescence at time t times fluorescence at time t plus tau divided by this normalization factor. Another convention is that you take an average fluorescence and only look at the fluctuations about the average. That's called the delta F. Then you multiply delta Ft and delta Ft plus tau. They have exactly the same information, except in this way of defining, your correlation function goes to 0. If the previous way of defining, your correlation function goes to 1. Okay, so never get confused because different machines, commercial machines, can follow these two different conventions. Okay, so now let's look at what was happening with our molecule. So here, the correlation function across, I said, from picoseconds to seconds, almost a second. And this my student Rajiv Abhayankar plotted now 12 years ago. And he made a very sensitive fluorescence correlation spectrometer, which still, I think, gives some of the best sensitivity any machine in the world, definitely more sensitivity than the commercial machines. But you see here, I told you that the probability will be low at time scales which are, so this is milliseconds. So 10 to the minus 6 millisecond is a nanosecond. Okay. So at time scale, and this is a log scale. So this is 100 picoseconds, this is 10 picoseconds. So at the order of 100 picoseconds or so, this is rhodamine molecule. So its lifetime is about 2 or 2.5 nanoseconds. That in the order of time is sub-nanosecond, the probability, the correlation is very low. Okay, it's a really single molecule, but the background adds up, so you don't get a real zero. If you filter everything right, you'll get closer and closer to zero. This was just a demonstration, so we didn't go to that. But you see that you can plot a correlation function. I want you to appreciate the fact that you're doing an experiment, simple experiment actually, as you'll see tomorrow when we demonstrate it from the lab, and that can gather data and analyze data over 10 orders of magnitude in time. Okay, and every part of that data has some actual significance. So this part has the significance of anti-bunching, and you know that this is the fluorescence lifetime. You can measure fluorescence lifetime, as I said, without any sync function. This is the fluorescence lifetime, and you can plot it and see this will be about 2.some nanoseconds. And then it goes up because of the bunching part in the microsecond time scale here. Okay, so it goes positive. So it was coming to 0, then it goes positive. Then it decays again because this bunching times your correlation, if I go back here, you come down to here, then the correlation function decays again. So the correlation function decays. There's a little bump here, which is due to something called diffusion. I'll come to that. But the point is that it is very close to 0. It is very easy to understand. This is anti-bunching due to the lifetime, fluorescence lifetime. And it goes positive because of the bunching at microsecond time scale due to the triplet state, but it decays again because of the triplet kinetics. So you can measure fluorescence lifetime and triplet lifetime right from this. And you don't need any sync pulse. The photons are coming randomly. You're just cleverly analyzing the data. What is the probability I'll get a second photon if I got a first photon at t? Okay, that's all you are analyzing. Okay, so if you have understood that, that's basically the basis of fluorescence correlation spectroscopy. Let me now make it a little complicated by going to moving particles. Till now, I didn't talk about particles moving at all. So now I'll say moving particle, let's say a fluorescent molecule in solution. So they are doing their diffusion, right, in the fluorescent molecule, small molecule in solution. They're randomly moving about. Okay, so there's some kinetics, and I have to figure out what that kinetics tells me. And I'll tell you in advance that kinetics tells me about the size of the particle because it tells me about the diffusion constant of the particle. So let's come to that. Okay, so okay. Okay, here. So how do I look at the kinetics? I look at it with fluorescence. And remember in the second slide or so, I put a circle around a molecule that was telling you that I have techniques by which I can look at a very small volume within which there is only one molecule. Okay, I'll have to come to that, but I think I'll have to go to my tab or tell you something. Okay. Okay, let me just try to do it here because I have only 20 minutes left. So what we can do with something called a confocal excitation detection, I will talk about that in the afternoon today. I can look at a solution and a very small volume within that solution. And I told you that now it's more complicated because molecules are moving about. So what kind of bunching, anti-bunching am I going to see? Let's think about it. Okay. So here I put some molecules, which are the green bright ones. Right now, don't worry about the black ones. The green bright ones, and this little shape that I have put in is the area I am looking at, the area I'm exciting and picking up fluorescence from. The way I do it is by using a pinhole. I will talk about it in the afternoon. So imagine I can only see this part. So my fluorescence still fluctuates. In a sense, you have bunching, anti-bunching still coming in. Not anti-bunching, that's really other, but there is some kind of bunching coming in. Why? Because when you're looking at a small volume and the molecules are moving randomly, those molecules occasionally, there will be how many molecules here? 6 molecules in this, right? But at the next moment, one of the molecules can go out, second molecule can go out, and something can come in, but it's not going to be 6 the next minute. Okay, it may be 5, it may be 7. If 2 molecules come in, 1 go out, then it's 7. So there is a fluctuation going on, but at some particular time, if you have more than the average, let's say the average is 5, and you may have 10 because of accident, basically, because of fluctuations. Many molecules have come in. They don't talk to each other, so they don't know another molecule is occupying in the same volume. So they're just coming in their own sweet time. So if you have 10 molecules, I'm asking now, is this going to be bunched? Think about it. 10 molecules by chance are in the we call probe volume, the volume I'm looking at. Next moment I look at, next moment, maybe next microsecond, I look at. So as I said, these 10 molecules, which is much higher than the average 5. So if I pick up the whole fluorescence, it's twice the average fluorescence. Let's call it 2F. Next microsecond, am I going to see that decrease by a large amount or increase by a large amount? Sorry. Well, you tell me that, wait a minute, how fast do they move? If their movement is slow compared to 1 microsecond, you'll see same 10 molecules next microsecond. Second microsecond, yeah, I tell you that they move at 100 microseconds, for example. Then say, okay, it's at the second microsecond, first microsecond after the first measurement, t plus tau becomes 1 microsecond, tau becomes 2 microseconds. You're going to see the same high compared to average 10 molecules. At 10, 20, 30 microseconds, you're going to see some change because that's the time scale at which the molecules can come in and molecules can go out. And so the change is, if you have a high fluorescence, it cannot change instantaneously because the diffusion takes time. In this case, say it takes 100 microseconds. So if you do a correlation function for short time compared to the diffusion time, 100 microseconds, you'll see high things. So again, you are going to see a positive correlation, kind of bunching, because you had lots of molecules coming. The way the fluorescence correlation function works, you can see negative also. Suppose you have only 2 molecules. It's not going to be 5 very quickly. It will take its time. So it goes negative, but I'm Ft and Ft plus tau, both are negative. Again, it contributes positive. So both positive fluctuations from average and negative fluctuations from average will give you the fact, since they're bunched, the negative thing is also bunched because things cannot rush in quickly. Positive things are bunched because the things cannot rush out quickly. You get positive correlation function. They will each contribute. But this contribution would go smaller and smaller because at 100 microseconds or so, the number of molecules is no longer related to the original number. So the bunching is at the order of 100 microseconds. So if I go back to the original thing that I had, you'll see that there is a little bump here. And if I expanded it out, you'll see that's actually the rhodamine in solution. This whole thing is taken from rhodamine in solution. At nanosecond that the rhodamine moves doesn't make a difference, because in 1 nanosecond, the rhodamine molecule is pretty much fixed in that time scale, even though it's 3, but in 1 nanosecond doesn't go anywhere. So in this little bump, if I just cut this out and expanded it, you'll see there is a extra correlation, which is due to this bunching, due to the diffusion. Occasionally there is too many molecules and occasionally there are too few molecules, about the average. And what you see is that correlation goes down to 0 at time scales of, let's say, 100 microseconds. Okay, because diffusion makes the numbers at that time scale apart random. Okay, that's all there is. That's all there is to understand in the fluorescence correlation method concept. How I do it, where I put a lens, how I detect it, etc. That's a different thing. Those are details. Those are experimental details. But conceptually, when you look at the correlation of photons, arrival times, you can get many informations at different time scales. You can get whether it's a single photon source, whether it's what is its fluorescence lifetime, what is its the triplet lifetime, what is its diffusion time, all from the same curve. Okay, so that's really fantastic. And what I'll show you is that also there could be other things. I told you kinetics, fluctuations due to, say, protonation kinetics of GFP. My first paper was on GFP protonation kinetics, on first paper on FCS. So how is that going to contribute? Well, that will have its own time scale, right? Randomly, but there is an inherent time scale, let's say at 100 microseconds or maybe 10 microseconds, a proton will come in, but it's an equilibrium. So the equilibrium is shown here. Sorry, we're a little disorganized today. Yeah. So you have a protonated state and unprotonated state, and the fluctuation is going between protonated and unprotonated, because nothing is really absolutely static. When you say something is in equilibrium and A goes to B, B goes to A, any given molecule is going to B, any given B is coming back to A, any protonated GFP is going to deprotonate maybe in 10 microseconds, any deprotonated GFP can come back and protonate, very much like the what you see in the singlet triplet transition. Sometimes it's dark, say protonation makes it dark, which it does, and deprotonation makes it bright, similar to the same thing that you have seen for singlet triplet dynamics. You'll see a dynamics, which will also additionally contribute to your correlation curve. So I'm also getting chemical kinetics from here, which is really surprising. How do you get chemical kinetics? You get chemical kinetics, you typically measure chemical kinetics by moving the population in one side and look at it relaxed to equilibrium. Okay, I'll show you an example. I have a jar of water, okay, and I don't know if you can see it well. There is a level, okay? And if I change the equilibrium like this and bring it back to equilibrium, so I have taken it out of equilibrium, bring it back. It'll take some finite time. It's very difficult to see with water. Some finite time for it to come back to the equilibrium. It's a bulk movement. Okay? And it comes back. And if you could measure that time with a fast camera, this is, of course, gravity-driven thing. You can see how quickly water can flow. It's actually can be observed in with ice. So honey, the flow is much slower, right? So I do make it go outside of equilibrium, ask it to come back, takes some time. You can see about a second. Outside the equilibrium, comes back, but takes a second. You can see it coming back. So both are under the same gravity. What is it telling us? It is telling us about how quickly honey can flow versus how quickly water can flow. It gives its viscosity. So this experiment where I drove the system out of equilibrium and then brought it to equilibrium, it took some finite time. This is how I measure kinetics typically. In high school, in your college, this is how we have done things. You start a reaction, you watch it go to the completion, take the time, plot it. It has something that you read out. It could be read out, could be fluorescence, and you can fit some sort of exponential, multi-exponential, and you get the kinetics. Here, how am I going to get the kinetics? Really, I'm telling you from that bunching, from the bunching of the things, because of the fluctuations, I'm getting some kinetics because I'm that time scale of those fluctuations, 5 goes to 10, 10 goes back to 5, goes to 2, comes back to 5. This time scale is also denoted by diffusion. So there's a philosophical question here. In this bulk thing, I measure something, and in that microscopic thing, I measure something. Are they the same really? They are. Under some bounds of disturbance, they are. This is called the fluctuation dissipation theorem. So there's statistical mechanics in it. But the point is, whatever you find from spontaneous fluctuations is the same time scale you can find from bulk departure from equilibrium. If you look at this water carefully, I don't know if you can see it. If you can look at the top level, or if you go to a pond and you're bored and you're looking at the pond, and what happens is that there's always some disturbances, some wind, something. You'll see little ripples on the water, like you see ripples on the water because I cannot hold them very steady. Okay, I'm not really making them depart, but you'll see ripples. The question is equivalent to how quickly do those, some place there is a ripple which is above the average height, the water will come down. You know that, right? How quickly does it come down versus this whole departure from equilibrium, macroscopic departure from equilibrium. The timescales are the same. That's why I can measure it in fluorescence fluctuation spectroscopy, get the chemical kinetics, A going to B, B going to A, and it is equally valid as measuring it from a macroscopic departure from equilibrium. But it has a great advantage over the macroscopic departure. What is that? And I will end my talk here. I'll tell you a little bit about something, but I'll end basically my talk here. The macroscopic departure from equilibrium needs you to change, make a T equal to, at T equal to 0, you have to hit the system. At T equal to 0, I am turning the system. And then so I have it here, and T equal to 0, I turn back, and the thing comes to equilibrium, right? I have to drive the system to make it go away from equilibrium, put my T equal to 0 there, and look at it coming back to equilibrium or coming to equilibrium. When I look at spontaneous fluctuation, like the little ripples on the pond, okay, I do not have to force the system go out of equilibrium. These little ripples, even at a molecular scale, are always there. That's the concept of temperature comes from this, because every mode has half a kT as temperature T, half a kT of random energy in it. So that mode could be translational mode, could be vibrational mode, could whatever, but everything is always fluctuating as long as it's at a finite temperature. Where fluorescence correlation spectroscopy is harnessing those spontaneous fluctuations to determine the kinetics, which will be the same kinetics which will determine if you could drive the whole system out of equilibrium. So without perturbing anything, taking care of the normal perturbation, without caring about t equal to 0, because the correlation function really gives me that power to analyze these random photon arrival times. Without the t equal to 0, I can get kinetics. And that's where I stop today for the initial thing. Okay, I'll come back for a part of the crowd for how to do it, optics and all that. Okay, so I'm open for questions.
Thank you. Thank you, Sudipta. Thank you very much for a very invigorating talk and going through the concept of FCS. So now let's open the floor for questions from students. Please unmute yourself and ask questions after you raise your hand. Okay.
Come on, be informal here.
Okay, Rahul Yadav from A.S.R, Bhopal. Rahul, can you unmute yourself?
Go ahead.
Sir, actually, sir, can you hear me, sir?
Yes.
Yeah.
Yes.
Sir, I am just confused. Can you simply explain about the bunching? It is just like grouping or ungrouping. Like I am very confused in this word particularly.
Yeah, if you have heard it for the first time, it will be confusing.
Yes, sir.
So I'm asking a very simple question. I have seen one photon. When do I see the second photon? As a function of time. Do I see a second photon? What is the probability of seeing a second photon? Let's say within the next 100 picoseconds. Let's ask that question. I've seen one photon. That means the system has done this. If you look at this, it has emitted. The first photon I have detected because the system has emitted. Oh. Look at the... okay. Would come here. Yes. Okay. So look at the red arrow down, going down. So it has just emitted. Oh. My computer has its own mind. Let's see. Okay, look at the left graph. So it has come down. That's for your first photon.
Okay. Yes, sir.
There is a finite time taken for the second photon to be seen. I'm pumping it hard. So as soon as it comes down from the ground state, it goes up again, let's say. I'm pumping it hard. Would it come down in the next 0.1 second, picosecond or 0.1 nanosecond or whatever, 10 picosecond? No, because I'm saying there's a lifetime, process lifetime. So it gets stuck. My mouse is not working. It gets stuck in the bottom, the sort of ground vibrational state of the excited state. Okay? It takes a finite time. Say it's 3 nanoseconds is its lifetime. So then it is very unlikely that it will come down in the next 10 picoseconds. It has just gone there. So if you take a probability distribution, you do this experiment many, many times, then your probability of getting a second photon after the first photon is low when the time scale is small compared to the fluorescence lifetime. But if you ask this question, okay, can I see a second photon? What is the probability of my seeing a second photon at 1 nanosecond? Probably it's not so low because 3 nanoseconds is the lifetime. At 3 nanoseconds, 10 nanoseconds, it becomes saturated. There, it has enough time has elapsed, so the photon will be in the ground, the molecule will be in ground state, it can go back up. So if I plot that on the right curve here, the probability of seeing a second photon, let's see one photon, probability of seeing a second photon is very low immediately after seeing the first photon, but it recovers with the time scale given by the fluorescence lifetime, because it needs to come down to the ground state to emit another photon, and that has a finite lifetime. So that's anti-bunching at time scales which are short compared to the fluorescence lifetime. Got that part, Rahul?
Yes, sir. Thank you so much, sir. It was very bit confusing and new word.
Yeah, Sudipta, there is a close by question from Chanchal Sharma, IIT Jodhpur. Okay. Is there any specific information from anti-bunching that you can get?
Okay. So the two things I told you about, that if it goes to 0, you see the way I have drawn this curve here, goes to 0, that means there is only one single emitter. See, if there is a second emitter, second molecule nearby, and you are, without knowing it, you are also looking at that, that can emit a 0.1 nanosecond after the first one emits because they are not related. So your probability is truly 0 only when you have a single emitter. So it tells you that you have a single emitter. Okay, when you take a particle, small, sometimes people work with quantum dots, etc. If a small particle or these nanodiamonds where you have NV centers, you want to know how many emitters are there. You do this anti-bunching experiment, you look at it at sub-nanosecond time scale. If it's going close to 0, you have guaranteed one emitter there. Okay, if not, it will go to maybe if 2 emitters, it will go exactly to 0.5. Okay, 3 emitters, 1/3, etc. So it tells you that. And the second thing it gives you is the recovery time is same as the fluorescence lifetime. It's actually a sum of inverse of the sum of the rates of excitation or de-excitation. But I'm saying at high fluence, the excitation is very quick. So you're controlled by the de-excitation, which is the fluorescence lifetime. So the curve tells you the fluorescence lifetime without doing any time-dependent experiment. Without doing any pulsed excitation. This is time dependent, but not pulsed excitation. So both of these informations you can get from anti-bunching.
Fantastic. Sudipta, then the next question is, why should the fluorophores always diffuse through the observation volume? From Ajay from JNU.
Why should the fluorophore diffuse through the observation volume?
Always diffuse through the observation.
Okay. So it's, the fluorophores are not actually going always through the observation volume. Your observation volume is fixed in a solution somewhere. There are lots of molecules dancing about. And they don't know where the observation volume is, but they are randomly moving about. So they'll come to this observation volume occasionally. If they're nearby, it'll come, it'll go out. They don't know at all. It's similar to this other cartoon I sometimes use. You'll see here. So it's a dance floor, 100 people dancing. There's a party going on. Huh? And there's a spotlight. Okay, someone. And the people are not caring. They're too busy dancing, so they don't care about the spotlight. They are coming in, going out, dancing around all the floor. But somebody from outside who can only see the people who are in the spotlight will see this number of people fluctuating in that spotlit area. Same thing in the molecular structure.
Chandrabhas, can you ask your question?
Yes. So I was actually intrigued. Because if suppose, let us say that you have a condition where you have stimulated emission, possibility, because you have more number of molecules present in the same volume, and you are having a condition satisfied, is it possible that that will actually not allow you to have correlations?
No, it will have correlation. Actually, stimulated emission can also be derived from the same graph. Your lifetime will go lower. So your ability to see a second photon quickly after the first photon increases because you are driving down the system. The light basically is still a lifetime, but the lifetime is not just the radiation lifetime. It's plus the stimulated emission. So you'll see the thing coming closer and closer. Basically, you are looking at lifetime, and the ability to see another photon soon after increases. Okay. But that's also you'll be able to see from
see it. Okay. Thank you.
Okay. Thank you, Chandrabhas.
Yeah, and there's a question from Shomi Datta, IIT Patna. Sir, will it always happen that only fluorescence molecule will show anti-bunching and phosphor molecules will show bunching?
So, okay. So what am I monitoring here? I'm actually monitoring the fluorescence. So if I monitor phosphorescence, suppose I go to a phosphorescent molecule and in a particular wavelength or something, only phosphorescence is happening, is very similar to the anti-bunching, except it happens at the time scale which is longer. But I'm not monitoring the phosphorescence. So I take that as dark. I'm only monitoring the fluorescence. So the phosphorescent state is dark. Okay. Otherwise, if you look at only the phosphorescence, it will be exactly see the anti-bunching, but at a longer time scale. Because phosphorescence time scale is, and if you look at one molecule, phosphorescence time scale is longer, you'll see it.
So the next question is from Torsha. It was a wonderful talk, sir. When we talk about size of a molecule, does it mean hydrodynamic radius?
Very good point. Yes. When I said size, so this talk was short and glib in a sense. So to say it accurately, thank you for correcting me. When I say size hand-wavingly, it actually means the hydrodynamic radius, because the molecule can have a very irregular shape. So what do I exactly mean by size? No, I mean the hydrodynamic radius. Thank you.
And the other question is from Philip. Philip, can you ask the question? Philip?
Hello, sir. Can you hear me?
Yes, I can hear you, Philip.
Sir, wonderful talk, sir. So I just want to ask you, like, how do we go with the measuring of phosphorescence lifetime from FCS? So, like, our signal will be like around 3 orders of magnitude less than fluorescence for measuring the phosphorescence signal in that case. So
this is related to my answer in the last question. I'm actually not measuring phosphorescence. I'm not even looking at phosphorescence photons, which may be at a different wavelength. I'm looking at fluorescence photons. But I'm looking at, my phosphorescence state is dark. But this width of the dark state, I can get from my correlation curve. So here, if you look at it, here, my cursor is working again, thank you. So this decay is because of the phosphorescence. So the way to think about it is K on, K off. You go to the phosphorescence state, come back. And actually, it is the inverse. This time scale is inverse of K on plus K off. So you can get the time scale of phosphorescence right from here without measuring phosphorescence. We're looking at fluorescence. So phosphorescence is a dark state. So, but still, as I showed here. So if you correlate it, the width of the dark state will be part of the correlation. Okay. So that's how we measure the phosphorescence lifetime without looking at phosphorescence at all.
Okay. Thank you, Philip. Arun Kumar from IIT Jodhpur. Arun, would you like to unmute and ask the question?
Sir, can you hear me?
Yes. Please, could you be louder?
Yeah, so my question is that if a sample is very less equilibrium time, like
say that again,
it will,
please.
so if a
Repeat.
sample is very less equilibrium time, like it will get stabilized after a sort of time, then it's fluorescence lifetime. So how can we measure the FCS? Like correlation, how can we be able to measure?
So the
I
question,
still didn't get the first part.
Yeah, the question is, Sudipta is as far as I understand, if the sample has a very slow equilibration time, how do you then do an FCS measurement if that equilibration time is slower than its fluorescence lifetime?
Yes,
This is what he said.
yes, sir. Right.
Yeah. So depending on which process you are looking at, so ultimately you're looking at equilibrium fluctuations. And if I look at a small volume, the fluctuations have a time scale given by the diffusion time. And if it's long, you'll see that diffusion time becoming long. But if you're talking about some other equilibrium, let's say chemical kinetics equilibrium, and you're looking at particles diffusing and your kinetics is slower compared to the diffusion time, you can't see it in FCS. Because those fluctuations will come to zero and will not respond to things fluctuating above them.
Okay.
Thank you, sir.
Thank you. So now the next question is from Shorodip Paul. Is there any way by which we can differentiate super diffusion to subdiffusion from linear diffusion using FCS?
Yeah. So the super diffusion, etc., sometimes comes because of the particle has energy source. Okay. Or because the substrate could be a solution is funny. It's not homogeneous. And you will have to fit models. So I can talk about it in the afternoon, though it's slightly higher level. You have to fit models to look at super or subdiffusion, there is a very good analysis came out about 15 years ago. People typically use that, and I can refer to it to you to it. You send me a mail, I'll send a reference. I don't remember it off the top of my head, but there are ways to analyze it, which will say that there is a R square goes as T, proportional to T. That's a linear diffusion. Now, R square can go as T to the power alpha, where alpha can be less than 1 or greater than 1. And you can figure it out by looking at FCS at few different volumes. And that analysis technique is is a very, very good technique. You need a little more things. You cannot just have one single volume, but it can be done. Slightly higher level. I'll send you that.
Shauradip, you can email Professor Sudipta Maiti and then get that reference. Okay.
Okay,
Thank
sir.
you,
Thank you,
Sudipta.
sir.
Yeah. Next is the
Let this
question.
be the last question.
Yeah,
Jyotishman.
last question.
Yeah, because 11 o'clock something I also have. I have to go for a meeting.
Yes, this is the last question. Sarita Puri, nice talk. My question is, if the size of the molecule is bigger, let's say oligomers, will fluorescence correlation be dominated by diffusion and affect overall correlation, and how to normalize them in an experimental data?
Again, something I didn't touch upon, and I will touch upon this in the afternoon, which is multiple species. Yes, short answer is, if you have oligomers and monomers, and let's say the oligomers are 10 mers and monomers are monomers, and the 10 mers are 10 times as bright, then yes, your fluorescence correlation curve will be dominated by the oligomers, the brighter particles. In fact, the domination goes, the weightage goes as square of the brightness. So really, if you have very large particles and very fluorescent particles, small particles, then it's tough to see the contribution of the smaller, less bright particles.
Okay. Thank you, Sudipta. This was actually very nice session. You had kept sufficient time for discussing the questions, and thank you for starting off on such a high note. So let's thank Sudipta and move
Thank
to
you, Jyotishman, for arranging this.
Yeah, thank you.
Okay.
We are all doing it together. So anyway, let's move on to the second talk, which is from the ultra fast track. And this will be given by Professor Anindya Datta from IIT Bombay. And Anindya, please come to screen. Yes. And you can share your slides. He will talk about TCS-PC measurements. And as advertised, Anindya was supposed to talk along with Shobhan on nonlinear optic basics, which has been shifted to next day. Anindya will give the more elaborate idea on that. So thank you, Anindya. Yeah.
Thank you, Jyotishman. It's always a pleasure to give this talk when you have done it so many times. While I'm at it, could you and Shobhan please man the entry?
Yes.
Somebody is very mad at me because I removed him and he cannot join back. I told him to join with a different account. But anyway, so good morning, everybody. Today, it is very difficult to talk after Professor Sudipta Maiti because he has made such a great presentation on FCS. What I'll do is I'll talk about a technique that is more classical in a way because it has been around for longer. And it is ubiquitous. TCS-PC is a technique that is now used extensively, not only by experts, but by many others, synthetic chemists, people who work in nanoscience and nanotechnology, many others. And one of the reasons why TCS-PC has become popular is that it's very powerful. It can give you access to a range of timescales, not as long as FCS possibly, but it gives you access to the shorter timescale. And also, it is easy to implement because now the instrument looks like this collection of boxes like what we had. The problem with boxes always is that it becomes a toy, and more often than not, the people using these instruments do not bother to think what is there inside the box. The purpose of our workshop is to unbox all the equipment that we talk about. If you want to go to better timescales, smaller timescales rather, hundreds of femtoseconds to picosecond, then TCS-PC does not really work there, and I'll touch upon it, why that happens. Then you need something called what is commonly called femtosecond fluorescence upconversion or femtosecond optical gating. That is what Shobhan is going to discuss tomorrow. Femtosecond optical gating involves a little bit of nonlinear optical processes as well. That the basics of that sometimes is not so clear to people who use the technique. So that is what will be done by Shobhan tomorrow. Initially, we thought that we'll do both of the things together today, but then we realized that the time would be too short to do justice to both the techniques. So that is why we decided to change the schedule a little bit. This afternoon, we'll go to this lab and we'll show you how exactly the experiment is done. If time permits, we can do a little bit of it even during this present session. Just give me a second. I'll set it to 45 minutes or so that we leave some time for questions. Yeah, here we go. Now, everybody is familiar with Jablonski diagram in this audience, I suppose. So if we have any molecule or nanomaterial or whatever, we excite it, the molecule or whatever it is promoted to the excited state, and then it cannot remain there forever. It has to relax, it has to come down to the ground state. And while doing that, it can do so by two pathways. One is radiative, which means light is emitted, and the other is non-radiative. That means the excess energy is just dissipated in the medium in some way or the other. The rate constant associated with the radiative process is commonly called Kr, and that with the non-radiative process is commonly called Knr. Now, what happens if I excite not with light that is always on, continuous wave light, but with a pulse? When I say pulse, I mean light that is on for a very short amount of time and then it goes off. Something like this. Remember, x-axis here is time. What I'm showing you here is a short burst of light that is used to promote the molecule from the ground state to the excited state. So, effectively, this molecule builds up an excited state population. This is not a single molecule experiment or even a few molecule experiment, unlike FCS. Here we're working with bulk. And when we say bulk, we really mean millions, lakhs and crores of molecules. And just to realize how many molecules we're talking about, one needs to think what Avogadro number is 6.023, 10 to the power 23. Even if we work with micromolar concentration, 10 to the power 23 just becomes 10 to the power 23 minus 6. That's still a very, very large number. So we work in the ensemble level most of the time using TCSPs. So the action of the pulse of light that comes in is to create an excited state population. And as I said, the population cannot persist forever. It has to decay. And in the simplest case scenario, it decays in as a first order process, very much like radioactive nuclei. These excited states are there to decay by themselves. So they decay following a first order equation. And we know that the integrated first order rate law is something like this. And a semi-log plot of the population of the excited state with time is going to be linear. Since fluorescence intensity is proportional to the excited state population at that instant, the plot of fluorescence intensity against time is also going to be linear if we make a semi-log plot. The only difference between what we are saying now and what we usually say for chemical kinetics is that instead of writing it rate constant, we have used this time constant, 1 by rate constant. And this is called a lifetime. The reason why it is called lifetime is that this is really the average time spent by a molecule in its excited state. That part of the mathematics is not very difficult. It involves solving a standard integral, which is available in compendia. So one can do it very easily. So that is the reason why it is called lifetime. And it's important to remember that lifetime is an average quantity, average time spent by a molecule in the excited state. So if the initial population of the excited state is something like 10 crore molecules in the observation volume, it does not mean that, and let us say the lifetime is 5 nanoseconds, it does not mean that all 10 crore molecules come down to the ground state in 5 nanoseconds. What it means is that if you take an average of the time spent in the excited state, then that average is going to be 5 nanoseconds. And an easy rule of thumb, if we have an exponential decay, to estimate lifetime is this: put t equal to tau. If you put t equal to tau, what do we get? E to the power minus 1 by e, right? So p at time t equal to tau is going to be p at time 0, which is population or intensity at 0 time, divided by e. E is approximately 3. It's not 3, less than 3, approximately 3. So for a single exponential decay of fluorescence or population, one can make a quick and dirty estimate of the lifetime by looking at how much time it takes for the intensity to decay to about 1/3 of its initial value. And that is how lifetimes were determined long, long ago in 1950s, 60s, for simple systems, long lifetimes, where when TCSPC was not available. But then it is not necessary that tau is going to be long. It can be short. And also, it's not necessary that the decay of the excited state population is going to be a plain and simple exponential. More often than not, even the semi-log plot of time-dependent population or time-dependent fluorescence intensity is not linear with time. And that is where the complication arises. That is why we need a technique that is more sophisticated than just trying to find out what is the intensity, how much time it takes for the intensity to decay to 1/3 of its initial value. So now, when the decay is, when the semi-log plot is not linear, then the most popular, most used, and most abused model that is that you see in literature is a linear sum of exponential terms. The reason why it is most used is that the expectation is that there are multiple kinds of populations that decay in different ways. Multiple pathways are available. That is why it is so popular. And there's no denying the fact that this is the case many times. But one needs to be careful. It is not necessary that a linear sum of exponential functions is the right model. And later on, I'm going to show a couple of examples of that. The problem is, if you use a sufficient number of parameters, in this equation, how many parameters do we have? Lifetimes, let us say it is a tri-exponential decay, as it's called, sum of 3 exponential functions. Then tau 1, tau 2, tau 3, these 3 lifetimes are 3 parameters. The amplitudes are 2 parameters. I'm saying 2 parameters because generally the amplitudes are normalized, so the sum is equal to 1. So the problem is that you have this kind of a shape and you want to fit it to a function involving 5, 6 parameters. It is going to fit if you use a large number of parameters, even though it may not be the right model. Those of you who have studied quantum mechanics or quantum chemistry would know that since we cannot solve Schrodinger equation for many electron systems, what we try to do is we try to somehow get to the right shape of the wave function that gets the minimum of energy by using a sum, as large a sum as possible of Gaussian functions and other functions that will be there. So this is just a way to get the right shape. In our case, in case of quantum chemistry, it's okay, because all you care about is the energy and finally what the shape is. The contributing functions don't matter. In our case, the contribution functions usually matter. So we should not blindly fit whatever we see to as many, to a sum of as many exponential functions that we have. And that is one of the major takeaway lessons from today's discussion, I hope. But we'll take a rain check on that and proceed with how the experiment is done. Now, I have already jumped the gun on this. The thing is, since the fluorescence intensity at a given time is proportional to the population at that time, you can just replace all the P's by I's, where I stand for fluorescence intensities. If we are talking about a single exponential decay, then the lifetime is the reciprocal of the sum of the radiative rate constant and all the non-radiative rate constants that are there. If you read Lakovich's book, for example, KNR is written as something different. In fact, even KR is written as gamma. But it's important to understand that all KNRs contribute to lifetime. Sometimes there's a confusion because people think that we are looking at fluorescence. How is it that we can talk about non-radiative rate constant here? We can talk about that because the fluorescence intensity that we see is really a marker of the excited state population. And this excited state population can be depleted by radiative as well as non-radiative pathways. So both of them contribute to different extents to the decay that we see, and we extract the lifetime from. So that is the second or maybe zeroth very important lesson. The lifetime that we have is reciprocal of not only the radiative rate constant, but the sum of radiative and all non-radiative rate constants. Very important to not forget that. The quantum yield, on the other hand, and here I have written PL because 50% of our effort is in semiconductor nanocrystals, where we don't talk about fluorescence, we talk about photoluminescence, but you might as well talk about fluorescence for now. The fluorescence quantum yield or photoluminescence quantum yield is the ratio of the radiative rate constant and the radiative plus non-radiative rate constant. This can be derived very simply, but even without derivation, one can think like this, that 1 by KR plus KNR is a lifetime, right? So KR plus KNR is the total rate constant that contributes to the decay of the excited state population. KR is the rate constant for the radiative part of it. So ratio of KR by KR and KR plus KNR essentially tells you what fraction of the excited state is depopulated to the radiative channel. And that is the fraction that is responsible for fluorescence. And that's why it is the fluorescence quantum yield. KR is representative of the molecules that give out light. KR plus KNR represent all the molecules in the excited state that come down to the ground state. That's why this equation arises. Of course, 1 by KR plus KNR is simply tau. So we might as well write quantum yield equal to KR multiplied by tau. And that is the most fundamental relationship between quantum yield and lifetime. Another important lesson, because sometimes this is somehow missed. I mean, I've had reviewer comments which said, why are you talking about lifetime while discussing fluorescence intensity? What is the relationship between fluorescence intensity and lifetime? Well, this is a relationship. Fluorescence quantum yield is a radiative rate constant multiplied by lifetime. So longer the lifetime, more is the chance of the molecule to emit photons. You can think like that. Of course, KNR does have an important role to play here. So what we see is that if we can measure the fluorescence quantum yield and the fluorescence lifetime, then very conveniently we can work out the radiative as well as non-radiative rate constant. And that is one of the most fundamental tenets that define why this technique is so powerful. By two simple experiments, you can have access to rate constants for very fast processes. Processes that get over in hundreds of picosecond to nanosecond. Why we cannot go below hundreds of picosecond? We'll come to that in a moment. At the same time, it is important to remember that all this discussion holds for exponential decays. The problem is, if the decay is not exponential, then it is very common to calculate something called average lifetime. Average lifetime is usually defined in two ways. One is sum over I, AI tau I divided by sum over I, AI. And as I said, sum over I, AI is usually set to 1. So it's simply sum over I, AI tau I. The other one is sum over I, AI tau I square divided by sum over I, AI tau I. I'm not saying these are useless. They do have their utilities in certain things, one of which we are going to discuss. But it's also important to understand that for most of the cases, if you just work out the average lifetime, you're getting an idea about the fluorescence intensity. You might as well not do the time resolved experiment. Just do steady state and be happy about it. If we can make sense of the components, then we truly utilize the power of time resolved experiments. It is not always possible to do that. The classical case being that of tryptophan. It's very well known that tryptophan has tryptophan decays are described by a sum of 3 exponential functions, and it's impossible to make sense of the individual functions because tryptophan fluorescence decay essentially comes from a bunch of different conformers that are there. You cannot really tell that this component because of this component is because of that. However, for most of the cases, you can and you should try to do it. Our first resort should not be average lifetime. Unfortunately, that is what it is in maybe 85% of fluorescence papers that come out. Whenever it is anything other than exponential, people happily work out the average lifetime and then they build a story upon that, which doesn't make much sense. Also, one cannot really work out these radiative rate constants and all with average lifetime. They hold only when the decay is exponential. If you can work with components and if you can extract their individual fluorescence intensities and all, then you can try to work out the non-radiative processes associated with every constant, every lifetime. It is doable. If one can do that, then that's a good experiment. But if you take an average lifetime and find out some rate constant based on that, it is usually wrong. Unfortunately, literature is replete with such reports. And our hope is that all these 122 people who are there, maybe 50, 60 of them are new to this field. Hopefully, they would go back from here with this understanding and they would be sensitized to the fact that we cannot just do things because they're convenient or because somebody else has done it. It is what is published is not necessarily gospel truth. One needs to think analytically, go back to basics, and do what is right. It has been published by so and so is not a good excuse for doing a wrong experiment or wrong data analysis. All right, we'll go back to the photograph of the instrument. I was actually planning to show you how a decay is recorded, but perhaps I don't have time now. So Orko will do it in the afternoon. Here, what we have is we have two excitation sources. This one is a femtosecond titanium sapphire laser, which is tunable from about 700 nanometer to about 1050 nanometer. Of course, you understand that those wavelengths are not usually very useful for as excitation wavelengths for fluorescence, unless you do a 2-photon excitation. So what we do is the fundamental coming out of here and the repetition rate here is also very high, 80 megahertz. That goes into this box, which contains two kinds of optics. One is nonlinear crystals, which Shobhan is going to talk about, which generates second or third harmonic of the fundamental light. So if you put in 800 nanometer light here, you generate 400 nanometer. How? Because we have these crystals which have the property that they can make two photons of the same energy coalesce. It's like on a surface, if you put a drop of water and put another one, they join up to make a bigger drop. It's exactly like that. Or if you have 3 drops, they join up to form an even bigger drop. That is like your third harmonic equation. So we have access to a large range of wavelengths thanks to the nonlinear crystals that are there. Of course, they're not the only pieces of optics there. You have to separate the wavelengths, so you have things like dichroic mirrors. And one more piece of optic is there. We should open and show them also in the afternoon, where what you do is you cut down the repetition rate. 80 megahertz, the problem with 80 megahertz repetition rate is that the separation in time between two pulses is only 12.5 nanoseconds. If your lifetime is long, then the decay doesn't even get over. So most of the time, you have to cut down the repetition rate to something that is more usable. That is what is done using something called a pulse speaker. We'll not go into how exactly a pulse speaker works. If there are questions, we can take it in the lab session. So the excitation light is reflected by these two mirrors. So this one is for the second harmonic, this one the third harmonic. They're guided into this cube, which is called, rather predictably, fluorocube. Inside this, the sample is kept and it's excited by this light. Alternatively, sometimes we also use this small little thing here. It's a diode laser. And we have an arsenal of diode lasers of many different wavelengths. If the lifetime is long, then we like to use the diode lasers whose pulse width is a little larger, 100 picosecond, 150 picosecond. The good thing is that they are more gentle on the samples. Femtosecond pulses can sometimes burn your sample. You have to be careful. So depending on what we are looking at, we use these diode lasers as well. And then the emission is collected at right angle, goes through a monochromator, which contains a grating and slits. You choose the wavelength that you want to look at, and that wavelength is detected by this, what is called the hybrid photomultiplier tube. And the output of this hybrid photomultiplier tube goes into the electronics here. If you look carefully, you see that another cable goes out from the pulse speaker into the electronics as well. What is the function of these two? We will discuss that either now or in the afternoon. But I'd like to draw your attention to the other side as well. We have actually now made use of all four sides that we have in the cube. In the other side, we have another monochromator and another detector, which is in a bigger box. This is the NIR detector. So now we can actually look at any wavelength in ultraviolet to NIR region. And let me take a minute out here and say that this instrument and all central facility instruments in IIT Bombay are available for use for anybody in India for a sometimes unreasonably modest charge. And to record a fluorescence decay on our instrument, you have to pay 100 rupees, which is not much. So in any case, in case anybody wants to use our equipment, you are more than welcome. I can tell you how to access the web page. You can just type. All right. This is what is there inside the boxes. We said that we are going to unbox the instrument. Let's try to do that here. This is the laser. I'm sorry, I'm stealing the thunder of my student Gaurav. His PhD defense is day after tomorrow, and he has made this animation very painstakingly. But it's so nice that a little unfair manner, I've taken the advantage, I've grabbed the advantage of being a supervisor and taken this animation and showing it to you people even before you could. So this is the output of the laser. It goes into the second harmonic or third harmonic generator, as I saw, and the pulse speaker. The light comes here, reflected by two mirrors, goes into the sun. And this thing here, this is the fluorescence light that comes out, goes through the monochromator. It goes to an emission polarizer as well. We have to make the measurement at a particular magic angle polarization. We'll elaborate upon that in the lab session. And then goes into the photomultiplier tube. And then from the photomultiplier tube, it goes into the electronics. TFD means constant fraction discriminator. There's another arm. When the light goes out of here, an electrical signal, a synchronous electrical signal is sent out by the electronics associated with the pulse speaker. And that also goes into another, what is called constant fraction discriminator. What happens afterwards, we'll see. But this is essentially what happens. So as you see, two signals are going out at the same time or at a fixed delay with each other. On this side, you have light coming out. On this side, you have the electrical signal. Both of them are delayed by using mirrors or by making the electrical signals go through a lot longer cable or something. And both find their ways to what are called start and stop ports of something called time to amplitude converter. Right? So essentially, what happens in time to amplitude converter is that the start signal starts the charging of a capacitor inside the time to amplitude converter. The stop signal stops the charging, and then the capacitor is discharged again across a particular resistor, and the voltage that is generated is measured. Now, as you understand, if the difference in times of arrival of the start and stop signals is large, then the capacitor is going to charge for a longer time, and upon discharge, the voltage is also going to be higher. So, a longer time difference between start and stop amounts to a larger voltage being generated. A shorter difference in arrival times results in a smaller voltage being generated when the capacitor is discharged. So just by looking at those voltages, we have a means of measuring the difference between the arrival of start and stop signals, or between a laser pulse and the corresponding fluorescence photon. So typically, this is what we are looking. Okay? We make many measurements, and in every measurement, we get some difference in time. Okay? And that is what is recorded in something called a multi-channel analyzer. So the way multi-channel analyzer is like a digital graph paper. So what you do when you want to use it is this. Let us say I have a graph paper and I want to plot some occurrence. This is what I'll do. Let us say these are my times. Is it visible? I cannot see. Can you see the paper? If this is the difference in arrival of time, I put 1 mark here. If this is the difference, I put 1 mark here. Again, if another event happens with this time, I increase by another mark. This way, what I do is
Anindya, we can't see anything what you're writing.
Okay, I will do it the hard way.
Yeah.
What I'm saying is this.
You can choose that option of line.
Yeah, I have. Hold on a second. To see where I can go.
It should come.
Let it be. I think we'll try to do it in the next session. Unfortunately, I'm also doing it from my home, so I don't have my pad on me. Okay. So what happens is this. Actually, you can see it here nicely. Let us have performed many measurements. And then the difference in arrival times is this for 1, 2, 3, 4, 5, 6, 7, 8 times. So here the number of counts is going to be 8. Corresponding to this arrival time, let us say there have been 3 occurrences. Of course, the number of occurrences is not 3 and 8 that we usually measure. We talk in hundreds and thousands. So then I plot 3 here. So what I do then essentially is that I build a histogram. A histogram of arrival times, a difference in arrival times of start and stop. And then the essence of TCSPC is that this histogram truly reflects the fluorescence decay. And it does, provided you do it in a careful manner. It is very important to get a precise timing information in all this experiment. And that is done by something called a constant fraction discrimination. I'll not talk about that right now because I have only about 16 minutes left. And we'd like to have some questions. By the way, whatever question you may have, you can start writing them in the chat box if you're not doing that already.
They're doing it.
Okay. So next, I want to talk a little bit about time resolution. You want to measure a lifetime. That lifetime can be 200 picosecond. It can be 200 nanosecond also. So what that means is that you should be able to do the experiment at different full scales so that your decay is complete, and also at sufficient resolution. And when I say sufficient resolution, I should perhaps say sufficient and necessary resolution as well. you can play around with both of these. The problem that I have observed in most of the cases is that students often like to record decays at the best possible resolution, which is in our case, I think 7 picosecond per channel. You can make it 3.5 picosecond per channel with a little bit of trick, but let's say 7 picosecond per channel. Now see, if your lifetime is something like 700 picosecond, as I said, and right now to make things simple, let's talk about only exponential decays, single lifetime. Let us say it is 700 picosecond. I've said that in one lifetime, the intensity decreases to 1/3 of its original value. So within 4 lifetimes, what will happen? The intensity will decay to 1/3⁴ of its original value. 9 9s are 81, 1/81. So approximately 100. That is typically what you want to record in order to get a believable estimate of the lifetime. So if 700 picosecond is a lifetime, then your full scale should be something like 2.8 nanosecond. Yeah. So, and you should have at least say 200 points there. So 2800 picosecond, 2.8 nanosecond, that is a full scale. If you want, what did I say, 200? 200 may not be good. Let's say we want 500 points there. So 2800 by 500, how much is that? 28 by 5, 38 by 5, 6. So that is when you actually need 6-7 picosecond per channel. However, if the lifetime is something like 10 nanosecond, 10,000 picosecond, then your full scale has to be 10,000 multiplied by 4, 40,000 picosecond, 40 nanosecond. So just imagine how many points would be there if you record a decay over 40 nanosecond with 7 picosecond resolution. Makes no sense. Because unnecessarily your time of experiment goes up. You lose time. And if you do the experiment for longer than what is required, there are chances that your sample may degrade or something else might happen. So it is very important to do a quick and dirty experiment at the beginning, get a reasonable estimate of what kind of lifetime is there, and then do the final experiment with the correct resolution and the correct full scale also. Once again, should not do these experiments with your without thinking and just by going by whatever the default parameter is. How to calculate resolution? Resolution is now calculated automatically, which is unfortunate, but you should do it by yourself. The way you can do is this. Suppose there's a TAC range and MC again is the number of channels. You just divide one by the other. If you want to do it manually, what you do is you record the instrument response function, and we can actually delay the instrument response function. Let us say for a value of 92 nanosecond delay, the instrument response function comes at 520, the channel number 525. And let's say we change the delay to 100 nanosecond. Now the instrument function will move to 600th channel. So your resolution is going to be 100 minus 92, 8 nanosecond or 8,000 picosecond divided by 600 minus 525, that is 75 channels. So this is what it is. Okay. Okay. That is one thing. The other point that I'd like to draw your attention to in the last 10-12 minutes or so is, so far, we have talked about delta pulse excitation, which means that we have assumed that the pulse that we are exciting with has a pulse width of 0. Of course, pulse width of 0 is never possible. It can be small, but it cannot be 0. The assumption is that it is sufficiently small so that it does not mess up your fluorescence decay. On the other hand, we are talking about 700 picosecond decays, where the instrument response function is something like, if you use a diode laser, 250, 300 picosecond. Even if it is 40 picosecond with the other laser and detector, 40 picosecond is not negligible compared to 700 picosecond, right? So what happens there is, you can no longer assume that your excitation pulse is a delta pulse, and you have to account for what is called convolution. What is convolution? This is the convolution integral where the actual decay is given by an integral like this. F, the decay function for t minus t dash, multiplied by p at t dash, where t dash is a particular time impulse function at time t dash, integrated from 0 to infinity of t dash. Looks scary? I'm sure, I hope it does look scary to some. So let us see if we can deconstruct it a little bit. This is what I'm talking about. Let us say this is your excitation path of finite width. If you take any point, this point one can consider as a delta pulse, and corresponding to this delta pulse, there's going to be a fluorescence decay. Corresponding to another point, there's going to be another decay, right? And the difference between this and this is that since I've taken a time that is closer to the time at which the maximum occurs, the zero time intensity of this decay is more correspondingly. Similarly, for all the points under this instrument response function envelope, we are going to get a decay each. All right. How many decays do we have then? In principle, infinite. In reality, it is defined by the resolution. So from here to here, if it is say 200 picosecond, and if you're working at say 5 picosecond per channel resolution, then you're going to have 200 divided by 5 number of decays that come out. But then if you look at any particular time t, and to understand it, we'll go back to one decay arising out of the impulse function or delta function at a particular time t dash. The intensity for fluorescence intensity at this time t is given by this decay, right? When you look at one single decay, the time of decay is actually t minus t dash. Because now this is zero time for this decay. What will we get? If the height of the impulse is t at t dash, then the decay that we get is going to be whatever is the decay model. We can say exponential, then it's going to be e to the power minus t dash divided by tau, let's say exponential function, multiplied by whatever the height is, p at t dash. All right. This is correct for a single impulse function or delta function at time t dash, and measurement time is t. So now let's go back to the more weird picture like this. This is what you had, right? Now you understand that at this time t, the fluorescence intensity comes not from one decay, but from all the decays that are there, starting with all the different delta functions that are there under the instrument response function envelope. How do you get this fluorescence intensity? Just by adding up the intensities of all the decays. That is what is denoted by this integral. And I hope that now the integral does not look scary anymore. As you know, a large summation is given by an integral. Here the delta pulses are sufficiently close to each other so that we can replace the summation by an integral. That's all that is there. Okay. The problem is, how do you know? How do you deconvolute? One way of deconvoluting would be to actually work it out, which is difficult. So most of the time we take the easy way out, in which we assume some kind of a fitting function, a decay, and we convolute it, which means we assume that this is e to the power minus t minus t dash by tau. We assume that tau is say 5 nanoseconds. We put that value and work out all these decays. When I say we, I mean the computer. Fortunately, we don't have to do it by hand. All these decays are worked out and the summation is done. And thus you get an intensity corresponding to every time t. Right? For every time t that is there. If there are 500 points, then for all the 500 points that are there, you work out the convoluted decay like this. But then who has said that 5 nanosecond is correct? It may not be correct, right? It's only a guess. So what the computer does is that it compares this decay with the actual experimentally recorded decay. It compares this fitting function with the actual recorded decay and sees whether there's a good match. And as you know, computer doesn't have eyes or ears. So the only thing that it can handle is numbers. And to see whether there's a good match or not, it relies upon things called goodness of fit, parameters of goodness of fit. And the one that is most popular, most common is reduced chi-square. Many of us might know that reduced chi-square is supposed to be close to 1, right? The reason why that happens is that chi-square is defined as the summation. This is not really 1 by n. It is 1 by n minus p, where p is the number of floating parameters. But if you just look in the summation, look at each term. On the in the numerator, we have the variance, the difference between the experimentally obtained data at intensity at point number I and the fitting data after convolution at point number Y. This is the difference. So how different the actual data point is from the point you have generated by fitting. In the denominator, you have sigma of I, which for photon counting is known to be associated with Poissonian decay. So sigma at I is root over yi. Y, remember, is the count. And about this, I want to make another point later on. So the noise, experimental noise that you invariably have for photon counting is square root of the number of counts that you have got. So if you divide, then in the numerator, you have the error that you get experimentally. In the denominator, you have the theoretically defined error. For a good fit, the ratio should be 1, right? And then you sum it over n number of points, you should get n. And then again, you're dividing by 1 by n minus p, where p is much smaller compared to n. You should get approximately 1. That's why reduced chi-square should be equal to 1. A couple of points here. First of all, it should be close to 1, but never less than 1. Even in Lakovich's book, it says that a range of 0.9 to 1 point something is acceptable. Actually, it is not. Because as you see, the numerator has the experimental error. The denominator has the theoretical limit. If you have a reduced chi-square that is smaller than 1, then what you're claiming is that you have done better than the best. It's unphysical. It should be as close to 1 as possible on the higher side. Point number 2, digressing a little bit, it is very important to understand that the noise associated with photon counting is root over n. So suppose I do an experiment and Orko is going to show us how the decays look different if we record them to different maximum values. Suppose I'm lazy and I record a decay of up to maximum value of 500 counts in the peak. But then nobody will be happy if I say it's 500. So I simply multiply it by a factor and make it 1000. An expert would actually be able to tell, because it will look very noisy. If you record to actual 10,000 count, then the noise is much less. Because signal to noise ratio is 1 by root over n. The noise is root over n, signal is n. The signal to noise, right? That is going to be 1 by root over n. So the thing is, you should never normalize fluorescence decays. You record whatever counts that you have to record to. If you want to show decays one on top of the other, please do the experiment where you record to the same number of counts at the peak. If you normalize, an expert can tell, and that may not land you in a very high situation. More important than reduced chi-square is actually weighted residuals. That has become less popular of late because there's so much of data. Here, what you do is you plot this, what is there inside the summation, for every value of I. The good thing about residuals is that it can tell you where it is deviating, if it's deviating at all. And then you can change your guess functions accordingly. I have 1.5 minutes left, but maybe I'll take 1 minute extra. The reason why I flagged that point about you do this fitting, you get a good chi-square and all that. It does not necessarily mean that it is correct. Because if it is not exponential, then, as I said, an error in one parameter can actually be compensated for by an error in the other. And here, this is an example from as long back as 1974. What they did was, this is the normal regular plot, this is the semi-log plot. They plotted a function, sum of two exponentials. First one is 7,500 multiplied by e to the power minus t by 5.5 plus 2,500 e to the power minus t by 8. Essentially, two lifetimes, 5.5 nanosecond and 8 nanosecond. The amplitudes are something like 0.75 and 0.25, and they plot the function. The other function is, instead of 5.5, the lifetime is 4.5. Instead of the second lifetime being 8 nanosecond, it is 6.7 nanosecond. The amplitudes are reversed. In this case, the shorter lifetime has an amplitude of, say, 0.25, and the longer lifetime has an amplitude of 0.7. You see, it is impossible to tell between the two decays in the linear scale. In the log scale, if you go to very long times, you can tell the difference. The problem is that at that time, in the log scale, the noise also appears to be more, and so you really cannot tell whether you have two lifetimes of 5.5 nanosecond and 8 nanosecond, or 4.5 nanosecond and 6.7 nanosecond with amplitudes reversed. Which one is correct? You don't know. And that is why it is better always, first of all, to have a model in hand. You should think what you expect. Secondly, it's always better to do what is called global analysis. I'll come to that. Before that, very quickly, just exponential or some exponentials are not the only available decay models. For heterogeneous systems, stretched exponential function is very popular, where you take this exponential function, raise it to an exponent. So beta is equal to 1, then you have an exponential decay. And this is very popular in FCS as well. If beta deviates from 1, then you are deviating from the exponential behavior. The other way of doing it, one of our founders of Fluorescence Society was very much into this, Professor G. Krishnamurthy, is distribution of lifetimes, where you try to not think that you have definite lifetimes of, say, 1, 3, and 5 nanosecond, but rather you think that you have 5 nanosecond plus minus something, 3 nanosecond plus minus something. And what you do is you essentially fit the decay with a large number of fixed lifetimes. And the reason why it is plotted in log scale, the x-axis, is that it gives you access to many decades of time. And on y-axis, you have amplitude. So here the lifetimes are fixed, amplitudes are varied. So wherever amplitude is 0, that means that lifetime is not there. And wherever you get some kind of a distribution, that is the distribution of the lifetime. So this is a very powerful decay model. People working in heterogeneous environments should actually use this. And there are other decay models as well, and they have been known for a long, long time, since 1975. I will not go into, no, I have to talk about global analysis, I think.
So it's at 10 minutes are remaining. So maybe you can take questions and then.
Yeah, I'll just, I'm done. Let me just talk about this, because otherwise I'll end up not doing it. Sometimes what happens is you have a system in which you have two species, let us say 3 nanoseconds, 7 nanosecond. They have the typical spectra. So if you record your decays across the spectrum, on the blue side, they'll be dominated by 3 nanosecond. On the red side, they'll be dominated by 7 nanosecond. So you can fit the entire range by a sum of exponential functions, where the lifetimes would be the global parameters and the amplitudes would be the local parameters. Global analysis is an non-trivial exercise. The modules are available commercially now. They should be available in your data analysis software. Otherwise, they are freely downloadable. The error that sometimes we encounter is that people just fix the lifetimes. That is wrong. Fixing parameters is not global analysis. Fixing parameters, in all probabilities, would give you results that are wrong. So if you want to do global analysis, please do it the right way. Don't just say that we'll fix 3 nanoseconds and 7 nanoseconds, because how do you know that those are the values? All right. So I will skip the time-resolved emission spectra. We can demonstrate a little bit in the hands-on sessions. So to conclude, this is a very useful technique, widely available now. The experiment, while doing the experiment, we should record sufficient number of counts and not normalize. To do the experiment at the right time resolution. Data analysis is non-trivial and very important. And we'll do a quiz, Jyotishman, to end. What is the most important component of TCSPC that we have discussed? I'll request the audience to type in the chat box and I'll give you half a minute to do it. We have talked about the laser, electronics, detector, optical components. Nobody's writing. Which component is most important in TCSPC? That's the concluding question. Please write in the chat box. Nobody's writing.
Can you
We will
please
not take
put in the
questions if they
chat
don't write.
box? Please put in the chat box.
Somebody has written something. One. And there are 136 people there.
No, somebody is writing user and the electronic part,
Electronic, non-linear
Good
crystal.
one.
and then non-linear
Anything more?
crystal, laser source.
Source. Very good, Jyoti. Next.
User is the best answer.
No. See,
You're right.
I think we can clearly understand that most of the participants are probably new here.
CFD, okay. All right, I'll give you the answer because
user is also
yeah, since Jyotishman is breathing down my neck, I'm going to give you the answer. This is the most important.
Yes, user.
A particular part of the body of the user.
Of the user.
So my concluding message would be is not only for TCSPC, please do not do any experiment with your brain switched off. This is a quotation. This is something that I heard from my PhD supervisor, Professor Kankan Bhattacharya. Let's end on this note and take questions.
Thank you. Thank you, Anindya, for a very nice and detailed and elaborate conceptual ideas as well as technical ideas associated with TCSPC. And of course, there will be more questions, but there are few of the questions already from the listeners here in the audience. So I will just take quickly because not all of them can be done now, but we will have parallel breakout sessions. So Anindya and Shobhan, please take care of that. So the first question that came immediately after a few minutes was Professor Datta said that the decay of the excited state is first order. I know it is first order, but I don't appreciate why we assume it should be first order.
You shouldn't. You're right.
How was the conclusion arrived?
Where
There's Anand Dev.
Yeah, I don't see it anymore. Or maybe why is it first order? Jyotishman, Anand. Yes, Anand. Very, very good question. First of all, what I said was in the simplest case scenario, you can expect it to be first order because if you think the molecules in excited state are there by themselves, right? They don't have help from anybody. And they have to come back to the ground state. So the situation is very much like, say, the radioactive decay, right? So that is why it is first order. It depends on the concentration and nothing else, concentration of the excited state. But there's a statutory message. So, but then the point is, if it is first order, then your semilog plot should be linear. In the lab session, we'll show you some decays like that. Or very senior student, Orko, who's going to do the demo, has very good luck with first order decays. Whatever he works with, have a single lifetime. So we'll show you those, but we'll also show you decays that are definitely not first order. Then there's a question from Kush.
Yes.
Sir, from slide 1, if a fluorophore lifetime exhibits multi-component, can we use the same equation? Actually, we can't. We can, if you extract the fluorescence quantum means of each component, lifetimes of each component, and work with the components, then you can. Otherwise, by using average lifetime, you cannot. You cannot really relate a quantum field with multi-component systems so easily. You can do it qualitatively, saying that it's becoming slower, so quantum field is going to be larger, and so on and so forth. But there is no straightforward linear relationship. Okay, Shubhasri from CCMB is saying always wonder how the reverse mode start and stop signal work to calculate lifetime, please come to the lab session. We are going to show you reverse mode as well as the forward. How the time delay is decided, Ikshita, once again, please come to the lab session. You decide the time delay in such a way that you get your instrument response function in a reasonable position on your screen. Sumit is saying if you excite the same sample at different wavelength, provide the same emission wavelength, you are getting the same. Only intensity changes the emission wavelength on different wavelength excitation. Does lifetime change? Yes and no. Lifetime should not change for most of the systems. But if you work with, say, a semiconductor nanocrystal, and then what we have seen is, and it's widely reported, when you excite at smaller wavelength, higher energies, then you can surmount barriers or you can have access to trap states and all that you don't have access to if you do only bandage excitation. And that is when the lifetime can be excitation wavelength dependent. Pramod Kumar is asking, can we correlate or initial guess of the fluorescence lifetime by looking at the steady state fluorescence spectra? If you are looking at steady state fluorescence spectra, it's difficult. If you're very experienced, maybe you can come up with something, but you have the decay at your hand. Looking at the decay itself, you'll be able to make some kind of a guess. All right, and then come the answers. If there is any more question, then I'll be happy to answer.
Okay. Thank you, Anindya, and thank you for this very nice session on ultra-fast track, which is on TCSPC measurements. So this is the first set of talks on time-resolved spectroscopy. So now we move to the third track, which is the Raman track. And we have an eminent expert, Professor Chandrabhas Narayan, who is joining us from the Rajiv Gandhi Center for Biotechnology. He's the director of the institute and a very well-known practicing Raman spectroscopist. He is going to give you the conceptual basics of Raman spectroscopy, which will enable you to go through this track without any problem. So, Chandrabhas,
Yes,
you're
are you able to hear me?
Yes. Yes.
Host has disabled participants share screen
Oh,
sharing.
wait. There's some issue. I'm sorry.
I knew
Chandrabhas.
this. I knew this.
I knew this. No, Chandrabhas. Now you're all fine. Yeah. Sorry about that.
Yeah. Now I can share. I think. Yeah. Enter screen. Share.
Okay. So now
You are able to see the
yes.
Are you able to see the screen?
Yes, we are. Full screen.
Okay. Yes. And I hope you are not seeing both my displays. I hope so.
No. A single display with
you are
basics of Raman
not. You are not seeing my next slide, right?
No.
Okay. Because on I have two displays here, so I'm able to see the second one. Yeah.
So you have 45 minutes, Bhas, and then we can take some questions. If it is 15 minutes, it's good. If 10 minutes, it's also okay. But yeah.
Sure. I'll try to exactly finish by 45 minutes. No problem.
Thank you.
I'll do that. Yeah. Thanks, JD. And of course, going after Sudipta and Anindya, great teachers, it is going to be quite a task for me to lift it up to that level. But I know that JD is going to be also helping me later. So he's going to make it much more simpler when you actually listen to him. So here, I'm actually going to talk to you about the basics of Raman's, and I'll just motivate you how we are looking at it, because you have already looked at some of the light matter interactions. So what we are already knowing is that most of the times the light and the matter, when they interact, the things which happen is that you will have transmission, then you will also have reflection, then absorption. And this is what was the previous two talks. There were absorption, and then you had luminescence, which actually can be a fluorescence, it can be phosphorescence, various other time scales it can have. So these are the major things which would happen with the material. And after that, it also has, very interestingly, another phenomena, which is called the scattering, which all of you know. And most of the times the scattering is of the same wavelength, which actually was incident. It comes out and it is called elastic scattering. Just like what we talk about elastic and inelastic collisions, this is also elastic scattering is basically where the energy remains constant after the interaction, and hence the color remains the same. But what Raman actually discovered was, and this is also called as Rayleigh scattering in many of the cases where you have a smooth surface which is actually interacting with the system. Now, when you also have this, there are blue shifted and red shifted lights which come out of the material. And this is what Raman actually got. Somebody wants to get admitted to the room. You can do it, Jyotish. So basically, you have red shifted and blue shifted light. And when I say red shifted and blue shifted, here I have shown it as blue and red. It doesn't mean blue and red always. It means green gets shifted towards little bit towards the red, and green can be shifted towards the blue. And this is what gave the Nobel Prize for Raman itself. So whenever you have such a thing, you can actually demonstrate it in lab itself. You can take any transparent liquid, and you know that transparent liquids actually pass the light through them. And you can see here that I have a laser, which is a monochromatic light, which is blue light. And this is the scattering from the dust particle in the room when you keep it dark. And when it passes through the transparent material, it actually gives out light in the, though the laser is directional, but you have light coming 90 degrees to it. And because my camera is at 90 degrees, and I'm able to see a white light coming out. Actually, it is not white. It is intense saturation of your detector because there is so much of elastic scattering coming from the molecules inside this liquid. And if you look at it at the bottom, it is actually nothing but cyclohexane. So Raman actually could discover this only because there is a lot of interesting organic molecules he was actually looking at, and they give you very strong scattering. Now, if I want to see the red shifted or blue shifted light, yeah, I just have to block this blue light. And today we have very good filters available. So if I actually filter out that blue light, and you can see that blue light scattering coming from the dust particle is disappeared. And now I see different colors coming out of this liquid. And this is actually what is the Raman scattering, which is coming. You are seeing in this case mostly yellowish, greenish color. And that is also intense, and you can do it. So whenever you have such light and you want to know what are the different components of light, you can actually do the following, that you can disperse the light. And when you disperse the light, you use either a prism, that is what Raman used. And today we use gratings, and we can actually resolve it much more better to know what are the different lights. And Raman actually got these lights on a photographic plate. And the photographic plate, you can see this is the elastic scattering. And this is your inelastic scattering on both sides. So this is the blue shifted light, and this is the red shifted light. And these are very characteristic to the molecules which you are having inside the liquid. Now this today you can digitize it. Basically, you can take a very good photo CCD and take a photograph. And if you take a photograph, you see here is the green light, which I actually put as the light for the Raman scattering. This is the elastic scattering of the light, very intense. And you can see many weak lines which are there. And we can always digitize it. And when you digitize it, you actually get peaks. So this is exactly how the Raman spectra looks like when you actually look at it in literature. I am always looking at the red side of it, not the blue side of it. So this is called the Stokes Raman, and I will actually explain why we only look at the Stokes Raman. But the intensities are different for various lines, and these lines are very, very interesting because the distance from, or the difference between these two lines is actually the energy of vibrations. So people actually are able to get vibrational energies of these molecules which you are looking at, or lattice in the case of solids, you are looking at, those vibrations energy is what you are looking. And that is the reason why in Raman, we always write at the bottom, Raman shift. So how much did it shift from the incident light? How much light got shifted? And that shifted light is actually the energy of the vibration. So today we can actually look at, say, let us say the spectra of CCl4. If I look at it, then CCl4 actually has a very nice spectra. And if I will say any tetrahedral molecule, the spectra would look similar, not same, similar. And that means if I had methane, it will also look the similar. So this is why Raman is a very, very interesting probe, because it is like a fingerprint of a molecule. So the coordination of the molecule, if it happens to be the same, spectra will look same. So you can characterize the spectra very, very easily. Now today we have computer programs. You can do MD simulations, or you can do Gaussian, you can do various other things, and you can actually find out what are the different vibrations this particular molecules will have, and what is the energy of those vibrations. So this is the simulation of the basically carbon tetrachloride. And you can see a tetrahedral molecule will have 4 different types of vibrations. This is symmetric stretching, where all the atoms of chlorine are moving away and coming closer to the carbon atom. Compressing while the others are expanding, and vice versa. So this is stretching modes. And here you can see it is bending of the bonds. So here is a symmetric bending, like 2 of them bending in 90 degrees to the other one. And this is asymmetric bending, where one bond is not bending, all other 3 bonds are bending. So these are basically the vibrations associated with any tetrahedral molecule. So whether it is CCl4, SO4, or CH4, or all of these things will have similar vibrations. But the energy of vibration depends on the atoms which are connecting this, and the bonds which are actually present. I will explain in the next one. So basically, you can also see that the energy of all the bending modes are lesser compared to the energy of the stretching modes. And that is very easy to understand, because when you stretch a bond, you need more energy compared to bending a bond. So bending the angle between the bonds. And so that is the reason why always the bending modes will be lower energy compared to the stretching modes. Now, very interestingly, I want you to see that whether this particular peak looks like a single peak. Very, very important it is to see that these peaks are not actually one peak. It is having multiplicity. But you are having a symmetric stretching, and symmetric stretching should have only single value. Now, whenever you have any spectroscopy, whatever may be the spectroscopy you are working on, NMR, mass spec, or UV visible, or Raman, IR, whenever you are doing these kinds of spectroscopy, if you think there are multiple peaks present, one of the best methods to actually resolve them is to lower the temperature, provided your molecule doesn't have any changes because of that temperature. So just lower the temperature, and if the temperature doesn't change anything in the molecule, you can resolve the peaks very easily. And this is what is normally done, because the width of the peak is dependent on the temperature. Now, when I actually lower the temperature, you can see I have used helium to lower the temperature. I go up to 28 Kelvin. But what I see is that this peak is actually not one peak, but it has multiplicity. Now, the reason why this happens is because chlorine is actually having 2 atomic masses, and that is Cl35 and Cl37. And this is in a relative abundance of 3:1. And because of this, you can imagine that, in fact, you can have all the chlorine atoms to be Cl35, which is a very lighter system. And whenever something is lighter, we always say it is having more energy. And that's why this particular peak is actually associated with all the four. Now you can realize that the next one has to be one Cl37 and another one is, three of them are Cl35. And next one is obviously easy to guess that two of them will be Cl37s and two of them will be Cl32. Now there are two more peaks and you can immediately guess that this is because of the fact this one is having Cl37s 3 and one Cl35, and this is all 4 Cl37. And now you can realize the intensity is directly related to the relative presence. So naturally 3:1 is the relative abundance. So that is the tallest peak. And you can see that Cl35s are actually possible because that is 75% of them being Cl35. So now you have a very good tool here that you can actually isotopically pure material, if you use, you can actually identify in a large molecular system, you can identify where the vibration is coming from. And this is quite useful in the case of studying large proteins and various other kinds of things. So isotope effect is there. Now, many of you would have a question, why are we not actually having any effect of carbon itself? Because carbon can be C12, C13, and C14. But you know the relative abundance is that it is more than 95%, 99% is actually Cl12, and Cl13 and Cl14 is very, very less. And that's why we don't see the effect of this isotope. So the weakness of the bands and intensity are also relative abundance it gives you. Now, very importantly, I wanted to actually give you an idea of how many vibrations can be there if I have n atoms. And this is a very simple concept which has been taught to you in 12th standard itself. Because when you have n atoms which are not connected to each other, these n atoms, when they move, can be described, and that is called the degrees of freedom. And they can be described by just translational motions, X, Y, and Z, because each of them are too infinitesimally small that they cannot rotate around themselves, or neither do they can vibrate around it. So they are too tiny. So only motions they can do is they can translate along X, translate along Y, and translate along Z, or any motion they are making is a linear combination of X, Y, and Z motions. So that is why we'll have 3 into n degrees of freedom, and that's what is called 3n possible movements. And now this is conserved whether the atoms are connected or unconnected. Now when they get connected, let us say they all get connected, naturally all the atoms now will be, any atom tries to move, all the other atoms have to follow that motion. So they can have multiple motions now. One is all of them move in the X direction or Y direction or Z direction, or any motion which is translational can be expressed as X, Y, and Z motions. And that's why we will have 3 types of motions which will be normal coordinates, which will be X, Y, and Z translation. Now, since they have connected together, there is a center of mass associated with them. And around the center of mass, they can actually rotate. And when they rotate, they can rotate along X axis, Y axis, and Z axis passing through the center of mass. Now, when, let us say, all the atoms are connected to, in linear fashion, since atoms are infinitesimally small, so what happens is that the rotation along the direction of the linear atom connection will be not considered. We will only have 2 types of rotations perpendicular to the linear direction of the atom's connection. And that's why So the total number of rotations would be 3 if it is nonlinear and 2 if it is linear. Now, we had 3n degrees of freedom. Now we have 3 translation and 3 or 2 rotation. The remaining possible movements will be vibrational around the center of mass. Vibrations are actually around the center of mass. The atoms can bend or move or stretch or any of those things without actually moving the center of mass. So center of mass remains at the same point, and the atoms can move with respect to the center of mass, either bend or stretch, any of those things. So the number of vibrations now becomes in a linear molecule 3n minus 5. And in the case of a nonlinear atom, it is 3n minus 6 vibrations. So these are the total number of vibrations possible in any molecule. Now, we can actually look at it in simple systems. So I have taken HF and I have taken HCl. The only difference between HF and HCl is that fluorine is lighter than chlorine. And you can see earlier I had told that whenever systems are lighter, they will have more energy. That means the vibrations will be vigorous. And this is a easy way to remember, because we always say heavier things are sluggish and lighter things are more energetic. And so mass is inversely proportional to the energy. And that is what is shown here. And very interestingly, we use a unit which is called centimeter inverse. This is an interesting unit. Always in fluorescence talking about nanometers or Armstrongs or any of those things. But whenever we talk about this frequency here, we talk the frequency in terms of centimeter inverse. The reason is because 1 by lambda is nothing but C times C nu. You actually have this nu lambda is your velocity. So naturally, 1 by lambda is inversely proportional to frequency. So centimeter inverse is directly related to your the frequency itself. Now, I think, thanks, JD. So basically, when we are talking about centimeter inverse, you can see it's an easy conversion to energy. 8,000, roughly 8,000 or 8,086 centimeter inverse is 1 electron volt. So you can see this is actually 500 milli electron volts thereabout, and this is about 300 milli electron volts. So most of your vibrational energy would be lying in between around 10 to 50 milli electron volts to all the way till 500 milli electron volts or 550 milli electron volts. This is the range of energy of all the vibrations which you can find in the nature. So this is very important number to remember, because we are actually working in that energy range. Now, very interestingly, if I add one atom to that, immediately I see the number of vibrations increase, and according to the degrees of freedom. Now, earlier it was 2 atoms, so 2 into 3 minus 5, because it's a linear atom, only 1 vibration is possible. Now, the moment I actually add one more atom, it is 3 into 3 degrees of freedom, that is 9 minus 3 translation and 3 rotation, which means I will have 3 different vibrations. So any molecule which has a shape of this, or like water molecule, will always have these 3 vibrations. And these vibrations are symmetric stretching, asymmetric stretching, and symmetric bending. And you can see the energies are actually higher for the stretching and lower for the bending. And this is all you will have. Now, when I actually increase one more atom, the total number of vibrations now should be 3 into 4, that is degrees of freedom, that is equal to 12 minus 6, that means I should have 6 vibrations. But any molecule which resembles NH3 or trigonal pyramidal molecule will have only these 4 vibrations, which is symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. This is because now another concept comes in, that there is a symmetry associated with this molecule. If I look at this molecule from this direction or this direction or this direction, they look exactly the same. So there is a symmetry associated with it. So some of these vibrations are degenerate. That means if suppose this was stretching and these two are compressing, I could also imagine this is stretching and this is compressing. So there is but in nature, I cannot distinguish it. They will look exactly the same. So this is a degeneracy. And similarly, I can have a degeneracy because these two are bending, and you can say these two can bend. So this is the degeneracy, and that's how the 6 comes in. And that means whenever you have a molecule which looks little more symmetric compared to the asymmetric molecule, the number of vibrations will be lesser. So if your spectra is supposed to be, Raman spectra is very clean, very less number of vibration modes, then we can easily say that this molecule is more symmetric compared to a molecule which will be asymmetric, will show all the vibrational modes possible. To extend this analogy of symmetry, I have taken another molecule which is having 7 atoms. So the moment you have 7 atoms, your number of vibrations will be 3 into 7, that is the degrees of freedom. So that is 21 minus 6, that is 15. So when you actually have 15 vibrations, but because this is an octahedra, the most symmetric molecule you can ever have, and this is SF6, so you have symmetric stretching, asymmetric stretching, asymmetric stretching, symmetric bending, asymmetric bending, asymmetric bending. You can see the bonds are stretched. Here the bonds are bending. Here the bonds are bending. Bonds are bending. So this is the 3 bending modes and 3 stretching modes. Now you can realize that this could have multiplicity. And this could have multiplicity, this could have multiplicity, this can have multiplicity. And that means there are degenerate modes. And that is the reason why 15 modes collapse onto 66 modes. And how to actually see that the number of vibrations can be increased? Just replace one of these atoms by another atom. And immediately you will start seeing the effect of asymmetry. And asymmetry will actually be immediately visible. So this is a beautiful way vibrational spectroscopy can be used for, without actually analyzing anything, you can say whether the molecule is symmetric or asymmetric. So this is basically the thing. Now, the concept is, how does light actually interact with the vibrations? And the vibrations can actually give me information about the energy of light gets shifted. So this is where I am going to show you how we can actually understand that light can actually interact with these vibrations and give information about the vibration itself. So here I would like to mention that there are 2 things we are actually having. One is light and another one is the molecule or the solid, whichever it is, lattice or molecule we are having. Now, you can actually understand Raman spectroscopy in 2 ways. One is, consider that the light is actually classical. That means it is electromagnetic radiation. And you can also understand that molecules can be just rotators, rotors, or vibrators, or all of those things. So they are classical. With this kind of a picture, this is called the classical theory of Raman spectroscopy. You can actually understand how does the vibrational frequencies shift, interact with the light and actually shift the frequencies. And it can also give, to a limited extent, information about why it will be Raman active or Raman inactive. Those kinds of information can be gotten. If you want to understand the total understanding of light matter interaction in Raman, then you can do another way of doing it, is considering that the light is actually still electromagnetic, but you can consider the particle as quantum mechanical, And hence you can actually understand the various aspects of that. That gives you the complete understanding of Raman. This hybrid method can be called as quantum theory of Raman spectroscopy. But ideally, you should have considered the light as quantum, as well as molecules as, or atoms as, or lattice as quantum. That is a complete theory, quantum mechanical theory, where you will do quantum electrodynamics and you will do quantum mechanical treatment of the particles. But interestingly, this is a rigorous method. The results what you get are more or less similar to the quantum mechanical theory of Raman spectroscopy. So to make things easy, I will start with the classical theory of Raman spectroscopy without loss of generality. I can actually explain how shift happens because it becomes easier to explain. But whatever I am saying in classical, I just have to substitute quantum mechanical expressions and immediately it becomes the quantum mechanical theory. So that's why I won't be having any difficulty if I want to extrapolate it to the quantum mechanical. But it is easier to understand what is this. So whenever I have a diatomic molecule, you have also studied in your 12th standard that two atoms connected with this, or two balls connected with a spring has a possibility to oscillate, and these oscillations have a frequency, and this has been solved very nicely using classical mechanics, and that has been done in your 12th standard. And you realize that the frequency is proportional to the spring constant, which is the spring associated, and it is inversely proportional to the reduced mass. Reduced mass is actually given as m1 m2 divided by m1 plus m2, which is basically coming from the fact that 1 by reduced mass is equal to 1 by m1 plus 1 by m2. Hence, m reduced mass is giving you that expression. This also now can be easily understood because as the mass increases, your frequency will decrease, so the energy of vibration will be lesser. Spring constant increases, it becomes more stiffer, then you will have the energy is going to be higher, and that means your frequency is going to be higher. So this is a simple classical mechanics. But when you are considering a ball, we do not have any problem when the light falls on it. But when you have atom and a bond, now you realize atoms are not actually just a ball. It is actually made up of a positive charge, which is the nucleus, and there is electrons around it, and that is negatively charged. And you know that electromagnetic radiations have both electric field and magnetic field, and we will not consider magnetic field. We will only consider the electric field. Now, this is an oscillating function. So because it is an oscillating function, you can write electromagnetic radiation as E in space and time. And in space and time, it can be written as E, that is the maximum of the electric field, times cos into omega t plus k, that is momentum into space. So this is actually the space. So if I was actually looking at electromagnetic radiation here and here, I would have to know which is the momentum, which direction it's moving, and how the electric field would be present. Similarly, for time, I'm actually sitting at this point and watching how the electric field is changing, and that is what is given by this. So that depends on the frequency of oscillations of this electromagnetic radiation. So these two factors are there. But you realize, and earlier it was told by even Sudipta, that when light is coming, the molecules are Brownian motion. This is much slower compared to the speed of light. So at a point when the light photon is actually interacting with this, it is instantaneous. That means the molecule remains stationary. So the X part is not at all to be considered because the electric field is not distance dependent. So electric field is only time dependent. And that means I will actually forget in the future discussion anything about the space, and I will actually only express omega t, cos omega t. So once that is done, I realize that because there is electrons and there is nucleus, and I am putting electric field is going to separate the charges. So initially the atom was neutral, so there is no dipole, or maybe it has a permanent dipole, doesn't matter to me. But as soon as I put electric field on it, I am actually going to displace the charges. And this charges will be displaced, and you know that electrons are much lighter compared to the nucleus, because proton is 1,000 times heavier than electron. So naturally the nucleus will never be moved much, while all the movement will be from the electrons. And as soon as the electrons move away from the nucleus, you develop a dipole. And this is called polarization, and this is called induced electric dipole. And you can see the electric dipole is induced, and this is dependent on three factors. There will be first order, second order, and third order of the dipole created. And you can realize that it is actually the polarizability of the electrons, which gives you the first order, and hyperpolarizability gives you the second order, and second hyperpolarizability gives you the third order. And if these are called the new nonlinear factors in the dipole, and this gives you the nonlinear effects, while this is the linear effect, and this is what gives you the Raman. So this is the nonlinear part. And you realize that to accentuate the nonlinear part, which you will be coming across while the light matter interactions are discussed, this needs because these are very small quantities, to actually measure them, you need to have high electric field. That means laser intensity should be very, very high. And that is why all the nonlinear effects will be actually done using high energy lasers. But Raman is usually done with the linear part of it. And this is what we will concentrate on today. So basically, it's a vector. So basically, electric field is a vector and dipole is a vector. So the multiplying factor is actually a tensor, and that's why it has two components. These are all for you, those who are interested in the mathematics of it, can understand how the vectorial multiplications happen. I would not be discussing anything in the nonlinear. I will only be discussing the linear part of it. So when I actually look at this, I see that the induced dipole is actually proportional to the electric field, and the proportionality constant is actually your what you call as polarizability. And polarizability, if it happens to be a constant, let us say temporarily, I assume polarizability is a constant, then it actually is going to give me directly the same, the induced electric field will be actually doing a dipole, which will be oscillating exactly the same frequency as the electric field which was introduced. And that is what is called elastic scattering or the Rayleigh scattering. But when you are having this light incident, the molecule can also vibrate. And when molecules vibrate, the electrons have to travel with the nucleus. That means your alpha is not a constant. It is actually a function of these vibrations. And hence, you can see that this alpha, it can be expanded in a Taylor series, because whenever the vibrations happen, these are not large-scale vibrations. They are small oscillations. And hence, small oscillations can be expressed as a Taylor series. And you can look at a Clark's table and you will realize Taylor series is expanded in this fashion. So this is your quantity which is unperturbed, and this is because of the vibrations itself. And each vibration will actually contribute to the your polarizability term. and that is actually dou alpha by dou Q, and this is the higher term, dou 2 alpha by dou Q square, where you can have multiple vibrations and they can actually produce the products. Now, when we look at it, this is the first order Raman, and this gives you the second order Raman. And I won't be concentrating on second order Raman, and you will realize second order Raman is very, very important. And most of the time, second order Raman gives you all the combinations, either omega square, or it can be omega 1 plus omega 2, or omega 1 plus omega 3. Various combinations can happen. And that's why it gives you a density of phonons. Actually, this is directly related to the density of phonon. Second order Raman is actually a signature for the density of phonons itself. I won't be discussing this in this lecture. Anybody wants, they can actually ask me during other interactions. So I will actually limit myself to this. And so this is basically how the alpha is there. And you see the oscillations of the vibrations are also having a frequency. And this can be written as cos omega vibration of the frequency plus a phase factor, which is I have added that. Now, when I substitute this into this factor, now I all of a sudden see that there are two terms which are coming. One is actually the elastic scattering, and this is the inelastic scattering. But all of us know trigonometrically, cos A into cos B is written as cos A plus B and cos A minus B. So as soon as I do that, now I see my induced dipole has three frequencies with which it will be oscillating. And these three oscillations are, this is elastic scattering, this is inelastic scattering, which is omega laser minus omega m. This is the red shifted light, and this is the blue shifted light. And that's basically what you have actually seen. Now, this is for every vibration, you will have these two parts. And this is why you have red Stokes and anti-Stokes Raman. And you will realize this is going to be, this is at dou alpha by dou Q. That means the polarizability, when we are taking the slope of the polarizability as a coordinate, the oscillations, then at equilibrium, if it happens to be 0, that means it is a maxima or a minima, then it will actually be Raman inactive, because this is going to be 0, and that means this will not have any contribution coming. So that is what is the selection rule. Now, one more thing I wanted to mention is any oscillating dipole produces electromagnetic radiation. So the molecule itself now starts oscillating dipole and oscillating. This is not the vibrations of the molecule. The electric field is actually splitting the charges, and that is oscillating, and that produces electromagnetic radiation. It has one frequency, which is elastic scattering. This is the inelastic scattering. One is red shifted and the blue shifted, and that's how you get the frequency. Now you can understand how the polarizability changes when the atoms are, like, you take a hydrogen atom, when they are not bonded, this is the polarizability. That is the summation of the polarizability of the electron of one hydrogen atom and the other hydrogen atom. And that is going to be this value. As you bring the atoms closer and closer, then what happens is that polarizability is going to be affected. There will be more polarizability in different directions. In the parallel direction, it will be polarized much more. And parallel direction, it will be polarized more. And in the perpendicular direction, it is difficult to polarize. And once it actually reaches a particular distance of distance between that, before bonding, it starts actually to decrease, because now the electrons are being shared between the atoms and the polarizability actually comes down. So this is how you can see that at bonding distance, this is the polarizability. The polarizability of two hydrogen atoms separately is much higher compared to the polarizability of a hydrogen molecule. And this is how you can describe it, and you can see that the polarizabilities are going to be different. Now, when molecule is oscillating, it is going to have different polarizabilities on either sides, and that is what is showing up. Now, when I look at any molecule, I can actually see if it is a diatomic molecule, both hetero and homo, that means AA or AB. What happens is when you have a stretching mode, the polarizability is when it is compressed. When you compress this, the electrons are going to be very, very close, very densely populated. So when I apply the electric field, I can polarize it more. So the polarizability will be higher. And when I stretch the atoms, the electrons are spread over a larger atom. So my polarizability will be lesser. So my polarizability is a monotonically increasing function. So at equilibrium, my slope is not non-zero. So this is a Raman active mode. So this is basically how you can actually understand. Now, if I actually look at, so if I look at a carbon dioxide system, there is no dipole associated with it. So when I induce when I put the molecule in vibration, you can see when I compress the molecule, the polarizability is high, and when I expand the molecule, the polarizability low. So what happens is that at equilibrium, the slope is non-zero. But if I was actually considering an asymmetric stretching, then when I am compressing here, the polarizability is higher and the polarizability is lower here. So naturally, the total polarizability before it was actually doing this motion is going to be higher, and to one direction, it is positive. And when this is compressed and this is expanded, this polarizability is higher compared to this. So this will be higher than the two of them. So naturally, it is like a minima. So if I draw a slope here, it will be 0, and hence this is Raman inactive. Now, similarly, I can consider bending. In carbon dioxide being a linear molecule, there are two types of bending. These are degenerate, and I can consider any one of them. So when I bend it, the electrons are going to be denser. So found in one direction, both of these bonds coming closer, it will be higher. And when it bends upwards, again, the electron density will be higher. So polarizability will be higher. So it will actually be a function which will be a parabolic. So the slope at this point will be non-zero, zero. So that means this is going to be bending modes are going to be Raman inactive. So it's a very easy way to actually describe this. Now, this doesn't give you certain other information, as I said. This is a classical. So you could get this understanding of why frequency shifts and why you are having these possibilities.
Bhas?
Now, yeah, I have
Bhas,
3 minutes more.
At 45 minutes, but yeah, you finish. Yeah.
Yeah, 3 minutes I will be finishing. And I have 3 minutes now. Yeah. So basically, this is where I will actually introduce the quantum mechanical part. And this quantum mechanical part is going to be introduced for the very specific reason, because my Stokes and anti-Stokes intensity is the prefactor to this frequency oscillation. So this prefactor is the same for Stokes and anti-Stokes. But in general, when I take a recording of the Stokes and anti-Stokes, you can see that always the anti-Stokes is weaker compared to the Stokes. And this is for this very important reason that if you have a Boltzmann's distribution, you will realize that it is actually dependent on the population of the excited state and ground state. And always you know that the ground state is more populated compared to the excited state. So this population is not the same. So basically, the number of excited states divided by ground state is going to be actually a function of the energy of the vibration itself. And this is one of the reasons why quantum mechanics has to be introduced. So I will not introduce anything beyond what is necessary. I had already told you that I was using that dipole. Now I have to have quantum mechanics. So I will have initial state and final states. And so this is the Stokes and this is the anti-Stokes part in the wave functions. So basically, this gives me the Raman scattering, and that is a third order perturbation. And basically, you have electron radiation, electron phonon, or electron vibron, and electron radiation. There are three terms. The reason why it happens is when light falls on it, the light is absorbed by the electrons. And always in the previous two talks, you had energy levels present. In here, there is no energy level because the light can be any light which I can provide. So naturally, what happens is it goes into a virtual state. Now, virtual state is described as whenever a molecule gets excited, it's all the eigenstates actually cause linear combinations. And these linear combinations can be many of them. And hence, you can actually absorb any amount of light. But these are virtual, they are not real. So they are very short lifetime. So the moment it goes up, it comes down instantaneously. So that is the elastic scattering. It is an electron radiation interaction. It will come down. But you know that electronic states are coupled with vibrations. I have separated it out in space now, but actually they happen to be in your Jablonski diagram. It will be written as vibration states and electronic states coupled together. Now I have separated out. When electrons are excited, it can actually interact with the vibration. It can give some energy or take energy from the vibrations. So when it gives energy, it actually excites a ground state vibration to the excited state, then loses energy. It is redshifted. So it gets redshifted. The light which comes out is actually a redshifted light. You can have the reverse also possible, excited state coming down to the ground state. And when that happens, you are actually going to increase the energy of the light. And now when it comes down, it is blue shifted. And this is how you will have. Now you realize the energy of the excited state, the energy of the excited state is larger. And since it is larger, the population of an excited state is always less. So this process is going to be less compared to this. And that is the reason why Stokes-Raman is always weaker compared to the anti-Stokes-Raman. Now, there is another interesting thing which can happen. If you have energy states of real present in this virtual state, and that happens, this energy, because of the perturbation theory, this is denominator, this could actually go to zero and or closer to zero. Then this whole Raman cross-section increases. This is called the resonant Raman, and that JD is going to talk about it in his talk. So you can also have the real states being when it actually has an interaction and goes into the state. Now, this is the last thing I will say. So this is what JD is going to take it over from here. So when normal Raman happens, these two energy levels are far away from it. And you have a virtual state, and that is going to be the normal Raman. But when you have energy of the laser light, which is coming closer to the absorption, then you can realize that you will have an intensity going up because of that. Now you can have exactly matching the energy of the absorption. So then your Raman signal becomes resonant, and you can exceed the energy level, go into the continuum, and then you will be little above that, and that can have very different effects. So this is off resonance. This is also off resonance, but there are a lot of interesting facts which gives you information about the vibrational states and interaction of the electronic states. So at this point of time, I will stop here, and the remaining part I will actually take it after as a specialized thing. I think I have given enough introduction to the Raman for a normal people who are interested can come to my next lecture, which will be in person, and they can actually interact with me and ask. Hope JD,
yes, thank you.
Justified what I had to do, right?
Yes. Perfect, Chandrabhas. Thank you very much
Yeah.
for elaborately describing Raman as you do wonderfully well. So in short period of time, there is so much to cover, but thank you for giving the concept. And for all the students who want to get a little bit more in depth into this idea, Chandrabhas's lab will be open at 4 p.m. For a demo, and Debanjan Bhaumik, who is a faculty at RGCB, will also be there, and will be there to demonstrate some of the features of the equipment that Chandrabhas has. And for more information on instrumentation, please join us in the in-person FCS in November in IIT Bombay. where according to the schedule, Chandrabhas will start with the instrumentation part. Okay. So Chandrabhas, thank you. Now we have a few questions, Chandrabhas.
Yeah.
Maybe we can address them. And
Yes.
okay. So the first few questions, Sujan Manna from IIT Madras, he is asking how to reduce the ratio of intensities of closely residing peaks. I mean, the example you talked about, that is about chlorine, if we follow isotopic abundance of chlorine, the most intense peak has to be where 435 Cl atoms are present. But that's not the case here. Thank you.
So you missed the point. It is 3:1 is the relative abundance. That means at any given point of time, if I am actually randomly picking up, if my chances of having 75% of the chlorine atoms being 35 is the most common case. 25% will always be, if I am unbiased picking up. When I am picking up, there is a possibility that I can pick up all 4 chlorine atoms. But that is not going to be higher probability compared to 3 chlorine atoms and 1 Cl37 chlorine atom. So that is why the intensity of 3:1, because that is the relative abundance of the system. So it is reflecting the relative abundance. That means 75% being chlorine being 35 and 25% being 37 is the most ideal case if I am unbiasedly picking up the atoms. So that is why that is the most intense. That is the answer for that.
Okay, thank you. Thank you, Bas. Then the second question is from Pramod Kumar from JNU. Wonderful talk, sir. At what circumstances here the electric field doesn't depend on space, it only depends on time? I did not get the point.
Oh, okay. So what I was telling is that the electric field has, whenever you are describing electric field, the electric field is traveling in space and time, both the things. So whenever you have to tell about a particular position and time, you want to describe what is the electric field going to be, you need to have the frequency component of the time and the momentum part of the space. So that is why you write it as omega t plus kx. Now, when a molecule is there, the molecule is doing Brownian motion, but the Brownian motion time scale is in milliseconds, just as told by Sudipta. It is actually very slow. When the light comes in, it is coming at the speed of light, and which is like many photons can come at any instant of time. So that means when the molecule is interacting with the light, there is no need of actually considering the electric field effect due to the space. So that is why I have removed the space part, and I am only looking at the time dependence of the electric field. And that's the reason why we have actually taken omega t, not kx.
Thank you. Thank you, Bas. There is a question from Shivani Tripathi, BITS-Pilani, Hyderabad. Very nice talk, sir. Do Raman spectroscopic technique can be used to differentiate between different isotopes of oxygen present in the same molecule at different positions?
So again, if you look at the relative abundance of the oxygen itself, it is not as high as chlorine. It is actually very, very close to 1 or 2% of that is O18 or O17. So that is one of the problems, because whenever the relative abundance, that means I have 100 atoms, probably 2 of them will be, or 1 of them will be actually going to be O18 or O17. And because of that, we will not be able to detect the effect of O18 specifically. Now, if I want to see O18 or O17 effect, then what I have to do is I have to get the O18 in my preparation so that I isotopically pure O18s I add to the molecule. This is done in amino acids. Most of the times, we actually prepare amino acids which are isotopically pure. In most of the cases, it is deuterium, or you add nitrogen, or you add C13. These are the 3 normally available things. In here, we can also make it O18 or O17, and you can prepare any molecule, and now this will have the isotopic effect.
Okay. The question actually also had that, can you distinguish the positional isotopes?
Yes, yes, you can actually. So many times we do so you put your protein in deuterated. D2O solution, if you put labile hydrogens actually get replaced by D, and it doesn't completely replace, it will have H also, D also. So you will have two peaks coming because of that. So you will actually be able to see these double peaks, and they are shifted. D is heavier, so it shifts to the lower frequency. So yes, we do see the effect. Now, normally it is in cases of labile hydrogens where hydrogen can be displaced by the deuterium.
Okay. Okay. Then another question by Rahul Yadav, A.S.R. Bhopal. It's not a question. It actually says, a wonderful talk, sir. I never learned Raman in this way. Awesome. Okay.
Thank you. Thank you so much. It's a
okay.
great feedback.
Okay. Arun Kumar Upadhyay asks, what is the same type of Raman active atom is present? What if the same type of Raman active atom is present at different vibrational state?
No, actually, atoms cannot be actually vibrating. It is a single atom cannot be vibrating, but it is actually a molecule. Probably what you may be meaning is, if there are atoms which are connected in different places, the same atom is connected in different ways, then the frequencies will be dependent on the coordination of that atom. So one example, trying to actually probably give a little more information than that. Suppose you have a planar system. So you have say whether it is a planar or pyramidal, if you want to actually understand. Then if it is a pyramidal structure, you know that many of the times you can have a conformation where it can be a planar or a pyramidal. And depending on the planar or pyramidal, the spectra will be totally different. And that is how you can actually distinguish. The same atoms are connected. So let us say platinum is connected to any, say, chlorine or something. It's a planar system. Now, if you slightly distort it and make it into a pyramidal, a square pyramidal, then you will actually have a totally different spectra. So same atoms can actually give you different spectra depending on the coordination there.
Okay. And then this question from Shujan Manna. Do resonance Raman or non-resonance Raman affect the time scale of transition of the spectrum? As for resonance Raman, the virtual state is exactly lying on the next excited state.
So actually, we don't have to consider virtual state in that case. The virtual state is actually required only because we are actually putting in, we have been always told that you need an energy level, then only the absorption will take place. But here we are actually talking about absorption of light when there is no levels present. And that is why we introduce the concept of virtual state. In normal sense, real states are always present in the molecule S0, S1, S2, S3, all of these things, triplet states, everything is present. They are all real eigenstates. But many a times the energy of the wavelength of light used for Raman, because it's wavelength independent, you can absorb any of the light. And this absorption happens instantaneously. And that is because whenever a molecule is excited, it can actually create instantaneously many combinations of the eigenstates, and that's what is the virtual state. And virtual we call it because we can't measure it, because this excitation happens and de-excitation happens instantaneously. Lifetime is so short that it is below 10 to the power of minus 15 seconds, so it is very immeasurable, and that's why the virtual state. So real states are actually absorption states.
And there is a finite lifetime for
lifetime
resonance state. So
resonance states have finite lifetime. Yes.
And
I want to say JD is going to completely emphasize on this aspect.
Right. Okay. Okay, Bhas. I think that ends it right on time for lunch. And so thank you. Let's have a big round of applause for Professor Chandrabhas and all the teachers in the morning session, Sudipta and Anindya. Thank you for delving into the concept so well and keeping the audience entire day engaged, the day part of the entire session engaged and asking questions. So thank you very much. Let's take a break for an hour for lunch and we will resume back with Professor A.S.R. Koti, who is going to give us basic understanding of AFM and how force measurements can be done using AFM. Okay, so we will resume back at 2 p.m. And thank you very much for joining right now. Yeah.
Thank you so much, JD, and thank you everyone. And wonderful, always to be part of the FCS.
Yeah, sure. Thank you, Bhas, for the time. Yeah. Koti, you can check the slide if you have something.
I haven't seen Koti for a long time. What is this, Koti?
He's here.
Show your face.
Yeah, he's actually right now muted. He's going to
He's come.
Yes, there he is.
Hi, Chandrabhas. Yeah, it was nice to see you and it was a lovely lecture,
Thank
recap
you.
of Raman spectroscopy.
Thank you so much.
Yeah, so JD, just I'll check maybe
Yes.
slides.
So people will join back again
At 2 o'clock, right?
at 2 o'clock. Yeah, but I will keep this on, so the Zoom is on. So.
Yeah. Do you see my screen?
Yes. Perfect.
Okay. Perfect.
Thank you, Koti.
Yeah.
Yeah.
Okay.
So we'll keep this on. We'll keep
Yeah,
the
sure.
first slide on.
No, I'll be logged in anyway. Okay. See you at 2.
Thank you. Yeah. Bhas, have some lunch.
Yes.
And then I think 4 p.m. is a demo from your lab. So.
Right. All my people have done some mocks already.
Okay.
So hope that is going to be going smooth.
Yeah. Okay. Thank you. Yeah.
You will be also there for explaining,
Yes,
right?
yes. I will actually do a journalism course
Yes.
because I will go from one track to another track and cover some of these aspects because this is going to the YouTube. So we will keep all the labs. We will show some aspects of all the labs.
Correct. Thank you. Thank you so much.
Yeah.
So see you later after
Yes.
lunch.
Yes. Koti, you're here, right? Okay, okay. Yeah, no problem.
I'm here. I'm here, ready.
Yeah, yeah, sure. Okay, okay. I can hear you from the office also.
I know, I know.
Please put your institute name along with full name. Otherwise, we can't
Got
get
it,
you
got it. Yeah, I
inside.
know to distinguish, I understand.
Okay, Koti, we are 3 minutes away.
Yeah,
So maybe you can share the slide.
okay.
Okay, great. Okay. So I think we can give 1 more minute and then start.
Yeah. Yeah.
So 45 minutes, I will essentially,
Yeah.
if you can keep
Yeah.
it to 45 minutes, then 15 minutes we can have questions.
I see. Okay. This window or top up, it's coming by default, even if I hide. Is there any way to hide?
What
Yeah,
kind of?
but if you hide again within a couple of seconds, it's coming back. That sliding window. No?
Okay, wait. I'll just come.
So when I hide, it's coming. Oh. No. Yeah, no.
And then here is that coming. That press that.
If I do this, okay.
And then
See, if I do this, it hides, but within a couple of seconds, it's coming. It's okay, mate.
okay, so here.
Because I'm the co-host, maybe. Yeah, that's it.
Okay,
It's coming. Because I'm the co-host, because someone is joining, so it's popping up.
Not getting that. Oh,
No, because I am sharing the screen. No?
Sure.
I don't think it's old and new because I'm the co-host.
But this
It's
should
okay.
not-
It's
Can I
annoying.
move also the first part?
Yeah. It's fine.
Okay, we welcome you all to this session, the post-lunch session. Oh, you can't share otherwise, Koti.
Okay. Then you have to make me co-host.
Yeah, I'll make you a co-host. Okay, Koti, yeah. You can share again.
Yeah.
Okay, so here is the thing. Let's welcome everyone after lunch. And I think some people are still joining in. So I will give maybe 1 more minute, Koti, for people to continuously join in, and then we'll stop. Okay.
Yeah, sure.
So it's fantastic that Professor Koti, A.S.R. Koti from TIFR has agreed to give us this conceptual talk on AFM and how it has wide range of applications in chemistry, material science, and biology, and also delve into a little bit details of how AFM tip can be used for doing some very exciting force measurements. Okay, so I will leave it at that, and maybe Koti, you can take over.
Okay.
Thank you.
Thank you, JD, and good afternoon to all of you for coming on a Saturday afternoon for this exciting teaching workshop. I think today and yesterday, I think you have heard variety of experimental tools, to really probe molecules or even atoms or cells, and then understand their, chemistry and physics and biology of this. So today my job is to introduce you to an interesting technique called atomic force microscopy, which has been there about past 35 years or so. Okay, which has applications in all branches of science you can really think of. Any experimental science, okay, including chemistry, material science, and biology, you can really apply this tool and then to learn something about the sample. Okay, so because you were learning about various types of spectroscopy, including optical spectroscopy, over the course of today and yesterday, just I want to delve into how AFM actually can fit into this umbrella of microscopies, how AFM can complement existing traditional optical microscope. Okay, so you already know that traditional optical microscopy is used for looking at the samples at higher magnification. Like if you use traditional optical microscopy, you can easily get about 1,000-fold magnification. And the optical resolution mainly is limited by the wavelength of the light you are using. For example, if you use green wavelength light, so your resolution is limited to about 250 nanometers. So anything less than 250 nanometer using a simple traditional microscope, you'll not be able to see. And just I want to really remind you here that we are talking about now angstroms and nanometer. So just 1 nanometer is 10 power minus 9 raised to meters. Point and 1 with 8 zeros between that. Okay. So optical microscopy is very good. For simple reason is that you can really watch cells or living systems. Not only shown example here at the bottom, right? That you have a eukaryotic cell, with bacteria growing inside the cell. So you can really identify this here. Beautiful, right? So, but let's see how AFM actually can differ and complement this microscope. Okay, so now we are talking about different sizes of systems, as small as atoms, few angstroms. Optical microscopy can't be used, as you know. Okay, but AFM can in principle be used if you have a sophisticated AFM in vacuum conditions. Literally, you can really identify atoms. I'm going to give you one example where you can really identify atoms in a material, like graphite. Let's say if you increase the size to a few angstroms to nanometers, then you have plethora of chemical molecules, typically made in the lab, have tens to hundreds of atoms, right? And these molecules can be again easily visualized by atomic force microscopy, where optical microscopy is not the right tool. But if you move to much larger molecules like biological systems, where you work with or even chemical systems like large polymers and protein molecules, so where you have a few nanometers consisting of thousands of atoms, again, in some cases, optical microscopy can't be used right away if you want to really see the individual molecules. But AFM, beautifully, you can really identify these molecules. I'm going to give you again one example in this case using DNA. When it comes to real living systems or individual cells, biological cells, which are really large, about a micron to hundreds of microns, and consisting of thousands and thousands of atoms. This is where optical microscopy really changed our world in how actually we understand these systems. And AFM can also be used in this range. Okay, so why AFM is important? Okay, AFM atomic force microscopy is a type of scanning probe microscopy. I'll explain what is the meaning of scanning here and what is a probe. And as I already told you, the resolution of AFM can be 1,000 times better than optical microscopy. Okay, or in principle, we can really have magnifications of the order of 1,000,000 times, 10 power 6 times. And that's why you can really use AFM as a tool to look at systems from the imaging or manipulating matter, like protein molecules, which I'm going to show you again, at the nano scale. Means that either you can image with high resolution, or you can really manipulate the individual molecules in a way where you want to really study their properties. Applications, as I mentioned, everywhere. chemistry, physics, biology, solid state physics, semiconductor science, molecular engineering, polymer surface chemistry, molecular biology, cell biology, and even in medicine. Okay. So what is AFM? So I'm going to run this brief video. Just a minute, I'll just reload again. Maybe there's some problem with the video. Okay, video is not running.
Maybe just click.
Yeah. So for some reason it's not working.
Okay. Maybe Koti, you can share the screen, full screen.
Full screen is
rather than just the
what I'm doing, and then I have this. This is the full screen.
Okay.
It's okay, it doesn't matter. What I wanted to really show is that this is a nice short video where you have a sample shown at the bottom, and then how that sample is actually imaged at the level of angstrom level here in a what is called raster scan mode. Okay, so you start at one point, and then what you see is this rectangular thing is called cantilever beam, which is a force sensor. And then that is attached to a, what is called small stylus, or in this case, a tip. And then at the edge of the tip is actually interacting with the sample. So whenever you have repulsive interactions, the tip actually moves away. Okay, whenever there is attractive interaction, it moves towards the surface. So this moving away or attraction can be monitored using simple optical detection method, where you have a laser which is deflecting off onto the cantilever and falling onto the photodiode. So simply looking at the output on the photodiode, you can actually measure the position of the cantilever tip and then height of this position. So this is basically gives topography of that. I'm sorry, movie is not working. It worked earlier. Okay, so the AFM story is not complete before without telling scanning tunneling microscope. So scanning tunneling microscopy is a precursor of atomic force microscopy. So briefly, scanning tunneling microscopy involves a very sharp conducting tip or conducting wire. Here in this case, imagine it's gold with a sharp edge where you have few atoms of gold. And now you have a surface which is actually conducting. Now, if you bring the tip very close to the surface and keep a distance about angstrom to a nanometer, and then complete the loop using a simple battery, okay, and apply voltage. Now the current is actually going to pass between the tip and the surface through space, okay, or through air. So this is called tunneling current. So this tunneling current depends on the distance or the spacing between this. So using this simple principle, now you can actually raster scan this conducting tip over the surface, and then you can actually measure the topography of the surface. Very interestingly, this technique was developed about, again, 40 years ago, and Gerd Binnig and Heinrich Kroner got Nobel Prize, okay? And they invented this tool at IBM Research Zurich in 80s, and then this was awarded Nobel because it's really revolutionized the field by looking at directly the surfaces. What I'm showing at the right bottom is the carbon nanotube, where using STM, so they have actually imaged this. You can actually see the hexagonal Coulomb lattice showing the surface of carbon nanotube. Okay, so but however, the limitations of STM is only for the conducting sample. Unless you have a sample which is conducting, you will not be able to really measure the topography or the height of the surface. Means that people who are interested in working in liquids or biological samples are not allowed to use STM because there's no way you can actually make conducting. But the people found that how to even do remote conducting measurements by coating a carbon thin film, etc. But these are not really ideal. But then taking the cues from the STM, Binnig and along with Quate and Gerber, tried to really modify this tool so that the tool can be used for non-conducting surfaces. Okay, that's basically the genesis of AFM. And then with their thinking and then development, in 1985, they invented what is called atomic force microscopy. So these three are the gentlemen, Calvin Quaid, Gerd Binnig, and Christopher Gerber, were involved in inventing AFM and then demonstrating that how AFM can be really used to measure, interatomic forces, and then that principle can be applied over a surface so that you can get this topography of the surface. And so again, this is the prototype schematic diagram which they have used. They have used a very interestingly STM principle, and then combined with what is called profilometer to get the initial stages of AFM development. And what they have used, very sharp, tiny diamond, okay, which is sharp enough, shown here. I'm sure all you can see my pointer. It's basically the is sharp diamond and the right. And this sharp diamond is attached to what is a gold foil. Gold foil is now acts as a conducting surface for the STM, and then C is the conducting tip. So now B as a sharp diamond tip is trying to image the surface A. Okay, A is non-conducting surface now. So now, because of the interatomic potential between the E and the sharp diamond, they can be attractive and repulsive. But then the cantilever D moves away and towards the sample. And then because it moves away and towards the sample, the spacing between the gold foil and the gold tip changes, which can be used to measure using a regular STM tip. So this is a prototype. And this is the first demonstration in 1985, published in 1986. And this is one of the most cited papers in AFM field, of course, and also in general, if you consider general in science. It garnered about 25,000 citations. Very beautiful paper, about just 4 pages. I recommend young graduate students actually look into this. Very interesting. Okay, so this is the first thing. So this is the image of that real microscope, which is shown in the schematic. It looks like this. Okay. So fast forward about 30 years. Okay, so within 5 years of the initial demonstration, so AFM really, people thought that yes, it can be really used to understand, or apply in various branches of science. And within 10 years, there are many commercially available AFMs came into existence. Okay, so now fast forward about 30 years. Now the general principle of AFM is this. Okay, you have a cantilever, the long beam, rectangular beam shown here. That is a force tensor. Okay, so basically bending of that is translated into a quantifying force. The tip is the cantilever is attached with this tip. This is called the stylus. The stylus or the tip is the one which is interacting with the surface underneath. The surface can be anything now. It could be a dry condensed matter physics sample, or it could be liquid polymers in liquid conditions, or it could be entire biological cells or even living animals. Okay, so the principle is that now you have to basically measure the movement of the cantilever. So people use, there are different ways of doing this. One of the well-known method is beam bounce method. So basically simply you shine a laser pointed onto the edge of the cantilever and deflect off to the quadrant photodiode. So whenever the cantilever beam moves, the laser deflects, and then you can actually measure the force, measure the position of the cantilever. But then tip is interacting with the surface, so it could be attractive or repulsive. Depending on that, you actually measure this. So now if you do this at many points in a raster scan method, okay, imagine like a 2D grid. Now you can really get at every point in this 2D grid, the height of the sample. Now if you put that information together, you get what is called the surface profile, the topography of the sample. Okay. So AFM cantilevers are the central to the atomic force microscopy technique. Okay, there are a variety of cantilevers, okay, are commercially available now, very different shapes. Just I want to describe maybe one or two. I'm going to show these cantilevers in the afternoon demonstration. Okay, so you see the shapes are triangular here in this case, and then at the triangular edge you have, if you zoom in, you see this pyramidal kind of tip here. And so okay, see the dimensions. The cantilevers themselves are about 0.2 millimeter. Okay. So hardly visible to the naked eye, but the edge of those cantilevers, how now you have a micron size cantilever tips, and then edge of the tip is only few tens of nanometers. Okay, so now such nano fabricated cantilevers along with the tip materials can be really used, and you can have variety of materials depending on your application. So if the application requires a very rigid sample, but if you want high resolution, then you can have a tip which is really rigid. It could be even a diamond, it could be the silicon nitride, it could be just silicon itself, and it could be functionalized, and so on and so forth. Okay, and as I mentioned, tips can be different shapes and sizes. What I've shown on the previous slide are the triangular cantilevers, but now you can have the tip itself, you can have different materials. So this is like a pyramidal tip, and this is like a large glass bead about few microns. Because let's say if you are imaging a biological cell of 100 micron, there's no point imaging at nanometer scale or even angstrom scale, right? So then you don't really need ultra sharp tip. You can have coarse micron-sized bead. But if you have a sample where you have a very flat sample and you want angstrom level information, then you need a very sharp stylus, as sharp as possible. It could be as few atoms shown here. Okay, so these are the different types of cantilevers. But how does that cantilever along with the tip and the surface would give really the height information? So here it's shown now in this cartoon diagram. Let's say this is your surface which has corrugated information. Now as you move the cantilever and the tip along with surface in a raster scan method, let's say in one line. So now you keep the distance constant. How do you keep the distance constant? Because you keep the tip close to the surface so that it's, let's say it's repelling to some extent. Now you change the height such that this repelling amount is exactly the same at each position, which translates to the distance. Okay, so basically the distance is directly proportional to the force applied by the sample on the cantilever tip. So now you create this, if you move the tip along with this surface, it creates now this dotted line curve, where the curve is actually exactly equal distance from the real surface. Okay, so this is how actually you can measure in a raster scan, point by point, moving from one point to another point, and then you can really get a 2D grid of this information. And now that information is basically your topography. Okay, so that's why it is called a scanning, because it scans, and the probe is the cantilever plus tip. And then this is sometimes called a touching microscope or a feeling microscope, because the probe is in contact with the sample. Somehow you have to really touch the sample, then only you get the information. Okay, unlike in optical microscopy, where the light photons impinge on the fluorophore, but you don't really have to have any mechanical appliance going into the molecules. But in this case, AFM case, that's the thing. So mechanically you touch the surface. So that's why it's feel or touch microscope. Okay. So let's a little bit going into details about different modes of AFM because of different varieties of applications, different amounts of resolution you want. So you can actually, and different types of samples. Some samples could be very rigid, so they're very robust. But samples could be fluid, means that are flexible, so they are very sensitive. So then you can't have just one AFM fitting to the entire plethora of applications. So you need to really use and modify your AFM to the application at hand. Okay, but the main principle is the same. What I'm showing on the right side, it's called intermolecular potential. Okay, so what it says is that, so basically as you vary the distance between the cantilever tip and the surface, okay, when you are far away, there is no interaction. The interaction potential of the force is zero. But as you bring the cantilever tip towards the surface, so when it is close enough, sometimes you have attractive forces, okay? So then the cantilever is actually bent towards the sample. So this is what we have shown, okay? The curve is actually going negative in this case, force. Negative force means attraction. But then if you push further, so this attractive potential now becomes pushing, and then it will be a reverse repelling. So at some point it becomes zero, but if you push further, then there's a great repelling force between these two surfaces that will result in positive force or repulsive regime. So now this entire molecular potential is divided into different regions. Okay, so when it is positive force and repulsive, it's called contact region, where you can really define that the sample and the tip are in contact. Okay, so if you use this regime for your entire imaging application, you get the highest possible resolution. Because the repulsion is so high, the values are so high, you can actually measure them very precisely. Okay, but then if you use the region where not in the repulsive force, but in the attractive force, then it is called intermittent force. Means that half of the cycle in the imaging is attractive, half of the cycle is actually repulsive. Okay, so this is called intermittent for force region or intermittent contact region. So this is ideal for the sample where the sample is not very rigid, but then can tolerate to some extent of forces applied by the cantilever tip. But then if you use the non-contact, so means really far away, only tip is attracted depending on the distance. So this is ideal for biological samples where you don't really damage by pushing the AFM cantilever into the sample, so that the sample is preserved its properties. So basically these regimes are now divided into different modes. It's called, you might have heard that AFM in the contact mode. So that's where the forces are high and these are repulsive. And then non-contact mode, where the tip is much farther away from the sample so that it doesn't really damage, but then it comes very rarely towards the sample so that you don't damage the sample, but the resolution is not going to be very high. Resolution is going to be poor compared to contact. But if you want to compromise these two, sample flexibility and the resolution, then you can go what is called tapping mode AFM or intermittent contact mode AFM, where you can actually use this region to get the information of the surface. Okay, so what I'm showing on the left bottom side is that the danger of contact mode is shown that if the sample is very flexible, and then if you are doing raster scan, sometimes you might damage because it's going to damage the sample. But then resolution is going to be high. But if sample is not sturdy or robust, then there is a damage. Okay, it means at the end you don't really get the right information. But if you use intermittent contact mode, there is a slightly poorer resolution, but there's not much damage to the sample. But if you go to the tapping non-contact mode, so then you get the lowest resolution, but absolutely no damage to the sample. Okay, so now I'm going to give it to some examples to describe that how AFM actually changed, different branches of science. So if you use contact mode, you get highest resolution. Shown here on the right side is basically a graphene surface. So graphene surface is a modified graphene surface. So where you have basically carbon sitting on an hexagonal lattice. Okay, so each peak here is basically a carbon atom. Okay, so finally you can really connect and then you can get hexagonal thing. So contact mode, you can get high resolution, but the damage to the sample if the sample is not really robust. Can measure frictional forces. Okay, so now AFM not only gives the surface topography, how the surface looks like, but it gives actually other properties like how stiff is the surface. Is it like a soft, like gel-like, or is it a rigid surface? So you can actually measure the stiffness at locally, almost at the sub-nanometer region. Okay, so if you have a sample with differing stiffnesses, you can actually measure that. Okay, this is an important application in the field of polymer physics and polymer chemistry. Non-contact mode, low resolution, but not much damage to the sample. Tapping mode is basically bridges in between contact and non-contact, better resolution, minimal damage. So now, over the years, the AFM setups themselves have become very complicated for various reasons, because now you want to have more functionalities. Okay, but this is the diagram. It shows that schematics. What are the important elements? Still, the important elements are the cantilever with the tip, Okay, that's basically central to the any AFM based tool. And measuring the bending of this cantilever using beam bounds mostly, but there are other methods as well. And then second important component is basically detecting this bending of this cantilever using position sensitive detectors. So sometimes we use quadrant detectors where you have 4 tiny detectors sitting together. So beam position on that will decide the position of the cantilever, or sometimes you use simpler detectors like split photodiode. And then what's important is the piezoelectric scanner, because you are interested in imaging. So the height information is coming from the cantilever tip, but then lateral resolution or the lateral, you have to really move this tip everywhere, right? So how fast you move, what is the resolution is dictated by these piezoelectric scanners, or simply piezos. So piezos dictate the XY resolution, and then cantilever along with the tip properties dictate the height resolution. Okay, this is very, very important. Of course, all these hardware components connected to each other. Sometimes there are feedback loops depending on communication between the tip, sample interaction with the piezo, where it is, and etc. Of course, computers are central to that. Okay, so this is how a commercial AFM looks like. Okay, one of the makes, and very often you see that these kind of AFMs are put in either acoustic free, noise free rooms themselves. So sometimes rooms are made for that. Or if you can't really afford the room, you can have enclosure, which can cover the entire instrument in that, so that it's free from the acoustic noise. This is very, 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 very important if you're imaging samples in air, where it's very easy for the sound waves to propagate and then damage your cantilever response in that. So now I'll show some of the examples. This is a beautiful example I liked, that directly, this is an EFM image of HOPZ, or just basically graphite. You can really see without even additional analysis, this is basically the surface height profile. Okay, so white means the highest point and black means the lowest point. That's the height band. And then shows that now you can see the hexagonal comb, right? So, and each hexagon is basically consisting of 6 carbons, so beautifully. And imagine now the carbon-carbon bond is about 1.5 or 1.3 angstroms. So you can really beautifully see individual carbons, okay, at the edge of this. That's the beauty of AFM. So now that's at the almost atomic resolution, right? Now I'm showing one example where hundreds of nanometers, means like about 1,000 angstroms. Okay, so this is a beautiful example of a double-stranded circular DNA called plasmids. And then these are now crumpled together to show this kind of shapes. So what's important is that the scale bar here, okay, it's about 100 nanometer. Now imagine if I put a fluorophore onto this double-stranded DNA and then try to use traditional optical microscopy, you see the entire DNA or entire this plasmid molecule as a single blob. Now you see the richness of the conformational heterogeneity, so these are shown here like 8 molecules. All 8 are different from each other in terms of, so their complexity in this crumpled organization, right? Not only that, here actually you see the pointed arrows are showing something branching. It's basically double-stranded DNA stitched together somehow that it shows really X-like branching. That branching you can really isolate and then pinpoint in this. That's the beauty of simply imaging these molecules using AFM. So in this case, interestingly, the DNA can be imaged both in air and then in liquid. Okay, so because that's biologically important, you can keep these molecules in buffered conditions, and then you can actually see this. That's the beauty of this. And of course, everyone knows about SARS-CoV. Okay, so this SARS-CoV-2 virus or the virion has interesting coat of spike proteins on the surface of the virion, right? And then these spike proteins, of course, if you zoom in, they form a trimeric architecture. So AFM has been used here. These are real AFM images showing that A shows the cartoon way of just imaging. P shows that each circular thing is actually one virion. Okay, one virion. And then C shows basically two variants, how the height profile. You can actually really see about a 50 nanometers. So it's about 100 nanometer sized particles. Clearly, you can see individual thing. And D shows one variant where actually its surface is actually damaged. So it's basically kind of collapsed variant. And the other images here, E1, E2, E3, shows that really each spike protein, within that you can see triangular kind of shapes here, means the trimeric nature of this. So this is a direct visualization of SARS-CoV-2 virion particles, where you can really appreciate that looking at the this. Okay, not only just imaging, okay, which is important just to visualize how the sample looks like, but you can actually do much more than that using atomic force microscopy. So in this case, what they are doing is that the same virion particle, you know that there is a spike protein. The spike protein interacts with what is called receptor binding domain. Okay, on RBD of the spike protein interacts with what is called ACE2 receptor domain. Okay, so this interaction itself, you can actually measure how strong is this the binding. Okay, and here you can see at the bottom right, showing that you can really mimic these experiments in vitro and then use AFM to measure how strongly the receptor binding domain interacts with the ACE receptor. You can actually do what are called unbinding experiments by pulling away RBD against ACE2 receptor. Okay, these kind of experiments can be really planned. These are very sophisticated, take a lot of effort, not only from the sample preparation, but AFM can be used to measure these interactions. So this is another example I always like to show is that you can really track chemical and biological reactions, okay, using AFM as a tool to understand variety of things. So in this experiment where actually they are showing is that so A beta is a 40 amino acid peptide and A beta 42 is a 42 amino acid peptide, which are known to form aggregates and which are important in enzymes. Okay, so here actually they are tracking the aggregation profile over time and then directly imaging. Okay, so whether the molecules form aggregates, if they form aggregates, how large are the aggregates, what is the profile of these aggregates, and then when do they form filaments. Okay, if they are filaments, what is roughly the shape? Can really see over the course of 30 minutes to about a day, 24 hours, you can really see how the different steps can be really monitored in a kinetic fashion using AFM by looking at directly these kind of things. Okay, that's the importance of this. So this is another beautiful picture. There's a very simple polymer molecule in certain solvent forms nice brush-like structures. Okay, so using AFM, you can really see that how these polymers behave in different solutions. Okay, and you can actually see these kind of images, and then you can actually see that how they even interact with each other. Okay, so do they form crumple structure or do they form certain architecture shown here? This is another example in semiconductor science where you can see that it's a kind of nanoscience, right? Where people are interested in making tiny circuits at a few atoms level or nanometer scale level by bridging different components. So in this case, actually interesting what they're studying is that, so what is shown with the arrow on both A and B is a very tiny gold nano wire is there. Okay, so this is a very thin gold wire. Okay, you can see even small tiny blobs of more atoms there. Okay, and how that can be used in this circuit diagram. So the left is I think it is FCS, scanning electron microscopy image, and the same circuit on the right side imaged by atomic force microscopy. You can really see that gold nano wire. Okay, so you can actually measure the properties of this using AFM profiling before and after the experiment, you know, if there are changes in the wire conditions and things like that. Okay, so while AFM is a beautiful technique, so what's very important is the AFM cantilever tip. So as I have shown many different tips, and then their applications are in different branches of science and various reasons. But then if you use the wrong tip, then you won't get the right information. Okay. So here I want to highlight on the left side you have a very large tip, which is not really sharp, means that it's not going to give you high resolution. But let's say if you have a sample shown as a blue half sphere obstacle here, and then if you use AFM tip to move around this, what shape you get as an AFM image is shown on the right side. Okay, so you get much larger size than the obstacle itself because your profiler is not sharp enough to give you higher resolution. Okay, this is we call an artifact. So one has to really keep in mind what's the sample underneath one is going to use AFM imaging, and then what probes should be ideal for that. Okay, on the right side, it's exactly the opposite. You have very sharp tip, there's no doubt about it. But your sample has a shape of very funny, you have very deep well, okay? But the tip is not able to reach the bottom of the well. But then if you use this raster scanning method, using this principle, what you get the shape out of this, or the topography shown on the right side, you get a V-shaped well, okay? But that's not the truth. So this is one example we are going to show in the afternoon, where we image a DVD disc, okay, which you store for information in data. But then what are the nanoscale features, so how actually they make these discs, and then how the information is actually stored there. We'll show you that by AFM imaging. And then maybe in that, if time permits, we'll show that if you don't use these certain conditions, you will not get the right information. This is called manipulation. So AFM not only for imaging, but you can actually use for manipulating molecules. Okay, what do I mean by manipulation? Okay, so this is the example I'm showing is the surface of what is called purple membrane. So the membrane has a lot of protein, which forms almost like crystalline structures because it's densely populated with membrane. Now you can actually image and then see that how these molecules are embedded in certain shapes. Here again, it's kind of hexagonal Coulomb lattice. But then you can image, and then you can actually pull out one of those molecules from the membrane. Okay, what is shown on the left is before manipulation, and then now using the AFM tip, you push hard enough that it sticks to the molecule. But if you pull the tip away, now the molecule is actually pulled out of this membrane. And then you measure later and then see that there is a hole created there. So this is, one of the ways you can really manipulate. Okay. And afternoon, we are going to show some examples, imaging, to show that some calibrated samples and DVD for imaging to show really at the nanometer or even sub-nanometer level. Amazing. Okay, my students have actually worked hard to put these experiments together. And another aspect which we want to really show, what is called dynamic force spectroscopy. Okay, so what is dynamic force spectroscopy? So it's not an imaging spectroscopy, but it's a force spectroscopy which uses the principle of atomic force microscopy. But it's a molecular manipulation too, where you use the principle of applying forces and then see that how these molecules actually respond to the applied forces, and then measure the mechano response. So this is a schematic, shows that we are going to show you a molecule called big polymer of a protein molecule, which literally you can actually hold between the cantilever tip and the surface. And then you can actually apply forces, and these forces can be measured using cantilevers. And then how, if the force is high enough, what happens to these molecules, which we are going to show. So in the dynamic force spectroscopy, unlike you do the raster scanning, you just sit at one point and then you do what's called push and then pull, okay, or approach and retract, push and pull, and actually measure the properties of the either surface underneath or the molecules which are attached between the tip and the surface. So let's say in this cartoon diagram shown that ABC is basically approach. So A is far away sample. B is when it's very close to the sample, where there's attractive forces jumped onto the contact, called set point. I'll explain this in the afternoon, what is set point. And then if you push further, now the sample, the tip is in contact with sample. Now you do exactly the opposite, retract or pulling away. So if you pull that, now Sometimes this profile is retraced, and then finally, if the pulling force is much higher than the attraction, then the tip is going far away from this sample, and then this profile can be used to measure the underlying surface properties. Okay, so approach, retraction, I don't want to go into details. Applications. Okay, so this DFS has applications in many different ways. One of the simplest ways people have used this is for unfolding of proteins, which is what we are going to demonstrate in the afternoon. And then you can actually image biomolecules and then force measurements in variety of solvents, things like that. And you can do antibody-antigen interactions, like I have shown in the case of SARS-CoV-2 surface protein receptor binding domain versus the ACE2 receptor, or any other protein ligand complexes can be used to measure this binding and binding kinetics. And you can use, I'll show maybe this example. You can use as simple as, let's say if you have a simple double-stranded DNA, you want to really measure, let's say if I hold two strands against each other, if I just pull them away from each other, so can I measure the hydrogen bonding interaction between these two strands which are keeping together, or the base pair interactions which are keeping together? Can I measure how much force does it require? Does it depend on the size of the DNA strand? Okay, meaning let's say if I have 20 base pairs versus 40 base pairs versus let's say 100 base pairs, can the force required to detach one from the other, does it scale up? That's exactly what is shown in this paper. On the graph bottom right side, you see force versus velocity. So depending on three different DNA fragments, one is 30 base pairs, 20 and 10, more or less they're actually scaling up. Okay, these are the kind of interaction studies one can actually subject to atomic force microscopy experiments. So this is the receptor protein interactions where you can attach a ligand using chemical functionalization to the AFM cantilever tip, and then a receptor onto the surface, immobilize. Now you can actually bring these two in contact with each other and then measure what are the forces required, because these kind of experiments in a way mimic in the real biological conditions where this might be happening. Sometimes, let's say if you have receptor on one cell and ligand on the other cell, the cells are coming in contact with each other, and there is a receptor ligand binding. But when cells are going far away from each other, this receptor ligand interaction is broken under the influence of stretching force. So you can actually mimic that in real experiments. So you can actually combine sometimes AFM experiments with optical microscopy. In this case, where they coated, I think, AFM cantilever tip with some fluorescent molecules, and then they studied the interactions of that ligand with some receptor on the surface. But then after repeated measurements, because these are really prone to high force, so molecules can detach, So then they are actually trying to understand the probe which is coated with a fluorescent molecule. Can it really stay how many cycles, Can I repeatedly do thousands and millions of times? Do they really molecules still stick to each other or not? Okay, this is a very interesting kind of thing. So this is a beautiful manipulation technique where you can really take out a protein which is embedded well in a membrane. But now you can really pull out that membrane protein, helix by helix in this case, and then measure, it's even refolding pathway. So now you completely stretch out, but don't really pull out completely. But if you go back, can it really fold? If it folds back, can it have the same shape? How long does it take? These kind of experiments can be really done. So maybe I don't want to go.
Koti, we can
maybe
stop
I'll stop
for questions.
I'll stop this. Okay, so afternoon we are going to demonstrate actually two experiments. Let me go there. So we're going to show AFM imaging because it's really meant for sub-nanometer resolution, right? So this is a gold standard experiment in AFM imaging, okay? So if you take a mica surface, which is really flat, unmodified, if your AFM is really good, you should be able to get the roughness, okay, up to the level of sub-nanometer or a few angstroms, which we are going to demonstrate. Second experiment which we are going to demonstrate in the afternoon is that how to really get, let's say, few nanometer level information. So it's a beautiful experiment which we can really do. It's a surface of a DVD surface, so it has very corrugated surface, which has well-defined grooves, heights, and etc., which we are going to show. And also maybe if time permits, we'll show that how AFM can actually give artifacts. One needs to be very careful using the same example. And then, of course, protein pooling experiments, so DFS experiments. So with that, yeah, I'd like to thank. So afternoon, I have volunteers from the lab, Rakesh, Kaushik, and Aditya. They put a lot of time together in refining experiments yesterday. So hopefully we'll have a fruitful time in the afternoon. Okay. And I'd like to thank Satya as well for keeping it. Thank you, Jay.
Thank you. Thank you, Koti. That was fantastic. Lots of information, very exciting stuff. And it's very difficult to, of course, as a teacher to condense everything, but you did a fantastic job. Thank you, Koti. Questions are already up in the chat. I'm going to read few of them to you, Koti.
Yep.
So here is the first question from Abhijit, IIT Indore. He
Okay.
says, how we can determine which mode we have to use for our sample imaging, such as tapping or NCM or non-contact or contact?
Yeah, so this is a great question, as I alluded briefly in the talk. Okay, so first of all, you need to know the properties of the sample. Is it broadly classification in air, dry samples, or the samples in liquid? So if it is in samples in liquid, okay, so you prefer non-contact mode because mostly these might be soft samples. But if sample is in air, most probably it's a very rigid sample, then you can actually go for contact mode. This is a brief classification, but you need to have a little bit more information about the sample, then only we can actually judge, otherwise, very simple principle is that if your sample has a soft material, which you believe that by applying nanometer or nanonewton level forces damages, then you don't want to go this. You can go intermittent tapping mode. But always best is that use the softest way of doing measurement, and then your sample is rigid enough, then you go next level. And then if sample is really rigid enough, then you can go continue. But all AFMs these days, commercial AFMs, these can be implemented right away. But begin with the softest sample mode. JD?
Okay. So then the next question is, how many times one AFM tip can be used?
So that's again actually great question. So the AFM tips can be used as long as they are, giving
not compromised. As long as they're not compromised.
As long as they are not damaged. So very often the damage is basically the cantilever, as I've shown, for example, like if it is a triangular one, very often one of the leg is broken. If one of the leg is broken, you can't really use. And even if the single beam ones, of course, if they're broken, you can't use. But in principle, you can use AFM cantilever tips as long as they are there. But I would advise that each time calibrate, because sometimes the properties might be modified if you use them prolonged way. Okay, so sometimes we have used tips for days and months. Okay, but sometimes we threw the tip within half an hour.
Yeah. Okay. So then the question is from Shoham Mukherjee, IIT Madras. How to identify artifacts in an AFM imaging?
Very good, very good. This is a great question. It's not always easy to actually identify, let me tell you. But there are tricks to really make sure that at least reduce, the probability of artifacts is that one of the best ways is that you image a sample, you get that image. You don't know whether that image is right or not. So you just tilt the image by a few degrees, okay, 45, 60 degrees, and then image again. So, so then the resultant image is exactly rotated by that much amount. It's very likely there are no artifacts. Okay, that's one of the ways to really show. Because when you do, especially the contact imaging, artifacts are very common because sometimes you have these shadows, or sometimes the tip is actually pulling the material. It's really cleaning the surface, rather than giving the true topography. So one of the ways is that I always advise rotating this. This is one of the ways. But another way is to reduce the artifacts is that I'm going to demonstrate this in the afternoon. Okay, so you need to know what information you are interested in. Are you interested in angstrom level, nanometer level, or hundreds of nanometer level? Okay. So then sometimes, so that information is not really fed in properly. Then, for example, like what is the scale onto which you want to image? Let's say if you have features at the nanometer level, but if you image coarse imaging, then you are going to lose that. Okay, so this is one I'm going to demonstrate using DVD disk, that if you don't have the right velocity, right pixel amount, you won't get the right information. Yeah, but it's, I would say we can only minimize, but this, we always have to be skeptical that some artifacts might be going in. Yeah.
Okay, Koti, thank you. This is very nice. Next question is from Advait from IIT Bombay. What is the interaction between the tip and the material? How do you describe the interaction theoretically? As a corollary, since we are working on the scale of atoms, how do you define a contact?
Yeah, that's a very interesting question. So this is where that interatomic potential graph, which I have shown. So very far away, zero force, and then close to the surface, attractive, but very close to the surface, repulsive. Okay, in general, we use what's called Lennard-Jones potential, right? So these are the ideal two atom interaction kind of thing. Can be very used, okay? So if you're working at the level of atoms, and then your tip is really sharp enough, okay? So we are talking about really non-bonded, van der Waals kind of interactions. So then this atomic potential is really good and replicates the system under this. But if you have more than that, if there is a very specific interaction, like receptor ligand interactions, so then it would not be very easy to come up with a simpler theoretical model, because sometimes if the surface of the receptor, surface of the ligand is really large enough, then you have multiple minima. The simplest interatomic potential has just one minimum. But now if you have larger surfaces, two surfaces interacting, you can have multiple minima. Okay. So the simpler is, I would say, very close to Lennard-Jones like potential for atomic systems.
Okay. Koti, next question is from Sarita Puri, Aizer Pune. She says that, hi, nice talk. Can AFM distinguish protein oligomers of different sizes and uneven population distribution within one sample?
Within one sample. Okay. So this is again a very interesting question. Okay. So let's say if you are doing imaging. Okay. So heterogeneity is a very common, especially for the biological systems. And it's very routine for protein aggregation or oligomerization. Okay. So the question is that, so as you have seen in the examples, using AFM, you are going to look at any point of time, maybe a micron by micron, or at most 100 micron by 100 micron. Okay, now question is that how many of those samples you can really replicate over a size of, I don't know, even by centimeter sample. Okay, so the more places you image, the more heterogeneity you can really pick it up. Can the AFM really distinguish between different types of oligomers? In certain cases, it's possible. For example, let's say if you have oligomer sizes differing by an order of magnitude in terms of size, it's very easy. For example, let's say one is 10 nanometer, it is 100 nanometer, which can be distinguished very easily. But if one is, let's say, sometimes monomer versus dimer, you will not be able to see because the sizes are not going to be an order of magnitude. So where you have to really either image to get good statistics, either you have to really image multiple samples or multiple locations on the same sample. But it is possible if your sample really permits, if you have enough locations to really probe, it's possible that AFM can really give you amount of heterogeneity and then other properties as well. It's possible.
Okay, next question I'm not taking because somebody has named themselves as Just, so I don't know what that means.
Okay.
The next question is from Ronak. Can AFM technique be used to detect bilayer changes in vesicles?
Can AFM technique be used to detect bilayer changes in? Vesicles.
Vesicles.
So this is again interesting question. Okay. For example, like people have measured, including Professor Sudipta Maiti, is that you can actually make bilayers with different types of lipids. The lipid height is different. So you can actually, in principle, measure two membranes which differ in thickness of the order of few angstroms. So one is really thick, another is thin. You can actually measure these differences. But you're asking me on the vesicle itself. Okay. So unless you can really make that circular spherical vesicle into, let's say, two bilayer membrane, okay, supported bilayer membrane, I would not think it would be very easy to measure. But if you can mimic that vesicle surface by making a monolayer on, for example, let's say on a mica or glass, so then if you believe that you have different types of domains where one is thicker and another is thinner, you can really measure these properties, and AFM is really the ideal tool because you can measure tiny islands, even if it is few nanometer islands, which are thick, or few nanometer islands which are thin. You can really measure this very easily using AFM.
Okay. The last question is by Nikita Mahajan. Which substrate is suitable for a better scanning and imaging? Glass, mica, or silicon?
So this is again good question. I would recommend mica is the best. The reason is very simple. So it is because we know the mica structure, it is layered structure. You can really peel a fresh surface, which is unoxidized, and then you can put your sample and then image if it is possible. But sometimes mica is not really possible. And then I would say you go for silicon wafer. Again, it has atomic resolution. And if you go for glass, glass is not really flat, not atomically flat at the nanometer or sub-nanometer level. So if you are interested in basically high topography image, I would say begin with mica, then go to silica, and then go to glass.
Okay, Koti, thank you very much. And there are actually there's still 2 minutes remaining before I bring in Arindam.
Okay.
Just quick questions. Can we observe the nanoparticle attached to organelle of cells using AFM? From Gaurav.
Yeah, can we observe the nanoparticle attached to organelle of cells? Okay, so if Gaurav means that if the organelles are inside the cell, then I don't think we can, because AFM is a inherently surface probing tool. So if the nanoparticle is attached to the surface of the cell, maybe one can think of doing that. But then it's not going to be easy in experiment. But if the organelle is inside the cell, I would say it's not really possible. Okay, nanoparticle. But again, nanoparticle size is important. If it is like hundreds of nanometers, then it's easier. But if it is tens of nanometers, I would say it would be very difficult. Okay, but if it is larger, because people use micron size beads, on eukaryotic cells, which can be measured very easily. But if the beads are becoming nanoparticles, smaller, they are difficult, but medium size is easy.
Thank you, Koti. Ganesh and Devayani, please join the parallel tracks that are going to start after 4 p.m. in Koti's AFM part. Please join there and you can get your answers to the two very nice questions you have directly. You can start, Koti, you can start by taking their questions. Okay?
Yeah. Okay.
So now I'll bring, thank you, Koti, once again. Let's have a big round of applause for Koti.
Yeah. Thank you all. Looking forward to 4 to 6
yes.
sessions. Okay.
Yes, absolutely.
Hello, Arindam. How are you?
Hi, Koti.
Nice
How
to
are
see
you?
you.
Fine, fine. Good to see you.
Nice to see you. Okay.
Okay, thank you. So next we have Professor Arindam Chowdhury from IIT Bombay, who is an expert in imaging, and he will talk about single molecule methods to look at how to use fluorescence and microscopes and spectroscopy to look at single molecules. So Arindam, over to you.
So I have a control over the shared.
Can you share it?
Screen, right? Yeah. So this is a very looks like it's a heterogeneous crowd here. So I was thinking about how to. Yeah, can you see me? Can you?
Yeah, but full screen, Arindam. We need full screen.
I'll do that. I'll do that.
Okay.
I mean, I have a problem with this full screen to do. Yeah, now it seems to be fine. Is it okay?
Yes.
All right. So the students can't ask questions directly, or can't they talk directly here?
Yeah, they can, but only after 45 minutes once you're finished. So we don't want any.
So the reason I was going to say that is, if there is some problem in between, then we can, if somebody has questions, they can stop me actually, because I've kind of kept it an open-ended thing a little bit, because I was not fully sure how much I will be able to cover. It can spill over, so that's
Yes,
why I have,
you can ask
you
a
know.
pop quiz in between and they can respond.
No, it's generally, it's better if we interact. All right, so
Fine, let's start.
thanks, JD. Thank you, everybody else for coming. Is it working? So I'm going to talk about looking at single molecules or single emitters, all right, and how we can image them, how we can collect spectral information from them, and how you can observe some dynamics from these species. And the main question that I would like to focus for this 1 hour session here is going to be why, how, and what you can do with it. Okay. The details of my presentation, I will share it with people if they want to, and for those people who are going to join in the focus session afterwards, I will share a link with you guys with more information, so you can read up before coming to IIT Bombay in November. All right. Okay. Now, the thing that I would like to focus on, and I've been focusing on, is trying to understand complex systems. And complex systems essentially most often lack uniformity in physical characteristics. And it can be physical or it can be dynamic characteristics, in fact. And this is an example that I show here, pointer options, of a part of a cell, and you can see there's this outside of a cell, there's some cell wall, and then there's some cell membrane, and the cell membrane contains a lot of different kinds of things. Inside the cytosol is just not plain liquid. There are pools and there are islands, there are DNA, there's, what is this? I'm sorry, I'm seeing something here. Jyotishman, can you broadcast or close all rooms? Shall I broadcast it? Okay, I broadcast it. Nothing's happening. Okay, I'll just cross it out.
No. Yeah, Prashant is fine. I think you just close this one, I think.
I just
Close
did.
all.
I just did. I just did.
Yeah.
Something popped up, so I just closed it.
Yeah, just close it.
And there's a lot of proteins and lipids and other things which are interacting with each other. So you can see that at any given point in space and time, there's going to be differences if you go along, from one point in space and time to another point in space and time. And that's really what I mean by inhomogeneity or, heterogeneity. And this behavior, can essentially be broadly classified into two parts. One, we can talk about a spatial heterogeneity, which essentially is also termed as static heterogeneity, or it can be dynamic in nature, something that changes with time, and we want to probe that information. Now, to probe it, as you can see, that if I get information from this entire cell, I will not be able to get this information. So I need to essentially probe sub-ensembles. So I need to probe some subparts of this, and maybe over certain time scales and over certain length scales. All right. So that's the basic idea. And that's really the reason why we want to do microscopy in the first place. Okay. Now, standard fluorescent probes that you typically work with, you take a cuvette, do a measurement, form some dye or something else. This works great in terms of the local environment around that probe when the solution is homogeneous. But when it comes to heterogeneous systems, then you can see that depending on the location of the probe or the probes, the response is going to be different. So as a result, if you're probing a heterogeneous system, you essentially are going to obtain some sort of a spatially averaged information from the system. And just to give you an example of that imagine that you are obtaining some sort of a fluorescence lifetime, okay? And from a system which is perhaps heterogeneous. And you get a response function of that fluorescence lifetime, which looks like this. And let's assume that the y-axis is a logarithmic scale. Now, if it's a logarithmic scale, your first response can be, oh my God, this looks like it's a non-exponential function. So there must be multiple processes that are going on simultaneously and with different time constants, right? But it can very well be that if there is a heterogeneous system, there are different subcompartments that is shown over here on top left, where the responses are individually, they are single exponentials, but with different time constants as you go from one place to the other. As a result, when you collect data from this entire region, you end up getting a non-exponential decay. So you have a room for misinterpretation. This idea is called static heterogeneity. Of course, it can very well be that for every part of the system, as shown over here in the bottom left, the responses are indeed non-exponential. That very well may be, but you do not know. You cannot tell the difference without actually probing these individual compartments that are shown on here on the left. Now, what applies to space here exactly applies to time as well, because it very well happen that you are going to see the response of function at one point of time from the same region be different from the response at another point of time. Maybe that's because of some changes that has happened, dynamical changes that has happened. And this again is referred to as dynamic heterogeneity, because here it's not about space, but about time. Let me give you another example. This is a situation, for instance, you collect an emission spectra, and the emission spectra looks like this, what is shown here in B, and it has got two humps in it. And you may speculate that many, many things are happening. Maybe there are some vibronic features. Maybe there are, two different species or two tautomers or two species have been formed. And this result is essentially coming from an ensemble measurement. But if you go down to sub-ensembles, and that is represented here using these dotted dashed hexagons here, and I've just shown 4 of them. And imagine that this system contains these different colored species, right? These balls, and there are different molecules or different something else, which is giving the spectral response. And as you can see that as you make these hexagons smaller and smaller, you end up getting different responses, because you may have either orange or some orange and some green, and or some pink and some blue and some green, or some blue and some green combinations in these different sub-ensembles. Now, the single molecule idea is essentially the ultimate sub-ensemble, where you say that, okay, my ultimate sub-ensemble is the single molecule, and I would like to get the information from individual molecules. And if you do so, you may end up getting spectral features which look something like this, the sum of which would end up getting in the ensemble. The same thing can be applied in dynamical systems as well. Now, what's the advantage here? The advantage of these measurements is that once you have obtained information or collect data from single molecules or sub-ensembles or ultimate sub-ensembles, which is a single molecule or single nanocrystals, and if you do so for a large number of molecules or species, then you can construct some distribution of physical parameters. And that's just shown here with its orange, green, blue, and pink on the right-hand side. And these distributions refer to the distributions of the properties that you're trying to measure. And the distribution, the mean of the distribution is typically what you would obtain in an ensemble resolution measurement. But here we have the advantage that we can also know about the width of the distribution. And this width of this distribution is actually related to the extent of heterogeneity in the system. So in essence, what I'm trying to say here is that if you want to know about the system in detail, about how the physical properties vary and to what extent, you need to create these distributions. And single molecule spectroscopy offers a way to do so. Now, what are the advantages? Of course, as I mentioned, we can obtain information of the properties, variation of properties in space and time. That's what I mentioned about heterogeneity. But more than that, once we have these distributions that are shown here on the right, you see the tails of these distributions are often referred to as rare events, okay? So these rare events are obscured in the bulk. You will not be able to measure them. And often rare events can be very important. Especially in biological processes, there can be rare events, which are important events, which may result in a particular reaction or a process, and some downstream event can lead to a really bad thing that's happening in the system, right? So, it's identifying these rare events is also an important process. And further, we can obtain information on mechanisms and as well as discover new phenomena. Now, let me give you a very quick example of what I mean by on insights on mechanisms that you cannot obtain from ensemble measurements. So imagine you have a very long DNA and you have some protein which is looking for a target. And this target may be of various kinds. It can be a promoter region where the protein is supposed to bind to this DNA and the gene expression will start. Or it can be a mismatch which this protein is going to try to repair, or it can simply be some protein which is going trying to cut the DNA at a specific location, okay? And it's not going to do so in any other region. Question is, how does this protein come and identify this target? This is a very classic target search problem. These kind of problems are very, very difficult, basically impossible to find out the result of using ensemble measurements, because there can be multitudes of processes that can be involved in this target search. For instance, you can have direct association to the DNA followed by either passive diffusion, or it can be some, if it's a motor protein, maybe it uses ATP and it undergoes translocation in one direction, or it can undergo some sort of a transfer, intersegment transfer from one DNA section to another. I mean, how would you differentiate these things? Are these proteins hopping from one point to another? Is it forming a sliding clamp? These kind of questions are very difficult to obtain from classical or ensemble measurements. Single molecule measurements offer a way to do so. Another example, this is more on materials and spectroscopy, is let's say you have quantum dots. And this particular example I've chosen here is of a doped quantum dot, where this nanocrystal is basically a small ball of nanocrystal of few thousand atoms, contains a few atoms of another species, okay? And this species happens to be manganese here. And the idea is that once you excite the system, and then the system can actually undergo energy transfer from the conduction band, the system goes to the manganese excited states, and this emission can happen via the manganese ion. Now, because it's like an atomic emission, you would expect this emission to be narrow. But in fact, in the literature, the vast literature is available, people have shown that there is a very broad emission that is observed for this manganese, okay, in these doped systems. Now, what is giving rise to this kind of ensemble spectra, which is very broad in contrast to what we may observe? There can be, for instance, different possibilities. Like, I can have situations from the left here that you have inherently a broad emission spectra for whatever reasons. And their peak positions are somewhat similar, only kind of determined by the size of the nanocrystal, because the size of the nanocrystal will alter the spectral peak positions. Or it can be possible that you have a narrow spectra that's coming from individual nanocrystals, but when you average it over an ensemble of nanocrystals, you end up getting a broad spectra because their peak positions for individual nanocrystals are very different. So how would you find this kind of information from an ensemble measurement? It's rather challenging. And again, if you do spectroscopy on individual nanocrystals one at a time, then you end up, you will be able actually to provide an answer. Maybe I will, if I have the time at the end, I will try to touch upon this. All right, so now let's go back to something that most of us love to see, the stars in the night, and especially if it's a picture that is taken by a high-end, ground-based telescope, so not the Hubble one, which shows mostly galaxies. And this picture here shows spots, and each spot's probably going to be a star, right? And you have seen this kind of picture. I'm sure you guys have seen this kind of picture before. But if you look at this picture, you will see a lot of basically a dark background. And in this dark background, you see the spots, which are symmetric spots, spherical or circular looking spots, a lot of them. But if you actually go and look carefully into it, and especially if you look at this top left region that is there over here, or the bottom left region, which I show over here, and I've just blown it up for you, you see that you start seeing, you can't really distinguish whether in this bottom, right corner, whether we have like got 2 stars or 3 stars in that spot, or that's a single star, right? And especially but the stars are coming, the stars are basically like point objects because they're so far away, even through the telescope. So you can't really resolve them. You can't see the shape of them. We can't tell what their sizes are from this picture. All the spots will essentially be of the same size if I take a profile, if I take a cross-section profile of the full width of half maximum. And on the top left here, you can see that it's very difficult for me or anybody for that matter, to distinguish an individual spot or an individual star, right? Because it seems that they are very close to each other. And because they are close to each other, you can't distinguish it. So the resolution of this microscope, or this telescope rather, is basically not good enough to resolve them, right? And this is essentially determined by what the microscope is called a point spread function, but essentially the diffraction of light. Because if you have a point object, and from that point object, if light is emanating from a point object, it's going to spread out. And it's going to spread out in a certain way. It's going to happen in a telescope. It's going to happen in a microscope, all right? So you essentially cannot resolve this point that is shown in green, whack in the middle. That's the point from which light is coming out. But the light that you observe is actually way bigger than the object, or the point object itself, all right? And this is really the point. This spread of this light, right, of this light that originates from a point, essentially is related to our very famous, well-known Abbe's limit of Abbe's limit of resolution, which is essentially says that if there are 2 objects which are beyond or below a certain distance, then you can't resolve them, right? And you can imagine that there are 2 different objects which will have some sort of a spread of the light, even though they're point objects. And if they are beyond a certain minimum distance, you can resolve them. If they're within a certain distance, you cannot resolve them, all right? And the same thing is essentially, you can see here on the lower right, that's a similar kind of a 2D version of it. If you look at what's shown here on the left, if you look at it from the top, you are going to see something like this, right? In some cases, you will be able to resolve. In some cases, you won't. And in case of the telescope picture that I showed you, in certain cases on the top left and the bottom right, you're unable to resolve because of these 2 objects being closer with respect to basically smaller than this d min. Now, going back to our systems of molecules, and I'm just going to give you a few examples here of molecules, all right? And this is on the left-hand side is rhodamine 6G. And then we have a cyanine dye. These are very well, very commonly used for microscopy. Then we can think of like a multimer of dyes, right? So 3 or 4 of the perylene dyes, which are attached to each other in a tetrahedral manner. This is an aggregate, but it's a covalent aggregate, all right? 4 dyes are coupled to each other. And these relative sizes are kind of comparable. Okay? Or you can think of a fluorescent protein, GFP. Lengthwise, maybe 3 nanometer, hydrodynamic radius, maybe 3.5 nanometers at most. And the chromophore is within it. It's much smaller. Very commonly used by biologists as well as chemists, or even a nanocrystal. This is actually, I've made it smaller because nanocrystals are most often, they are bigger. but in the range of few nanometers to few tens of nanometers. But for all these different kind of probes that people use, these fluorescent probes that people use in chemistry and in biology, if you look at one of them, just one of them, you would end up getting an image which would look something like this, all right? And these pixels that you see over here, each of these pixels are typically in the order of around 70, 80 to 100 nanometers, all right? So you can see that the species that we are talking about, these molecules, they are in the order of 1 nanometer to 10 nanometer, roughly, okay, in the order of nanometers. But the light that you're going to observe is actually spread out over a larger number of pixels, and it's in the order after magnification of this full width of this species that we have here is in the order of 250 to 300 nanometers, all right? So, so this is something that is important for us to understand because when we talk about single molecule fluorescence or visualizing single molecules, we actually do not refer to looking at the molecules themselves. We are essentially looking at the light that emanates or comes out of this molecule. So we are talking about fluorescent molecules, all right? Okay, so this is just a version that I've magnified the size of the molecule 10 times, at least 10 times, to show you, what the relative size of the molecule is as compared to the spot that we would normally see. Now, as a consequence of this, right, now on the left-hand side, you imagine, for the sake of argument, that these are the actual sizes of the molecules, all right? Or maybe it's magnified by 10 times. And they are placed reasonably close to each other, much smaller, of course, as compared to the minimum distance that is needed to resolve each individual species. In reality, when you try to image them or look at these species through a microscope, you are going to end up seeing the image that is shown here on the right. Everything is going to get blurred out. And this is basically a consequence of diffraction limit. And of course, in recently, 2022 or 23, the Nobel Prize was awarded for super resolution, where they did exactly the opposite thing. They basically said that we can break this diffraction barrier and you can end up getting, you can get down to the length scales or can resolve these molecules in the length scales of few nanometers or few tens of nanometers, all right? But that is the story that I can discuss some other day. All right. Now, you can imagine now that if I take these molecules that I have over here and somehow stretch them, I stretch them, they are all kept on some sort of a rubber band, two-dimensional rubber band, and I hold the four corners of this two-dimensional membrane, rubbery membrane, I start stretching them. That's the same thing as saying that, you are doing a dilution. You're lowering the concentration of the molecules per unit area that you are looking at. And if you do that, you are going to start seeing something like this. And even here, things are not fully clear, but you can sometimes see some spots which are pretty spherical or circular in nature. This is a colored image. We can talk about why it's colored later. That's not important right now. While there are a lot of times they're also clustered together, right? So sometimes they are clustered together, you can't resolve it, sometimes you can. And if you keep doing the exercise and you increase, again, you stretch it even further or lower the concentration, and essentially what you're doing is what I like to call homeopathy, right? You do dilution. The more dilution you do, the more effective homeopathy medicine becomes. And in our case, the more dilution that you do, more separated or more segregated each molecule becomes from each other. So if we can stretch that such that or do this homeopathy business in such a way that each molecule gets separated from each other beyond this d-min or the minimum distance for of Abbe's limit, then you will basically start seeing stark background with spots which are mostly spherical. Of course, there will be certain situations where molecules will not be very, very close to each other. And there will be certain situation where molecules will be close to each other, which you will not be able to resolve. but you really don't care too much about it because you say that, okay, I'm just going to reject the stuff that are too close to each other. And I'm only going to look at the molecules which are clean and nice and which are well separated, all right? So this is essentially the way single molecule spectroscopy has been done for immobilized. These molecules are not moving around, they are stuck, and that's one of the ways to do it. All right. Now, so far, I've shown you these images, but I have not talked to you about, how we get to do it. So as I told you that I'll discuss in this lecture about why, how, mostly, and maybe if time permits, then we can talk about, some applications, all right? But I don't think we will have the time. So what I'm going to do is, given that we have a lot of people from different backgrounds, I'm talking about the students, and many of you who are there right now maybe are in first or second year of PhD, and you may not work in fluorescence, or may not work with light, or didn't have prior exposure. I'm going to start with very, very basics, okay? So, and this, I'm going to assume that everybody here knows that, what fluorescence is about, right? I mean, you shine light on a system which has appropriate difference in energy between the ground and the excited states. And then you can, under certain situations, you can get light coming out of the system. And this is a spontaneous emission process. But what is most important for us to remember is that this green light that is coming out of the system has a difference of energy as compared to the blue light that is getting absorbed, all right? And this idea is called a Stokes shift. So this is something that I expect everybody here in the audience would know, because this is all undergraduate knowledge. And in the bottom, I just show you examples of, different colors of fluorescent solutions which emit different colors of light. And these are actually from quantum dots, which are all excited at one wavelength, but they emit different colors of light. All right. Now, those of you who have collected a single fluorescence spectroscopy spectra, or done a spectroscopy measurement, would know that the way to collect fluorescence spectra, is to essentially shine light on a sample or a chamber where the sample is, in the way that is shown over here through a monochromator, which I'll just call an optical filter, and collect the light at a perpendicular direction, right? This is standard. Why? Because fluorescence is actually quite feeble as compared to the amount of light that you are using to excite the sample. So if you look from this direction, you are going to be in trouble, because the detector will essentially get flooded with the excitation light. And so you don't want to do that. Fluorescence occurs in all directions. So you get the collected light in the perpendicular direction. Now, the problem with microscopy is that you typically want put a sample on a slide or a cover slip, which is shown over here, which is typically less than a couple of hundred microns, or less than 100 microns in thickness. And so doing this perpendicular arrangement is kind of difficult. So the way you do microscopy is essentially what is called in the reflection mode, okay? And this I will also refer to as the epi-fluorescence mode. In the epi, in the sense that when you shine light, you use a dichroic filter or a dichroic mirror, which reflects the blue light, and it excites the sample. And once it excites the sample gets excited over here, light comes out of the spot. The emission is now shown in green. This green light is collected by the same objective lens that is used to excite your sample. And now this light comes back, but instead of getting reflected, it passes straight through this dichroic mirror, because this dichroic mirror has a very special property. This dichroic mirror has a property that it allows a certain wavelength of light to pass through, while it reflects a certain wavelength of light. And that's why I told you that the Stokes shift is going to become important, because we know that the emission is actually Stokes shifted with respect to the absorption. And therefore, if you excite in a region of lower wavelength, higher energy, you can detect the emission using this dichroic mirror and some additional filters. You can detect it using a detector, and you can form an image. Okay, this is the basic idea of fluorescence spectroscopy. Now, the way you do an excitation can be twofold. And I'm sorry, but I'm going to spend a little bit of time on this, because I think many of our students and colleagues co-workers may not have a full idea about how image is formed. Now, one of them, which is very, very common, and I'm sure most of the places have this setup, is called the confocal microscopy setup. And it's also kind of falls under this epifluorescence because you do the same thing. You excite the system using a laser. But here, as you can see, that you have done some sort of a beam expansion, and then this collimated beam comes to the back of the objective and focuses itself, you get a focus at the point at the sample. That is kind of shown right over here. Now, under this situation, what happens is that in this focal volume, you have molecules that are there in the focal volume. They emit light. The objective collects the emission that originates from that focal volume. And it is eventually collected in some sort of a photodiode or a point detector. It collects all the light. And once it collects all the light, and after this emission that is being collected, you are rejecting the excitation light using the dichroic mirror and the filters, and it's coming through a point hole. I'm going to pinhole. I'm going to come to why we need a pinhole. Then you get some point, right? Now, the idea of scanning confocal microscopy is that you do a scanning. You go from one point to another point to another point to another point, and you keep moving, and you collect the emission that comes from different regions in space, and you reconstruct the image, okay? And that's how you get a profile of the intensity profile of the entire area that you're mapping out. The other way to do it is wide field illumination, and the wide field illumination essentially involves focusing the laser to the back focal plane of the objective, and that way you get a collimated beam that comes out of the sample, and you illuminate a pretty large area. This large area can be controlled. It can be anywhere between few tens of microns or few microns to few tens or hundreds of microns. But the difference is that here you illuminate the entire region, so where you have many different kind of different molecules that are there, and you collect the emission directly. You don't need any pinhole. And instead of a point detector, you have a ray detector. So it's like a camera, like our eyes, like our cell phone cameras, and you basically take a snapshot. And in that snapshot, you are going to get the different intensities at the different pixels on the camera, and that will create the image. That is the basic idea. You still have the same resolution as average limit, which is 250 nanometer resolution. Now, this is something that I'm sure many of you have already seen or already have heard lectures on. In a confocal setup, if you have talking about not immobilized samples, but if you're talking about a solution, and if you have a confocal volume, which is basically about 1 femtoliter or so, and if you take a low concentration of dye molecules in solution, then what will happen as these dye molecules diffuse in this confocal volume, they will be increase in intensity that will be detected by the signal that will be detected by the detector. And this is something that has been exploited back in 1994 by Dick Zare and Shuminini, where they showed that if you have a simple system like this with rhodamin 6G in solution, you can essentially look at these bursts, right? These bursts of light. And this is something that Gillard talked about yesterday when he talked about single molecule FRET. And when you do FCS measurements, you are essentially looking at the same thing. You are going to generate autocorrelation and so on. So I'm not going to spend time on this because my focus here is to look at an individual molecule and sit on that individual molecule and look what's happening to the molecule as a function of time. That is really the objective of single molecule spectroscopy. All right, before we move on, we need to make one thing sure here that the fluorescent that we're talking about has to be strong. If you want to detect the fluorescent light from a single molecule, it has to be strong. So we essentially need to have a very high extinction coefficient at the point of laser excitation, and also a very high quantum yield, typically more than 0.5, which means that 50% of the rate is of non-radiative recombination process is smaller, is small compared to the radiative recombination process. Okay, so that's what we want. The other criteria that we have for the choice of the fluorophores, the excitation and emission should be in the visible region. We're going to come to that perhaps in a few moments. And it should be Stokes shifted with relatively narrow emission spectra. And finally, it has got to be photostable. if it undergoes photo-excited state reactions or excited state degradation, then those fluorophores are no good because it will not be able to cycle, go up and back and forth, up and down, ground to excited state to ground state with the emission of light many, many times. You want that to happen over few or tens of millions of times at least in order to detect, look at a molecule and look at it as a function of time. Okay, so if you actually look at a raw data, okay, of an image. Now, I've collected this image using either a confocal measurement or a wide field measurement. I don't care right now. You'll see that it's actually, if you look through the naked eye, you'll see it's extremely dim. The contrast is very, very poor. So what's it that determines the contrast? You know, and there's a perception that, oh, single molecule emission is so weak that, you know, that's the reason why we can't see it. That's not quite true. And if I explain to you in a moment, you'll understand why I'm saying this. Again, I'm going to go back to the night sky and astronomy, and even without astronomy, just the night sky. If you want to look at the stars, right, you know that the stars are there during the day. Even now, we have the stars. It's daytime right now. We just don't see them. We don't see them because there's too much of sunlight or too much of ambient light that is present in our skies. So compared to those scattered and unwanted light that we don't want to see, the light from the stars are very, very dim. Now, you see that as we go from a city sky, which is basically Mumbai, as you will see in November, and maybe to suburban regions, if you go to like Lonavala or Mahabaleshwar nearby, and then you go to deep interior Maharashtra, and then you move on to maybe, you know, get out of Maharashtra and go to Ladakh and go over there to a secluded region. You're going to essentially get an excellent dark, you know, sky, and then you will be able to see way, way, way more number of stars. So they're going to be way more dim, but you will still be able to see them. You'll be able to see the Milky Way very, very clearly, isn't it? Now, our eyes, fortunately, our eyes are excellent detectors. Our eyes can detect down to 4 to 5 photons it can detect, all right? So it's not about a detection problem. It is about this signal to background. So the main idea here is that if you want to enhance contrast and if you want to see the emission that comes out of single molecules, you need to reduce the background and you have to be very, very careful. You have to consider all the factors that contribute to the background and somehow get rid of the background signal and scattering, and then only you will be able to see single molecules. Now, the way the confocal microscopy or laser scanning confocal microscopy works, and I think I told you that I'll talk about the pinhole, is that this pinhole allows you to reject the light that comes from out of plane as well as the light that is coming from different regions, okay? And that is really the job of the pinhole. Of course, the smaller the pinhole, the better will be in terms of rejection of out of focus light or out of plane light. But that comes with a cost. And the cost is that the smaller the pinhole, the less light will come to the detector, even from the molecule. It will be more difficult for you to do that. And so we have to come to a compromise. And typically you use a few tens of microns size of pinholes to reject this out of plane light. This is one of the ways to reject the light that is unwanted, scattered and unwanted light to reach the detector. Another way, of course, there are many other ways. I'm not going to the details. I'm just giving an example of how people can do that. Another way to do so is using a method called a total internal reflection fluorescence microscopy. And in this method, people have known this for a long, long time, whereas I learned about it when I was doing my PhD, is that when you undergo total internal reflection of light, an evanescent wave is generated in the rarer medium. And in this evanescent wave, this is basically some sort of a standing wave, and the standing wave decays exponentially as you go away from the surface, okay, of the interface. And so what you can do is this wave that is generated, the standing wave that is generated, which is very intense near the interface, and it also has the wavelength, same wavelength as the wavelength of excitation light, right? This can be used to excite fluorophores, which are very close to the interface. So essentially, you reject or you do not excite the fluorophores that are there in solution. They're in the bulk medium. They don't contribute to the emission, and only the fluorophores very near the interface contribute to the fluorescence. All right. Now, this idea has been used, and the method that will use that is called total internal refraction fluorescence microscopy. This is another way to reject this out of focus light. Now, typical configurations for single molecule imaging are either confocal microscopy or scanning confocal microscopy with a pinhole. And often people have also rejected the pinhole and simply used the detector's diameter, because typically avalanche photodiodes that are used, they're very small in size. They are in the order of a couple of 100 microns or 100 microns or so. So if you can maximize the intensity there, it automatically takes care. It almost behaves like a pinhole. Of course, epifluorescence, where the light is, as I told you before, or it can be a turf or a total internal reflection fluorescence. I've given an example of what is called through the objective turf, because that's what we do in our lab. But you can also, for that matter, you can also use a prism on top of the sample here on a glass slide, and you can take the light from above, and you can also do a prism type turf. Okay, but I personally think like to do the objective type turf that gives you a better signal. Now, so far, everything is good. Now, what we have not thought about yet is that we need to immobilize the molecules. How do we do that? If we don't immobilize the molecules, they're going to fly around. We'll not be able to, just like they move around in the focal volume, right? They're going to fly around. So we need to kind of hold them at one place so that they do not move, right? That's an essential criteria to look at a molecule one at a time. We cannot allow them to move too far away. So there are various ways to do it. I don't want to get into the details. Simplest way to do it would be just throw them on a glass cover slip, which has been cleaned thoroughly to get rid of impurities, and then get rid of the solvent, and just look at the molecules that are there. Alternately, you can put this molecule, mix it in a polymer, and then you can spin cast a polymer on the surface, and this polymer provides you with a very, it's a high TG polymer, high glass transition temperature of a polymer. So it gives a very rigid environment, very viscous environment. It doesn't allow molecules to move around, so you can detect a molecule. For biomolecules,
Arindam,
yes.
Arindam,
Yeah.
it's 45 minutes now. So
It's,
maybe because you will get some questions also.
yes,
So
I know.
maybe you can conclude here and then you can take it off.
I was going to conclude here in 2-3 slides.
Okay,
So
fine, Arindam.
about, I mean, I was thinking of covering something else, but what I was thinking was kind of tell them that, what are the criteria to, detect, how do we still know it kind of thing. So maybe I need 3 more minutes, maybe.
3 minutes, okay, fine.
Okay.
And then we can take questions. Yeah.
My watch is for whatever reason is not going slow. So, I mean, I can do the rest of it later, I think, in the more specialized thing. So after doing all those things, right, you can end up getting images which look like this. This is on the left-hand side is a confocal image. And as I was telling you earlier about the raster scanning, you can see these lines. These are actually coming because the objective is moving, or the stage is moving in one direction at a time, and you're collecting the image. These are isolated single molecules. Well, at least I'm saying so. And the right-hand side is a TARF image of, again, rhodamin 6G molecules in a polymer. But this doesn't really do justice, because you really have to see the three-dimensional image here. So now you can actually get a better feel of the noise level that we are talking about and the signal that originates from these molecules. And again, so far, I have not proved to you that these are single molecules. These are just single spots. How do you know that these spots actually contain one molecule and one molecule only? How do you know that they don't have 2 or 3 molecules over there, right? There is no guarantee of those things. And for that, we need to do certain checks. And again, as I told you, in 1 hour, or 45 minutes, it's difficult to kind of manage everything. So I'm just tabulating it right now. of how to. First of all, we need to make sure that the spots are diffraction limited and the circular in nature as shown over here, you see. Because if my molecule, since my molecules is much smaller than my spot, I will always get a circular or spherical spot. And the second is that when I have a concentration depends on the emission spot. That means if I change my concentration, my number of spots per area should increase or decrease depending on how I have changed my concentration. The emissivity of each spot cannot be too bright, okay? They should be comparable, reasonably comparable. I mean, it's not too much different from each other. That's one criteria also. But most importantly, I think, what is the criteria is to know about this idea of a single-step or abrupt or discrete photo bleaching. And the molecule will die. The molecule dies in one shot. You see abrupt jump in the intensity back to the noise level, as well as what is called a single-step photo bleaching or photo blinking. It's again abrupt and discrete. Wahid talked about it in the lecture yesterday, so I'm sure you guys have seen it. Those are direct evidences of a single molecule, a photo, in existence of single molecules. And of course, the spectra of these molecules are also supposed to be much more narrow as compared, especially as compared to ensemble. And yes, we should see polarized emission if they are in immobilized conditions. And of course, there's a final and ultimate proof of single molecule detection is photon anti-bunching. Again, it's a little detailed method. I don't want to go into the detail, but we can talk about that. You guys can Google it up and find out what anti-bunching is. Now, since in the interest of time, I am going to skip my my slides. I kind of knew that this was going to happen because I was going to explain blinking, and photo bleaching. So I'm going to shift straight to the final slides that I had, which is kind of, well, pseudo summary, you might say, that what I showed you about the detection and imaging of single molecules, immobilized conditions or not, essentially has expanded over the last 30 years. This is going to be 30 years. It's more than 30 years now, over 30 years into a multitude of techniques that people have used. People have done imaging and collection of movies shown over here. You can do spectroscopy. You can do fluorescence lifetime imaging of single. You can track single molecules. You can do polarization resolved methods. You can do single molecule FRET, super resolution. You can also do FCS, which many of you are aware of. And you can apply these techniques to study polymers. You can look at catalysis. A lot of work is being done on biomolecular structure and dynamics, single molecule sensing. There's a lot of Photon correlation method measurements that are being done. Even DNA sequencing, and looking at properties of quantum dots. So you can see that it's really grown in diverse direction, in diverse direction. So with that, I'll just stop here and take questions. And maybe in the following section, I can start talking more for the focus group of people.
Yes.
I hope it's okay, Jyotishman, right?
Yes, perfectly. Thank you, Arindam. That was very nice. You had a night sky analogy, so that was very nice. Always good to see night sky at any point of time. Goes back to childhood days. Okay, so now we have at least we will take few questions. So there is one question in the chat box already. Ajay JNU from JNU is asking, what is the reason behind the spherical shape of the observation volume rather than an ellipsoidal one?
It is not a spherical shape of observation.
Yes.
The observation volume is actually not spherical shaped at all. It is actually an ellipsoid. Okay, you are absolutely right, Ajay. It is an ellipsoid. If you're going to be there in the breakout session, I can talk about it, but it is an ellipsoid.
Okay. Are there questions that people have? They can actually unmute themselves and ask directly to Arindam. Questions from students?
I don't know. Was I too technical?
No, it was fine. I actually, in the entire session, we did not talk about fluorescence spectroscopies, which you did. So thank you.
Oh, you didn't?
That.
Oh,
we didn't really talk about that in. It used to be GK taking care of that long back. in FCS.
I see.
Yeah.
I think somebody's asking a question.
Yes.
Uh,
Yes.
hello,
Yes.
hello, Arindam sir. It
Yes.
was a really nice talk. So
Thank
I
you.
am confused in one part that
Yes.
you said that it has to be immobilized, the
Yes.
fluorophore,
Yes.
like whichever we are observing.
Yes.
But when we are using a solution to perform single molecule experiments,
Yes.
like so it will move.
Yes.
Obviously, we are using picomolar concentration, so it has to be one at a time. But I'm a bit confused. If it is moving, how we are we
So
will
see,
manage
the
to.
idea. I'm sorry. What's your name?
My name is Paromita.
Hi, Paramita. Where are you from?
I am studying currently in my first year PhD in University of Bordeaux.
Okay, Paramita. Thanks for your question. So the idea is that you have a diffraction limit, right? The diffraction limit is, let's say, spot is like 250 nanometer, right? Now, if your molecule undergoes movement within 100 nanometer region or so, we have no problem. Like, for instance, if you think of this kind of a GUV, I think Gillard also at one point of time worked on this, right? You can have molecules. Can you see, Paramita? There's this DNA attached to
Yes,
donor,
yes.
acceptor, some protein is there, right? You can see that these guys can freely move inside this vesicle, right? There's no problem because the size of this vesicle is within 100 nanometer, all right? But if this is, yes.
No. Please continue.
Okay. But if this a situation like this, right? If the focal volume is small, isn't it? Molecules are going to come in and diffuse out. Similarly, if you have a wide area and if you have a molecule that you're looking at or molecules that are looking at, which are undergoing motion or fast motion, they diffuse out in solution, then I will not be able to, or you will not be able to probe the molecules for long enough a time. Maybe you will be able to probe it for a frame or two, right? I'm just going to give you an example here of a situation which you just mentioned, or rather an extreme situation that you just mentioned. This is an example of a 100 micron area of molecules which are completely immobilized, okay? The moment I change the viscosity of this medium, okay, you will see that they start moving in. Can you see that? Okay, I'm going to blow it up again for you. I'll show it to you here. You see they're starting move, they're undergoing this motion. Now you can see on the left hand side, I can look at one guy and sit on it and I can collect data. But on the right hand side, they're moving so fast, I will not be able to collect the information in a reliable manner. So if I'm going to try and do spectroscopic measurements, for instance, right, I will not be able to do so because for that, the molecule needs to be in one place. Remember what my objective is. My objective is to collect data, or let's say spectral data or intensity data from one molecule and that molecule only, not from another molecule. Actually, that is the difference between an FCS measurement. Although FCS is a single molecule technique, you are detecting the light, that photons that come out from single molecules, but then you ensemble average. Once you're going to do the correlation function, generate, you're ensemble averaging over a large number of molecules. Here, on the other hand, what I'm talking about is collection of data from one molecule and sticking to it and collecting for a certain time duration and doing the same process over a large number of molecules. That would not be possible if I do not immobilize my molecules. Am I clear?
Yes. Thank you.
Thank you, Paramita, for the nice question. There are two questions in the chat box. Debayani Chakraborty from ISC Bangalore is asking how the images of single molecules are analyzed.
Yes, I have. For that, you have to come to the breakout session because essentially the idea is that, I don't know whether you guys can still see my screen. Can you guys see my screen?
Yes.
Can everybody see my screen here?
Yes.
Right. So, you can essentially think of it like this. I take, these are some single molecules. Can you guys see this? They are single molecules. I open it up in image J, and you can look at the intensity.
No. Arindam,
Yeah.
you have to share as a whole screen probably. We are not been able to see the image.
Yeah, image J we are not able to
Oh,
see.
you're not seeing. I see.
No.
Then
So you can
maybe
stop sharing this one and then share as a whole screen.
stop share. Okay.
And then share as whole screen.
Okay, hold on. I have the screen. Can you?
No, you have the screen, but you just share the entire window. Not just the PowerPoint.
Show all windows, basic advanced files, whiteboard screen. I have the screen.
No, entire screen.
Okay, can you see the screen?
Yes, now it is correct.
Now it's fine. Now it's fine.
All right, this is a data by this is the data. Can you see the movie?
Yeah.
This is actually Yamuna Krishnan's data from a 2016 Nature Nanotechnology paper, right? You can see things are moving around and stuff like that, right? Now, I hope you could see this, right?
Yes.
So similarly, these are not single molecule, they're nanocrystals, but you can see that I can take a region, I can look at the intensity profile, I can see that, no? I can just play around in image J and I can look at the intensities, I can integrate them. If I want to know more about the of things as a function of time, let's say I look at a region, I can find out, how things change.
You can show this.
Right?
Yes, you can show this in the breakout.
Yes. So all these details, I think I can show, in the later sessions. In fact, for the later session, I have also kept it kind of open. But if you want to do spectroscopy, you can fit the data to a Gaussian, and then you can you still see my screen?
Yes.
Okay, so if you're doing spectroscopy, for instance, spectra would look something like this. I had only one slide on the data. As that these are my spectral streaks, certain spectra. Then you can make a rectangle, integrate it and plot it, and then you can fit it to a Gaussian. You can find out peak positions. You can find out widths of it. You can integrate the intensity. So these are very standard ways of doing the.
Okay.
Yeah.
Okay. Just because of the lack of time, just a quick answer to the last question. What is the scanning time to obtain such high quality images in confocal? This is from Ronak at BITS-Pilani.
Ronak, thank you for the question. It actually takes quite a bit of time. It takes about 10 to 15 minutes. 10
to 15 minutes.
10 minutes, yeah. Because you have to sit, if you have to park yourself, you have to go slow to get a really good high quality image that I showed you. That one took 15 minutes.
Sure. Okay. Thank you very much, Arindam.
Really.
We conclude the common talks right now, and we thank all the teachers from the morning, from Sudipta, Anindya, Chandrabhas, Koti, and Arindam for this wonderful set of lectures that you have provided and the effort on a Saturday, and also making sure that the lab is also ready for a demo. So thank you very much to all the teachers, and thank you all for joining. Now what I'm going to do is I'm going to start the breakout rooms, and these breakout rooms will have the names associated with the tracks. There are 5 tracks: FCS, single molecule, just like the one that you heard from Arindam; Raman, that Chandrabhas talked about; ultrafast, that Anindya talked about; and AFM Force, that Koti spoke about. So all those breakout rooms will start right now as I push the button. Please go and join the sessions.
So, Jyotishman, I'm a little confused. So I will log out of here and then join again.
No. You join through the Zoom. I will start the session right now. Yeah. Okay. So now
5
you have
rooms.
to sort of so assign.
How do I know I am in the right room?
No, you will choose. So I'll broadcast.
So I see a lot of names here.
So you have to go to the rooms.
Breakout rooms in progress. It says breakout rooms in progress.
Yes, so people are joining already. Okay.
Yes, but where is my room is where my question is.
You will choose from so I will.
It has names given.
Okay, Sudipta. Shobhan, I could see.
Yeah, go down. It is downstairs.
Ultra fast, Raman, AFM.
Is
I
it
got it.
names are assigned based on
No, people are joining. People are
Yeah,
joining.
people are joining. I can see that.
So
I can
go
see
and
that.
join. Actually, Abhirami has already joined.
Okay.
Raman Demo has joined. Okay, Ultrafast has joined. Yeah.
So, JD, where can I choose the room?
Niche,
Yeah, go
all the
down.
way down.
Go
You
down
have to
in
go
that
all the
breakout
way.
room.
Breakout rooms,
window.
okay.
Yeah, go down. Scroll down.
Scroll
down to
down.
AFM Force.
See, names of
got
the
it,
rooms
got
are
it, got
in
And join.
bold.
Join. Just
Okay, got
join.
it, yes. Yeah.
So just go and join the whatever room
I'll
that you
join
have to
maybe
be in.
after. So, Jyotishman, I had a question. So, the way I was thinking was
So
to keep.
Ultrafast has 9 people right now. Yes, Arindam.
Right.
No, go ahead, go ahead.
No, Ultrafast has 9 people. AFM is joining. There are 4.
Hmm.
Raman has 8. Single molecule has 8. FCS has 18. Yeah, and there are multiple.
It's increasing. It's increasing.
I think
step
if
by
we
step.
wait a little bit, we will
Yeah.
automatically.
Let everybody go there.
Yeah.
Yeah, and then we can go afterwards.
Yeah, meanwhile, Arindam can ask his question.
No, so these are the people, whoever joins now, are going to be the people who are going to stick for today, tomorrow as well, isn't it? And in November 16th.
We are not sure about that actually. Because right
We have
now,
not,
they can go from whatever room to whatever room.
No, what
We are
I'm
going
saying
to
is
decide
that
on the list of names for November after this exercise. But there's no guarantee that people who are there in the rooms today will be there, because there are people who have not joined.
I was thinking about that. No,
Yeah.
that is it's the way I.
No,
you know.
so I request everybody to join a session. There are lots of unassigned names. Sai
No.
Harinath,
No,
Sabyasachi
Jyotishman,
Rakshit,
Jyotishman, that is the right answer, but not to the question Arindam is asking. Arindam wants to know whether people who are in the single molecule room today, are they going to be
they are
in the
not the
single
people.
molecule session
Not
later on?
necessarily. Yes.
Not necessarily. Right now, they are
Then
free to go from wherever to wherever.
I see.
They can be journalists. Yes.
Yeah, they can only just hop around here and there. But generally, people probably will stay for quite some time, I think, for the whole thing.
I'll go to the room, otherwise Orko
I'll
will
go
start
to
before me.
Raman.
No, but wait. I think let everybody else join a little bit, and
because
then
I have to assign. So everybody goes in, and you are like the hosts, right? So you have to give some permissions to people to share. Otherwise, they will not be able to share.
Okay.
What happened? Jyotishman went into the room, is it?
Yeah, probably yes.
Because I'm going to take 10-15 minute break, and then only I'll start. I'll tell them I need a 10-minute break. And
No, but you can go to the room and then tell.
I'll do that. I'll do that. So what happened was, I was preparing kal theke. I was not sure that how much will be covered here, and then how much detail should I go in the next one. And
No, but anyway, you have the
It was
time
fantastic.
still now. Yeah, it was very nice, very nice
What
talk.
happened
And
was fantastic. Everybody enjoyed it. Everybody learned. It was very lucid. I mean, groundwork is done. Now you can go to higher ones. I'll go there. Otherwise,
Go.
Yeah, I'll also go.
Shobhan is also where? Shobhan, you are in which one?
Ultrafast, yeah.
Right.
Have to go
Otherwise,
first.
Orko will leave us out and do it by himself.
Okay.
Kudeta.
Yeah.
Okay, 12. Okay, I'll join the join single molecule. Yes.
Guys, I need to make an announcement. You guys need to choose a breakout room and go inside. Philip, Mansi, Avinash, Lisa, Abhijit, go to a specific breakout room. Sai Harinath, please join a breakout room. Look at the breakout rooms thing and just join there. Scroll down and join any of the rooms. There is Force, AFM Force that you just heard. There's ultrafast, there's Raman, there's single molecule, there's FCS. Guys, please join one of the rooms. You need to join.
See, if you go back, what right? What
Yeah, we only got out of the Raman demonstration. We are still inside.
Yeah, you are in the main terminal. The main.
It's like putting you in a bin.
Bin.
Good, good. I like it. I like it.
Thank you, Bas. Okay.
Great. So see you. Bye.
Yeah, take care. Yeah.
Yeah.
Okay. So there is only one session still running, which is a single molecule. The person is not letting it to be finished.
That's not so surprising.
So
We can go to the room and see. I mean, I have the privilege of being able to go to the room, actual room, and seeing. Like 2 doors away from here.
Yes. So
okay, Orko, good job. We can plan
Orko
that.
did a very good job.
Why is Bansi here? Bansi is not in single molecule.
No, people are coming out now. People are coming out slowly.
Okay. So, Shobhan, what I was thinking is this: can we do it like this? Tomorrow you start with upconversion, and Orko will be in the upconversion lab.
Sure.
Right. So then we can do the demo.
Yeah.
After that, to show the data analysis, you don't have to go back to the TCS/PC lab, right, Orko?
Not really.
To do the, no, he's muted.
Oh, which data you
wanted to show some data analysis, right? You're making DAS, global analysis.
Maybe we can show it.
Show it in the in person.
Okay.
During in person.
Fine. We'll be ready. Or otherwise, let us focus on upconversion tomorrow. Okay?
Yeah.
Sure. I think we'll either call it a day, or how to enter the breakout room?
You go to the breakout more and then breakout rooms.
Where is that?
More, niche, right side. Just beside the leave button. You click on the... No. Click on the 3 dots more.
End.
At the end.
Oh, that I was trying to go to this single molecule group.
Oh, so go to the breakout rooms and join the single molecule.
I don't even see it.
আচ্ছা triple dot ওই 3টে ডট কেটে যাও ওখানে ব্রেকআউট রুম থাকবে
ভাই ডট ফট কিছু নেই I have few. I'm sharing my screen. You show me where there is a dot.
এ বাবা শেয়ারিং বাই স্ক্রিন ভাবে হয় না ওরভাবে হবে না শেয়ারিং বাই স্ক্রিন জুম
No. Zoom will not be showing you that way.
তুমি
You have a more. Just
security
beside
participants chat. no summary, all AI companion, record, show captions, polls, or breakout rooms.
Eight to breakout room.
Single room has 19 people.
Yes.
Yes.
FCS still has 3.
FCS ওরা বেরোচ্ছে না ওখান থেকে বলে দেয়া হয়েছে শেষ হয়ে গেছে
Raman 1. Ultrafast Alisha Khan is still there. I don't know why. AFM,
so
one person may not be there.
so
I just joined the single molecule and
yeah you can
enjoy.
Yes
Let's see also.
মানে I think শোভন went away. Okay.
Okay, then I'll also leave.
Good. So everything is finished, Shobhan. We are done for the day. So thank you.
All done. All done. Very nice. Very well created. I'm sure that tomorrow also will find.
Yeah. So I'll close the session now.
Okay, let's close it.
Okay. Take care. Bye.
Bye.